This is a Harvard University course taught by Dr. David Malin, and we are proud to bring it to the FreeCodeCamp YouTube channel. Throughout a series of lectures, Dr. Malin will teach you how to think algorithmically and solve problems efficiently. And make sure to check the description for a lot of extra resources that go along with the course.
All right. This is CS50, Harvard University's introduction to the intellectual enterprises of computer science and the art of programming. My name is David Malin, and I actually took this course myself back in 1996. I was a sophomore at the time. I was actually concentrating in government because a year prior, as a first year, I'd come into Harvard thinking that I liked history and constitutional law and sort of similar classes in high school. And so when I got here, I rather gravitated toward that which was familiar. I figured if I liked and if I were good at that particular subject in high school, then that's presumably who I'm supposed to be here. But it wasn't until sophomore year that I got up the nerve to step foot in the CS50 classroom. And even then, it was only out of curiosity. Like, I had no intention of studying computer science, of even taking CS50 when I got to campus. But people were talking about it, and there was a lot of like, beware, and it was perhaps for the initiated only, and I didn't really know ultimately what computer science was. But for me, the sort of light bulb went off, and I found that contrary to what I'd seen in high school, where I saw friends of mine like programming away in the computer lab, heads down, sort of antisocially, just doing whatever it was they were doing, it really wasn't that once I got to this particular class in this particular place. It was much more about problem solving more generally and just learning how to express yourself in code in different languages so that you can actually solve problems of interest to you, even if you have no intention of being a computer scientist or an engineer, but just want to be able to solve problems, analyze data, do interesting things in the arts, humanities, social sciences, physical sciences, or really any other field. And indeed, this particular path led me to computer science, but the hope for CS50 more generally is that indeed you just find your way to applying principles that you'll learn over the coming months to whatever field is of interest to you. With that said, it was definitely a lot of work, and not without its frustrations for me, but there was no better feeling than like banging your head proverbial against the wall for some number of hours, even days, trying to fix a bug, a mistake in your code. And then, oh my God, the rush of emotion, of accomplishment, of pride, of exhaustion when you finally solve some problem that's really been weighing on you. It's just so incredibly gratifying, but also empowering. Because unlike a lot of fields, like computer science was built by humans themselves. And so if a human built this, surely you, another human, can understand it as well. And so even though there's going to be some distractions along the way, you're going to see what looks incredibly cryptic if you've never programmed before over time. And with practice, everything just starts to make more sense. And with time and with practice, you just get better at this particular field. And indeed, really, the key to success in programming in general is just to allow yourself enough time. And so at least, thankfully, I quickly got into the habit of starting early in the week, for instance, when writing actual code. Why? Because you're going to like run up against a wall. You're not going to see some bug. Something's not going to jump out at you. And that's fine. That's when you sort of call it a day, take a break, move on to something else, and then just come back to it. And that's what keeps programming fun for me, even all of these years later, whether it's teaching or actually applying it. But there's down the road a history of an MIT hack. And it looked a little something like this in yesteryear. And there was a little sign the MIT students, when they made this hack, on the wall that says, "Getting an education communication from MIT is like drinking from a fire hose, which indeed they have connected to what should have been otherwise just a water fountain. And that's going to be what it feels like sometimes, not just in computer science per se, but just an unfamiliar field. If you're not from STEM, if you're not from CS, that's fine. But so much of it ultimately is going to be absorbed by you and going to be within your grasp by term's end. So just keep in mind that's very much the intent, but you'll be amazed what you're able to create, to accomplish just 3 or so months hence. Indeed, 2/3 of you, contrary to what you might think or assume, have never taken a CS class before. So it's absolutely not the case that the person to the left and to the right surely must know more than you. Indeed, it's quite the opposite. And as you'll see in the coming weeks, as you write your own code and solve your own problems, what ultimately matters in this course is not so much where you end up relative to your classmates, but where you end up relative to yourself when you began. And it really is all about that delta, whether you've programmed or not, just getting something out of a class like this. And if it does take time, and if you do feel those frustrations, but you simultaneously eventually feel that sense of accomplishment, that just means it's all working. And indeed, hopefully, all the more worthwhile and gratifying ultimately as a result. So what are we going to do in the coming week? So here we are in week 0. We'll soon see why computers and computer scientists start counting, if you will, from 0. But week 0 is one in which we explore computational thinking, sort of thinking like a computer and starting to clean up your thought processes, getting you to think, to solve problems more methodically, and then ultimately translating that into code. And some of you might recognize this environment here, aka Scratch, coincidentally also from MIT. You might have used it in grade school. We'll use it today and a little bit this weekend in the course's first homework assignment or problem set, but not so much to kind of play around in a way that you might have if you did use it in yesteryear, but to explore ideas of computer science and programming that we're going to use and reuse every week hereafter as well. Thereafter, we're going to transition just next week to week 1, so to speak, whereby we'll introduce you to a more traditional language, a lower level language, an older language called C. And in C, you're going to use your keyboard, not so much your mouse and pointing and clicking, but you're going to write code that soon is going to look a little something like this. And if you've programmed before, you can probably glean what this is going to do. If you've never programmed before, which is the case for most of you, this too will soon make sense. But this is the most canonical program that most any programmer ever writes, called Hello World. And indeed, that and all of the surrounding syntax above and below just that sentence, Hello World, will soon make all the more sense. You'll learn how to use industry standard tools, so to speak. Pictured here is something called Visual Studio Code or VS Code. You'll use a cloud-based version of it initially, so you don't have to suffer with any technical difficulties or headaches like that. It'll just work right off the bat. But we'll use that tool and others ultimately to then explore ideas in computer science, principles that you can apply. And we'll take a look underneath the hood, so to speak, of your computer at your memory, or RAM, random access memory, where all of the data is ultimately going to be stored. We'll also take a look thereafter at bugs. A bug is a mistake in a program. Here is an actual bug in an actual computer in yesteryear, but we'll teach you how to debug programs, find your own mistakes, find others' mistakes, and improve that code as well. We'll transition then to algorithms, step-by-step instructions for solving some problems, which we'll touch on today too. And if you picture here, this is actually a pretty representative problem. Odds are you haven't had to deal with something like this, but it's representative sorting, for instance. If you think of each of these small bars as being a small number, each of the bigger bars as being a bigger number, you might wonder, well, could you as a human sort all of these bars? Like get all the short bars over here, all the big bars over there. Well, odds are if you're like me, you would probably kind of eyeball it. And if you could physically interact, you might just start grabbing the smallest elements first, put them over on the left, maybe grab the biggest elements, put them over on the right. But what's your algorithm there? Like, how would you teach someone younger than you who's never done that before how to do it? How would you compel your Mac or PC or phone to do something like that? You can't just kind of wave your hand and say, oh, figure it out, move things around. You have to express yourself more methodically. So we'll translate even ideas like this into code too. And that's what the Googles and others of the world are doing constantly as they sort and organize the world's information. We'll use metaphors along the way if it helps. We'll talk about your computer's memory as kind of being like a postal address. Like every mailbox in the world has some form of postal address, street, city, state, country, and the like. And it turns out that's how your Mac, your PC, and your phone also work. You've got a whole bunch of memory, like the picture before, but you can think of it really as individual mailboxes. And you can put anything you want in those mailboxes, and you can go to a mailbox to grab information that's from it. So at the end of the day, that's really all your computer's doing with information. It's just kind of organizing it, not into mailboxes per se, but a term you probably know called bytes, for instance, instead. we'll talk about problems that arise, even nowadays. In fact, most of you are familiar with your Mac, PC, even phone, like spontaneously rebooting sometimes, crashing, the little annoying spinning beach ball or hourglass icon that happens. Like, what is with that? Well, those are just bugs in programs that humans at Apple and Google and Microsoft and others, they screwed up. And they wrote buggy code, and your computer, when it encounters those mistakes, doesn't know what to do. And so 9 times out of 10, so to speak, it just crashes or freezes or the like. But that kind of stuff will make more sense. So even the real world will make sense. And pictured here are some lower level terms we'll eventually get to mid-semester. But generally speaking, when something is going this way, as per this arrow, and something is going this way, as per this arrow, like that does not end well. And that often is what happens when your computer crashes. Someone's using memory up here, but someone else is using memory down here. And then they're not really talking left hand and right hand. So that is just a high-level overview of some of the problems we'll encounter. But we'll focus too on data ultimately. So pictured here is something fairly technical called a hash table. It's an amalgam of something we're going to soon call an array and also something we call a linked list. And these are just fancy terms for describing how you can organize information even more flexibly than just putting individual values in mailboxes. Like, how could you build structures, like actual data structures, so to speak, 2-dimensional structures at that? And so what you're seeing here is a glimpse, as some of you might have recognized, of some Harry Potter universe names, but they're organized somewhat alphabetically. And notice that anytime there's multiple people with a name that starts with H, like Hermione, Harry, and Hagrid, well, they can't all fit in that mailbox if each of these squares along the left is that same mailbox. So you have to kind of chain them together. Well, we'll learn how to do that in code so that even if you get more data than you expect, if your business is booming and you're some web-based business, how do you keep adding and adding information to your software to actually keep up with it? But this, again, is what code's going to soon look like, as soon as next week in week 1, this here being C. But we'll transition in a few weeks to a more modern, higher-level language, so to speak, called Python. Indeed, the course very deliberately, back in my day and now this, introduces you first to C, which, funny enough, many people don't tend to program in certainly every day. I use C generally September, October, November, December when teaching CS50 itself, but it's everywhere nonetheless. In fact, even today's other languages with which you might be familiar, like Python and Java and yet others still, use C, this same primitive language underneath the hood, because it's so darn fast. And as you'll learn over the coming weeks, it really gives you access to and an understanding of what's going on conceptually down here, so that thereafter, after CS50, when you're writing code, you can sort of think at a very high level what's actually going on. So in fact, in just a few weeks, what looks like this in C is going to look instead like this in Python. And you'll better understand what's going on underneath the hood. And odds are after this class, you'll reach for a language like Python more frequently than C, but you're going to benefit from that bottom-up understanding thereof. Thereafter, and towards term's end, we'll introduce you to a few other ideas, like where do you put large amounts of data in things called databases. Not things like spreadsheets like here, but actual databases where using those same kinds of data structures, you lay things out in an interesting way in memory. Thereafter, we'll transition to a very familiar environment that you and I use every day, the web. Like the web has become rather the user interface or UI that we use everywhere on the laptops, desktops, and even mobile devices nowadays. Well, pictured here is a language called HTML. It's not a programming language. It's a markup language. And some of you might have made home pages or portfolios in the past. But you'll understand what's going on here. But more powerfully, you'll understand how the computer sees that same kind of code, builds up a hierarchical family tree type structure in memory, and then you can manipulate that tree with code to actually add more and more information, chat messages, anything on the screen that you like. And finally, we'll tie all of this together by introducing what are called frameworks and libraries, third-party code that makes it a lot easier to solve problems of interest to you. And so in particular here, this is the very first web app that I myself made back in like 1997. I was part of the first-year intramural sports program, not as an athlete, but as the programmer, and I was teaching myself how to build web applications. I only knew C and maybe a little bit of something else at the time, but this became, for Harvard at least, the very first website for the first-year intramural sports program. And it wasn't just a static website with links and images and the like. It was interactive. You could register for sports. We could input exactly who was in a tournament bracket or the like, and it could actually automatically keep track of this data. So there, two, after just 3 months of a class like this, you'll go from writing quite simply this week and next hello world to building things like this for whether it's web, mobile, or other platforms as well, if you so choose. But we'll get you off of the course's infrastructure by the end of the term. You won't be using any toy environments along the way. We'll empower you ultimately to write code after CS50, especially if this is the only CS class you ever take on your own Mac or PC using the same software, but not the cloud-based version thereof. But all of this software is itself free and can be used by you powerfully after the course's own end. But along the way, as you may know, is there this tradition within the class, particularly in healthy times, of a number of events that really brings people together, not just collaboratively academically, but to just solve problems and generally engage with each other as well. Coming up first, CS50 Puzzle Day, which is meant to be not jigsaw puzzles, but logic puzzles that require no prior experience with computer science or programming, but it's just an opportunity to sort of quietly work on a packet of puzzles with some number of friends for prizes and more. Later in the semester, once you tackle your final projects, the capstone of the course, where we don't give you a homework to write, you yourself come up with something to build. We'll get together generally around 7 p.m. in the evening, wrap up around 7 a.m. if you so choose, and it's an evening, a 12-hour opportunity to collaborate with classmates on your very own final project in a large space on campus that ends, if you're awake with us, at 5 a.m. We can hop on some CS50 shuttles and go down the road for some pancakes at IHOP around 6. Of course, this is 6, 7 a.m. at that point, but it's an opportunity finally to lead into what's called the CS50 Fair, which is an end of semester celebration and exhibition of everything that you'll accomplish over the coming months. And in fact, pictured here are some of your predecessors in healthy times. The CS50 Fair allows you to come with your laptop or phone and exhibit to students, faculty, and staff across campus, put together something in person and on video that people can delight in seeing as you exhibit what it is you created and what you learned over the course of the several weeks, and ultimately a chance to just share and inspire others as well. And you'll all walk home ultimately with your own I Took CS50 t-shirts saying as much as well. So with that high-level overview of the course, I propose that we begin to take a look at what computer science itself is and what it is we're going to be doing over the next several weeks at this lower level than 2. So what is computer science, right? If you're maybe like me or new people like my friends in high school, you probably assume that it means programming. And that's absolutely a big part of it for a lot of people, because with code you can write, you can express ideas and solve actual problems, especially involving data. But computer science itself is really the study of information, if you will. How do you represent it, and how do you actually process it? And in that sense, computational thinking is just the application of ideas from computer science, a course like this, to problems of interest to you. Again, in the arts, humanities, sciences, social sciences, whatever the domain of interest is to you. So with that, if computer science is all about information and with it the solving of problems, well, what does it actually mean to solve a problem? Let's see if we can't propose a model into which all of the lessons learned will ultimately follow. And I'd propose that this is problem solving. You've got some input, which is like the problem you want to solve. The goal is to solve it, so that's the so-called output. And then somewhere in here, the proverbial black box, is some kind of secret sauce that gets the work done. And in the coming months, we'll have to decide, well, how are we going to represent these inputs and outputs? And really, how do we code up? How do we write solutions for what it is that's solving the problem of interest to us? So when it comes to representation of information, there's a lot of ways we can do this. And for instance, if the problem at hand quite simply is to take attendance at the beginning of class on the first day of school, well, how could we go about doing this? Well, we could actually use a system called unary. Well, what is that? Well, that's a fancy way of saying 1, 2, 3, 4, 5, maybe 6, 7, 8, 9, 10. And I can use my digits, pun intended, on my fingers to actually count everyone up. And eventually you need toes and whatnot if you have to count so high. But unary is a very simple system of using a single symbol, a human finger in this case, to just solve some problem, like counting the number of people in the room. Let's make this slightly more technical for a moment, a little more mathy. That's just called base 1, where the base under which you're operating has one digit in it, like literally a human finger, and maybe multiple such fingers if you need to count higher. But of course, most of you, if not all of you, generally vaguely know that computers use something other than unary. And even you and I probably don't use this that often. They use what language or alphabet instead? Yeah, so binary. So binary is indeed the system that computers somehow use. So in this case, bi implying 2. And so computers have 2 digits, it turns out, at their disposal. And in fact, if you've ever heard the technical term bit, which is like a smaller version of a byte, more on that soon, well, a binary digit is the origin of that term bit, because if you get rid of some of the letters and you're left from binary digit with just bit, thus is a bit. A bit is just a 0 and 1. It's 2 more digits than you might have on your own finger. And of course, it's fewer, though, than you and I have. You and I typically use, as humans, the decimal system. Dec meaning 10, because you and I generally use 0 through 9. So on the one hand, another pun intended, you've got unary. Computers use binary. We humans generally think and talk in terms of decimal. But at the end of the day, these are fundamentally going to be the same thing, which is to say that it's all pretty accessible to us. Even if you're not a computer person, I dare say you're about to be. So what is a bit? Well, a bit then is a 0 or a 1. That is a so-called binary digit. But how do computers only speak in binary? How do they solve problems, represent information using only binary? Well, at the end of the day, if they want to represent 0 and 1, we need to do so physically somehow. And I dare say that maybe the simplest way to think about a bit, a 0 or 1, is like a light bulb. And so by human convention, let's just assume that if you are a computer, be it a laptop, desktop, phone, or the like, and you want to represent the number 0, you know what? You just keep a light switch off. You keep a light bulb off. If by contrast, you're that same computer and you want to represent the number 1, you take that same switch, that same light bulb, and just turn it on. So a light bulb that's on represents a 1, and a light bulb that's off represents a 0. So why is this relevant to computers? Well, at the end of the day, you and I are charging our laptops or phones at night. So there's some like physical resource being replenished there, whether you're on battery or some power cord. And so inside of a computer are just thousands, millions of tiny little switches nowadays. You can think of them metaphorically as light bulbs, but they don't yet actually shine light. But there are tiny, tiny little switches. And those switches, if you've ever heard the term, are just called transistors. So like computers have millions of transistors that can either be flipped on to represent 1s or flipped off to represent 0s. And from that very simple mechanism, electricity is there or it's not, a 1 or a 0, computers can actually count obviously from 0 to 1, but it turns out even higher if they use a little more electricity as well. So how might I do this? Well, let me go ahead and propose that I just grab one of our own light bulbs here on stage. This one's off. So for instance, if this were miniaturized inside of your Mac, PC, or phone, this would be a transistor. And indeed, here's the little switch on the bottom. And if your computer wants to represent a 0, it just leaves the switch off, and the light is not shining. If you want to represent a 1, well, now I've counted as high as 1, because the switch is now on. I've grabbed a little electricity. I'm holding on to it inside of the computer. And so now I see that this is a 1. All right, but unfortunately, with just one switch, one light bulb, I can only count from 0 to 1. How do I count out higher, might you think, intuitively? Say again? Yeah, so more light bulbs. So let me do this. Let me just grab something to put these on so I can use a few of them at a time. And let me propose that here, instead of having just one light bulb, let me give myself maybe 3 in total. So all of them are initially off. And if you think of this in miniature form in your mind's eye, this is like a computer with 3 transistors, 3 switches, representing now the number you and I know as 0. Why? They're just all off. So how does a computer go about representing the number 1? Well, it turns on one of these light bulbs. And how does the computer represent the number 2? Well, you might think, if I may, you just turn on a second light bulb. And if you might think, how does a computer represent 3? You just turn on the third light bulb. And so as such, with 3 bits, a computer would seem to be able to count from 0 on up to 1, 2, 3. But it turns out if I'm a little smarter here, I can actually count higher than that. Why? Well, I'm just considering like the combination of bulbs being on here. What if I do something like this? This is still 0, I will claim. But what if I propose now that this will be how a computer represents 1? On, off, off. This, though, will be how the computer represents 2. Notice I didn't turn on the same 2. I'm just turning on the 1 in the middle. This, I now claim, will be how a computer represents 3. This is going to be, in just a second, how a computer represents the number we know as 4. And yet I'm still only using 3 bulbs. This is going to be the number the computer represents as 5. This is going to be how the computer represents the number 6. And then lastly, it turns out with 3 light bulbs, if you're smart about it, you can count, it seems, as high as 7. Now, even if you kind of lost track of like what I was turning on and why, I claim there were 8 different patterns, from all of them off to all of them on. But notice that I started to permute them. I took into account which ones were on and which ones were off. Why, though, do these represent the numbers we know as 0 through 7? Well, let me go ahead and maybe let's do this. Instead of just considering there to be light bulbs, let's assign some special significance to each of them based on where it is. And maybe for this, could we get maybe 3 volunteers? 3 volunteers? OK. You're being volunteered. OK, come on up if you want to go over to the stage there. Yeah, you want to come on up as well? And over here as well. So there's some stairs on either end. Maybe a round of applause for our first volunteers of term. All right, so you are number 1. And if you want to go ahead and stand roughly right here, how about you want to be number 2? OK, come on over and right to the right of here, and you'll be number 4, it turns out. And if you want to come over here on this end, let's give you all a moment to introduce yourselves briefly to your classmates if you'd like.
Hi, I'm Ellie. I'm a senior.
Nice to meet.
I'm Rayhana, and I'm a first year.
Welcome.
Hi, I'm Joseph, and I am a first year.
Welcome. All right, so glad to have all 3 of you up here. Thank you. Let me propose now that we'd like you 3 to represent, how about the number 0? And I claim now that if each of you now represents a switch, you have sort of fancier light bulbs now. One is a 1, one is a 2, one is a 4. But each of you still just has a switch on the bottom, in fact, of your plastic devices. I claim these 3 volunteers are representing the number 0. Let me ask you all now, how might you represent the number 1? How should you cooperate here? OK, so we would have on, off, off, which I think matches what I did with my 3 light bulbs as well. If you want to go ahead and turn yours off, how might you all 3 represent the number 2? OK, so off, on, off now, from right to left. How would you 3 represent the number 3? So that's why my 2 light bulbs went on at the end. How would you 3 represent the number 4? Perfect. Number 5? Number 6, and number 7. All right, and give us one more. How would you represent 8? OK, you can't. How about then one more volunteer? One more volunteer. OK, come on up. All right. What's your name?
My name is Moeen.
If you want to say it there.
My name's Moeen.
All right. And Moeen, you're going to be number 8. And if now you all actually, let's make this. How would you represent number 8? All collectively as 4 bits or 4 switches. OK, 8. And now lastly, give me 15. Everyone's awkwardly doing arithmetic in their head. Oh, using unary. 8, yeah, is everyone? 8, yes, OK, round of applause. OK, thank you all. If you want to leave your numbers over here, we have a CS50 stress ball for you. But thank you for volunteering. You can turn those numbers off and leave them over here. So thank you. So how do we go from there to creating these patterns? Well, even though we still had 3 bits initially and 3 switches, later 4 bits and 4 switches ultimately, we still used the same approach fundamentally to actually representing information. And now why were they those patterns, and why did I very deliberately have our volunteers line up in that way? Well, I wanted them using base 2, aka binary. But with binary, there come certain rules. And even if you're not familiar with binary beyond that it exists and relates somehow to computers, it's actually pretty much identical to the system you and I use every day, known as base 10, aka decimal. So let's consider, if you will, by rewinding to primary school for just a moment, like how decimal works. And you'll see that even if you're not a computer person, you actually are. You just have to tweak your mental model ever so slightly. So here is the number that you're probably viewing as 123. But why is that? Well, it's not really 123. This is just a pattern of 3 symbols on the screen. 1, 2, 3, and your mind is sort of rapidly assigning mathematical meaning to them, 123. But why is that? Well, if you're like me, you probably learned back in the day when you have a 3-digit number like this, the rightmost number is in the ones place, the middle digit is the tens place, the leftmost digit is in the hundreds place. And why is that relevant? Well, if you then quickly do some mental math, as you and I just do instantly nowadays, that just means 100 times 1 plus 10 times 2 plus 1 times 3, of course, 100 plus 20 plus 3 gives us the number you and I know as 123. But beyond that, how do we get to just 2 digits instead of as many as 9 in the decimal system? Well, let's generalize this. In the decimal system, you and I know if we've got 3 digits represented by these hashes here, yes, it's the ones place, tens place, hundreds place, and if we keep going, thousands, 10,000s, and so forth. But why is that? Well, base terminology is now a little more germane. That's technically the 10 to the 0th column, the 10 to the 1, 10 to the 2. So these are powers of 10, where 10 is your base. Computers just simplify things a little bit, because computers at the end of the day only have access to electricity, on or off. They don't have access to like 10 different types of electricity, just 2, on or off, if you will. Well, they just use a different base. And the rightmost digit would be in the so-called 2 to the 0s. Then the middle digit is 2 to the 1. The leftmost is 2 to the 2, aka 1's place, 2's place, 4's place. And as we kept going, 8. And if we keep going, 16, 32, 64, 128, and so forth. But the idea is fundamentally the same. So why is this how the computer represents the number you and I know as 0? Well, off, 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 from right to left, or in this case, left to right, is just 0. Why? Because that's 4 times 0 plus 2 times 0 plus 1 times 0 is, of course, 0. This is why 001 represents 1. This is why 010 represents 2, and 3, and 4, and 5, and 6, and 7 on up. And why did we need a 4th bit to represent 8? Well, we kind of needed to carry the 1, so to speak, using our familiar human terminology. But for that, we need a 4th bit, another transistor. And this now represents the number 8. And that's why we ended with on, from left to right, off, off, off. So I keep saying on and off, or the light bulb is on or off. But really, I just mean 1 or 0. And so computers and we humans think of things digitally as just being 0s and 1s. But mechanically, you can think of it indeed as these light bulbs. Now, a bit's not very useful. Even 3 bits, 4 bits, not that useful. You can count to 7 or 15. Generally speaking, bytes are a more useful unit of measure. And anyone familiar? How many bits is in a byte? Yeah, so 8 bits are in a byte. You can think of it as an octet equivalently. In some contexts, there are nuances there. But think of a byte as just being 8 bits. And that's just a more useful measure. So what does this mean in real terms? Well, if you've ever downloaded like a music file or a photograph or a video, those are measured in bytes. Probably not small numbers of bytes. Probably kilobytes for thousands of bytes, megabytes for millions of bytes, gigabytes for billions of bytes, especially for video. That just means you have a lot of patterns of 8 bits, some combination of 0s and 1s on your computer's hard drive. Here then, with a byte of bits, 8 bits is how a computer would typically represent the number 0. And if that same computer uses all 8 of its bits, its full byte to change it to 1, anyone who's quick with math or have seen this before, how high can a computer count with 8 bits or 1? Yeah, 255. Why is that? Well, we're not going to turn this into a constant math exercise. Indeed, after today, we're not really going to think about or talk about bits at this low level. But this is the 1's place, 2's, 4's, 8, 16, 32, 64, 128. And if I do all of that math from left to right, that indeed gives me 255. It ignores how we might represent negative numbers, but perhaps more on those some other day. But computers, of course, do so much more than numbers and math and all of this low-level stuff. We send text messages, write documents, emails, and the like. So how might a computer represent something like the letter A? I claim at the end of the day, your Mac, your PC, your phone just has lots of transistors, lots of switches that it can use in units of 8, in units of bytes. How, though, if it's already using those patterns of 0s and 1s apparently to represent numbers from 0 on up, how do you go about representing letters of the alphabet, might you think? Yeah. OK, so we could assign a number to every letter. OK, so let me just conjecture. Well, let's just call A 0 for simplicity, B 1, C 2. And now let me play devil's advocate. OK, how do I now represent 0 or 1 or 2. Well, we've maybe created a problem for ourselves. If now we have to steal some numbers to represent letters, we kind of have to pick a lane. But there's a solution to that too that we'll see. And it turns out the world is not quite as simple as A being 0. A typically is represented by computers everywhere, phones everywhere, with the number 65, the decimal number 65. Using 8 bits, if we turn some of the zeros to ones, let me just stipulate, you can represent the letter A using 8 bits by turning certain ones on and certain ones off. But we will try not to focus on that binary level too much. So if A is 65, it turns out that B is going to be 66, and C is going to be 67, and so forth. And so where does that get us? Well, it turns out there's a whole system that maps numbers to letters. And here, as I alluded to verbally a moment ago, is the pattern of zeros and ones via which you'd represent 65. And just quick check here, we won't constantly do math. Ones place, that's easy. Twos, fours, 8, 16, 32. 64's place, so 64 plus 1 gives us 65. So once I do that, how do I get to all of the others? Well, it turns out a bunch of Americans years ago came up with this, ASCII, the American Standard Code for Information Interchange. Now, what does that mean? Well, it's just an acronym describing what really you proposed, a mapping between numbers and letters. Not quite as simple as 0, 1, 2. Starts at 65, 66, 67 for capital letters. But here are most of the letters in use today, at least with this system. So this is just a big chart from online. And you'll see in the middle of this chart here, here's my 65A. Here's my 66B, C. And let's see, 72 is H. 73 is I, and so forth. So there's a mapping, at least for English, between all of these numbers and all of these letters. And if we focus here, those are the beginning of our uppercase alphabet. So suppose then that today, tomorrow, you receive a text message from someone. And underneath the hood, now that you're a computer person, you figure out a way to see what pattern of zeros and ones was sent. In this case, it's wireless as opposed to wired, but it's still some pattern of zeros and ones. And your phone is turning some switches of its own on and off to represent that message from a friend. Suppose that the 3 patterns you received were these 3 bytes from left to right, spelling out a 3-letter word. Well, if we do out the math, ones place, twos place, and so forth, I'll spoil it for you. Suppose that you received a text message that doesn't literally say 72, 73, 33, but you received a pattern of 8 plus 8 plus 8, 24 bits that, if you do out the math, represent the decimal number 72, 73, 33. Anyone recall what message you might have received from the green and white charts? Yeah. Hi. But yes, hi is the message. But 72, 73 gives us H and I. What's 33? Any guesses to 33? Yeah, over here. Yeah, so it's an exclamation point. How would you know that? Well, you really do need some kind of cheat sheet, aka ASCII in this case. And if we look elsewhere, let me highlight the left of the chart. You can see that next to 33 in decimal is indeed the exclamation point. So back in the day, a bunch of humans got in a room, decided that, hey, when we start building PCs and later Macs and phones, we all just have to agree on this form of representation of letters of the English alphabet in this case. We just need to agree on this mapping. But somewhat curiously, notice this. It turns out that once you paint yourself into this corner and start using 65 for A, 66 for B, well, how do you represent 65 the number and 66 the number if you want to do math or use Excel or something like that? Does anyone kind of see the solution perhaps? How do you represent the number 1 in ASCII? Yeah, in the middle? Yeah, so this is getting a little maybe Inception or something, but you could represent numbers with other numbers. And so if you want to represent the number you and I know as 1, like when you type it on your keyboard, turns out the computer stores that as the decimal number 49. If you hit 2 on your keyboard, the computer's not storing 2 per se, it's storing the decimal number 50. Now, thankfully, the paradox kind of stops there. We just have a mapping now of numbers to numbers. But really, at the end of the day, and you're going to learn this when we start writing code in that other language, C, next week, it's just context dependent at the end of the day. Inside of your Mac, PC, and phone, there's just all of these permutations of bits, all of these patterns of zeros and ones. And generally speaking, when you open up a text message, that you've received from someone. It's zeros and ones, but obviously if it's a text message, the whole point of text messages is to send text. And so those patterns of zeros and ones by default will typically be interpreted as letters of the alphabet. So you won't see zeros and ones, you won't see decimal numbers, you'll see the English message that your friend intended. By contrast, if you open up something like Excel, that same pattern of zeros and ones might indeed work out to be 72, 73, 33. You might see cells in your spreadsheet with literally those three numbers. Why? Because spreadsheets are all about numbers and number crunching and math in many cases. If by contrast you open up Photoshop and try to look at that same pattern of zeros and ones, it's not going to be 72, 73, 33. It's not going to be zeros and ones. It's not going to be high. It's going to be some color of the rainbow. You're going to use those patterns of zeros and ones, it turns out, too, to represent colors. And indeed, so long as you and I just agree, as humans long have, what these patterns are going to be, all of our systems, many of our systems nowadays are indeed interoperable. But I'm being very biased here. And indeed, the A in ASCII is very American-centric. What do you not see in this chart? If you speak any other language than English, odds are you're not seeing characters you know and love and need every day to type or send messages. Well, there's a huge character set that's not supported here, whether it's accented characters and a lot of Asian alphabets. You have many more symbols than can fit even on this screen here. And so humans kind of painted themselves into a corner early on, or really Americans did. But on a typical keyboard, US English keyboard, yeah, you have A's and B's and C's, uppercase and lowercase. But you also have accented characters here. And nowadays, not sure if this is maybe necessary, but nowadays you have other characters on your keyboard like these. And these are kind of a playful incarnation of what's actually a technical solution to this problem. If I claim for the moment that ASCII historically used 7 bits to represent letters, and let's just round that up to a byte, 8 bits to represent letters, ASCII can represent as many as 255, or really 256 total characters. Why 256? Well, if you have them all 0, that's 0. And the highest number I claimed a moment ago was 255. So that's 256 total possibilities. That's not many letters. It's fine for English, but not a lot of human languages. So what might the intuitive solution be if you want to represent accented characters, Asian characters, emoji, even like these, which are just keys on a keyboard nowadays? What's the intuitive solution if a byte's too few? Yeah. Yeah, so add another digit. Just like we had a 4th volunteer come on up to give us a 4th bit, let's just throw hardware at the problem and use a few more bits. So maybe instead of 1 byte, let's use 2. Or heck, let's use 3 or 4 bytes. Even though it's getting a little expensive, we're going from 8 to 16 to 24 or 32 bits. That's how computers do things these days. And thankfully, we have so much memory inside of our computers and phones, we can certainly spare a few to represent these things. And the solution then to ASCII is what we'll call Unicode. So Unicode is also just a mapping of letters to of numbers to letters, but in many different languages. And indeed, the Unicode Consortium is a bunch of people from all different companies and a lot of different companies and countries and cultures whose mission as an organization is to capture digitally all forms of human language in this case, and to ensure that especially smaller demographics of humans speaking lesser known languages are nonetheless represented and preserved digitally using some mapping of these zeros and ones. It turns out, though, if you start using 32 bits, as many as 32 bits to represent characters on a keyboard, that's 4 billion possible permutations of zeros and ones. That's way more than we need for most human languages. So there's a little bit of room in there for some of those more playful things, like those emoji. So for instance, suppose you got a text message with this pattern of zeros and ones. Or if we do out the math, suppose you receive a text message that if you do out the math in decimal is 4,036,991,106. Anyone know what emoji you're looking at? It'd be weird if you do, but what is this? Well, it turns out that as of this past year, this is the most popular emoji to be sent by many measures, face with tears of joy. So that is the pattern that a bunch of humans in the Unicode Consortium decided would represent this. But you'll notice many of you might have iPhones, some of you might have Android devices too, and sometimes these don't actually look quite the same. This happens to be the current version of face with tears of joy on iOS. On Android, it tends to look a little something more like this. And here's kind of a curiosity. Even though you and I look at these things and they look like images, They're not images. They're characters, at least as we've defined them now in Unicode. And iOS and Android and Windows and Facebook and other companies and apps nowadays really just have different fonts, if you will. So just like fonts with English and other languages can give you different characters with serifs or not, emoji are themselves, yes, drawings that someone made, but they're really just a font. And so that same pattern of zeros and ones might just render slightly differently on someone's phone or another. If you've ever gotten like an icon on your phone that's broken and you've been sent an emoji, but it's like a square or something arbitrary and not sensible, it might just mean that you have not updated to the latest version of iOS or Android, which just updates the font of supported emoji, because those folks at Unicode pretty much every year nowadays are adding more and more emoji to that particular character set. Now, I went down the rabbit hole figuring out the other day just which are the most popular emoji these days. On Twitter specifically this past year, the most popular emoji, by contrast, was loudly crying face. I don't know if that says more about 2021 or about Twitter, but you'll see different trends certainly in how these are used. But even humans themselves didn't necessarily think 2 steps ahead. And now a lot of the emoji are this sort of default yellow color, but there's a lot of emoji that aren't sort of these cartoon characters, but they're meant to represent humans in various professions or gestures or the like. And nowadays, too, you've probably noticed on your phone, and Macs and PCs, there are different skin tones that you can assign to certain emojis. If it's supported by the company and by Unicode, you can actually like touch and hold on a certain emoji, and then you can choose the appropriate skin tone to represent yourself or someone else, and that then modifies the display. Well, let's just think for a moment here, how did Apple and Google and Microsoft and others go about implementing support for emoji with different skin tones? How could you do this? If you want to represent some smiling emoji, but in 5, in this case, different skin tones, you could come up with what? 5 different patterns that are identical structurally, except for the skin tone used in places in that image. But that's a little inefficient, right? To kind of just do copy, paste, 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 and like change the color in Photoshop, if you will. That's going to use more bits, more information than you might need to. How else, if you now start to think a little bit more like a computer scientist, if at the end of the day all you have are zeros and ones, how else could you implement skin tones, might you think? Yeah. OK, so RGB, we'll come to that in just a moment. That stands for red, green, blue. That's one way. In this case, though, I'm seeking an alternative to just using 5 different patterns of zeros and ones to represent the same emoji, but different skin tones. So not quite RGB. Yeah. OK, so store one copy of the emoji and then store different variants of the color that you want to assign to that emoji. Yeah, so this is actually an example of, do you want to elaborate? OK, so you can use a loop to actually output these things. More on that in a moment. Let me go down this road for just a moment. This would be, in some sense, sort of a better design, if you will. But why? Yeah. OK, so filter, if we think sort of in the Instagram sense, you can sort of change the color of something. And that could be related here, too. Oh, interesting. So maybe it could be just a completely different font. And you have 5 different fonts that are almost identical, except for the various interpretations of skin tone for those same emoji. Let me spoil. I think if we go down this one particular road, the way the Unicode folks decided to do this some years ago were the first byte or bytes that you receive via text or email just represent like the structure of the emoji, the default yellow version thereof. But if it's immediately followed by a certain pattern of bits that these humans standardized to represent each of these different shades of skin tone, then the phone, the Mac, the PC will change that default color, yellow in most cases, to whatever the more apt human tone is. So you just use twice as many bits, but you don't use 5 times as many bits. So what do I mean? You don't have 5 completely distinct patterns per se. For each of these possible variants, you have a representation of just the emoji itself structurally, and then reusable patterns for those 5 skin tones. Unfortunately, that wasn't quite versatile enough for other features that were in the pipeline. And nowadays, too, and there's a double meaning now to representation, emojis had tended to focus on certain professions. And early on, too, were certain professions associated with certain genders and vice versa. And you couldn't necessarily be one gender or another in a certain profession or another. There were these combinatorics that just weren't possible. But nowadays, as you might have seen, you can have couples in love, for instance, that actually look a little more like 3 emojis, but just kind of combined into one. And indeed, this is is just one key press on your phone. And you can combine different emoji on the left and on the right with an emoji in the middle. And so it turns out how computers nowadays represent these patterns are one set of bits for the character on the left, one set of bits for a character on the right, one set of bits for whatever emoji you want in the middle, and then you assemble more complicated compositions of emoji by just reusing those same patterns and bits and bits. Emoji doesn't, the Unicode folks don't have to come up with a whole new representation for some very specific incarnation. They can create one for person, for male, for female, for other characters that you might want to display and reuse those same patterns of zeros and ones. And so here you see sort of the imperfection of or lack of foresight of humans for building a system early on that was entirely American-centric, no characters, emoji, or the like, that's evolved to. And so that's an important detail in computing nowadays. It too is evolving. And the languages you're about to learn in the coming days, those too are evolving as well. And new features are getting added. And even programming languages have version numbers. You might have a different version of an app on your phone. Programming languages too have different versions as well. Questions then thus far on how information is represented using ASCII or Unicode or anything in between. Yeah? Oh, good question. So to recap, why can't you just, let me summarize that as, why can't you similarly use different patterns to change the context of what these patterns of bits represent, whether it's a number or a letter or a graphic? In actuality, that's kind of what's happening underneath the hood. It's not standardized in quite the same way, but starting next week when we transition from Scratch to C, you'll learn about types, data types, where the onus initially is going to be on you, the programmer, to tell the program whether or not this pattern of bits should be interpreted as a number or as a letter or as a color or something else. Nowadays, though, and toward the end of the semester, you'll use languages like Python, where the computer just figures it out for you by context, which makes it even easier and faster to program as well. Other questions on Unicode, ASCII, or the like? All right, well, how about just a few other forms of information? RGB was called out earlier, red, green, blue. How do images get represented in computers? Well, in fact, it's typically an assembly of some amount of red, some amount of green, some amount of blue. But there are other representations. If you're a graphic designer, you might know them. But RGB is still pretty common. What does this mean? This means to represent every dot on your phone or every dot on your TV or your laptop or desktop, there is a number representing how much red that dot should show, a number representing how much green, and a number representing how much blue it should show, red, green, blue, respectively. So for instance, if a dot on your screen, we're using these three numbers, these three values or bytes, 72, 73, 33, in a text message or email, that would be interpreted as I claimed hi. But in Photoshop or in some graphical program, that same pattern would be interpreted as, let's call it a medium amount of red, a medium amount of green, and a little bit of blue. And why medium and little? Turns out that each of these are bytes. The smallest value you can have in a byte, we said, is 0. The largest value you can have in a byte is 255. So I'm just kind of spitballing here. This is like medium, medium, and a low amount of red, green, blue, specifically. Those three colors, like wavelengths of light, are combined in such a way that you would have this dot on the screen, a sort of murky shade of yellow or brown. That is how a computer would store precisely that color. And in fact, we've seen this color. When you type in "faced with tears of joy," generally on your screen it looks like this, typically much smaller. But let's zoom in. Or let's zoom in a little more. What are you starting to see, if you know the term? So pixels, it's getting very pixelated. A pixel is just a dot on the screen. And if you really zoom in on it, you can literally see all of the dots that compose an emoji, in this case on iOS, in the font that Apple's using to represent this particular pattern of zeros and ones. So one of those yellow dots, and there's many of them, all that kind of blend together here, each dot on the screen, I claim, is 3 bytes. How much red, green, blue for this dot? How much red, green, blue for this dot? How much red, green, blue for this dot? And you'll notice, too, that when it gets to be sort of brownish here, the dots really stand out. The 3 values, the 3 bytes, aka 24 bits, are just slightly different. And so underneath the hood, this is why images, photographs that you take, or GIFs that you download get so darn big, potentially, because you have a number representing every dot on the screen. Well, if this, I claim, is indeed how images are typically represented, using pattern of bits that are assigned to some amount of red, green, or blue, how do you get video? What is a video if at the end of the day all we have are zeros and ones? What's a video, perhaps? Yeah, Oh, let's go here. Way in back. Yeah, pixels really changing values over time. And do you want to confirm or deny the hand that went up here? Yeah, or equivalently, a sequence of images that over time are changing on the screen. So both of those are valid interpretations. And just for fun, if you grew up with these sort of picture books, you might remember a little something like this. If we could dim the lights. That's sort of the old school analog way to implement a video, in the sense that that artist wrote out like hundreds of pieces of paper with almost identical images, but where the ink from their pencil or pen was slightly moving. And if you digitize that such that each of those strokes are represented with dots instead, that's really what you're seeing, is a sequence of all of these images flying across the screen. And if we dive into the real world, if you've ever watched a film, a Hollywood movie is typically 24 FPS, frames per second. That really means you're seeing 24 images per second. Or on TV or in soap operas, it's often 30 frames per second. That makes things look a little more smooth. So it's not actual motion picture, if you will. It's sequences of pictures. And your brain and mine are kind of interpolating that, oh, this is smooth movement, even though we're just seeing a lot of pictures really fast. Now, that gets really big. And we'll talk later in the semester how you can compress information so that you're not using way more bits than you actually need to. And there's fancy algorithms that folks have developed. But at the end of the day, that's really all a video might be, is a sequence of images. Conversely, if you want to represent the music that accompanies that or something else, if any of you play an instrument and can read sheet music, how could you digitize this? Like, how could you represent musical notes in a computer? You and I hear them when we play files, but what's really going on underneath the hood? Any musicians? Piano players? Anyone? Yeah. OK, so hertz value, so some frequency. So sound is some frequency, and it's kind of hitting your eardrum, and that's what makes it sound low or high or somewhere in between. So maybe we could assign, just like there's letters A through G here, maybe we could assign specific frequency values, which are just going to be numbers measured in something called hertz, something per second. And maybe we could have a few other numbers for each of these notes, not just the note or the frequency. Maybe we could represent the loudness of it, like how hard or how softly a human might equivalently press it. Maybe a third number, like duration, like how long is their finger on the keyboard. So you could imagine quantizing something like music that in the real world is perfectly continuous as something more discrete by representing each note over time as just some sequence of values. And there's so many different ways to do this. MIDI, if you've heard, MP3s, AAC. I mean, almost all of the file extensions you see on your Mac or PC, if you see them at all, ultimately just mean there's a different form of representation for, in this case, something like sound. So let me just stipulate, there are these and many more ways to represent inputs and outputs. And thankfully, humans have standardized a lot of this. They don't always disagree. And this is why we have different file formats for Apple numbers and Microsoft Excel and Google spreadsheets and sort of stupid incompatibilities like that. But generally speaking, humans have standardized how we represent the inputs and outputs to and from problems. But let's now focus on this black box, so to speak, in the middle, this abstraction. So abstraction is technically a term that you'll see all over the place in computer science and really problem solving that just refers to the simplification of something so that you don't focus on the lower level implementation details. You really just focus on the high level goals or the process itself. Therefore, your car, if you have a license and have driven or have been in a car, so far as you're concerned, is probably an abstraction. Most of us, if you're like me, probably don't really know or care how the engine works and all the parts that are moving. To you, it's just a way of getting from point A to point B. It's an abstraction. But someone, hopefully, the mechanic, does know those lower level implementation details. If you had to understand how a car works every time you want to go to school or to the store, it's probably going to be a pretty slow process. You just want to think and operate at this higher level of abstraction. And we're going to do this all the time when writing code and solving problems. So what then is in this black box, this abstraction at the moment? Well, generally, it's what a computer scientist would call an algorithm. Step-by-step instructions for solving some problem. Now let's consider the implementation details. That is to say, how you might solve certain problems. And let's take a sort of old school example, but in modern form. This icon, if you have an iPhone, is of course for your contacts application. And if you've got a whole bunch of family members or friends or colleagues in your phone book, you have some kind of contacts pictured here. And it's alphabetized typically by first name and last name. And odds are you and I are in the habit, if they're not already a favorite, of like clicking on search and then using autocomplete. And what happens when you start typing autocomplete? Well, if you type in the letter H, you'll see only, presumably, Hagrid, Harry, Hermione, and so forth. If you type in HA, that shows you only Hagrid and Harry, and it all happens super fast. So how is that happening? Well, typically, you could just start at the top and look to the bottom searching for all of the H's or all of the HA's. But for larger data sets, that's going to get slow. For the Googles of the world, that's going to get really slow. And even on our phones, when you have hundreds, thousands of contacts eventually, even that kind of approach, that algorithm step by step might be slow. So how might we go about searching for someone in a phone book like this? Like, say, John Harvard, well, here's an old school incarnation of this. And odds are you might not have had occasion to even physically use this thing nowadays. And in fact, this is a bit of a white lie, because this is the yellow pages, which means this is a book of companies, not people. But this is all you can find. And at that, it's even hard to find this. But this is the same thing in analog form, physical form. So if I wanted to search for someone like John Harvard, how could I do that? Well, I could start on page 1, and I could start searching for page 2, page 3, page 4, page 5. A little hard to do physically, especially since no one's used this phone book in a lot of years. But is this algorithm correct? Turning page by page. Very inelegantly. Is this correct? Will I find John Harvard if he's in here? All right, so yes. I mean, this is a little stupidly tedious, because if there's like 1,000 pages, he might be a few hundred pages into this. But it's correct. At some point, I will find him. And if he's on the page, I'll be able to call. Why? Because presumably the names are alphabetized in here. And there's no like cheat sheet on the edge. So I have to search for John Harvard from left to right, searching for H if it's alphabetized by last name. Well, what would be marginally better? Well, how about 2 pages at a time? It's hard to do with a 20-year-old phone book where the pages are kind of grown together. But 2, 4, 6, 8, 10, 12. This algorithm, is this correct? All right, so no, why? Yeah, so I'm skipping every other page. So if I don't consider that and I find myself in like the I section or the J section, well, I might accidentally conclude, nope, I haven't found John Harvard yet, just because I skipped him because it was sandwiched between 2 pages. Now, I can fix this, I think. If I do hit the I section, well, let me just double back 1 page, just in case he was in that last page. So it's recoverable, but it's almost twice as fast, minus that hiccup there. But what most of us would do, and what your phones are doing, albeit digitally, is they open up roughly to the middle of the phone book. And they look down and they say, oh, I'm in roughly the M section. So I'm roughly halfway through this 1,000-page phone book. But what do I now know about John Harvard? Where is he? To my left or to my right? All right, so alphabetically, he's presumably to my left. And so here I can both metaphorically and physically tear the problem in half. You don't need to be impressed. It's really easy down the spine that way. But I know that John Harvard is to the left here. But now I can throw, unnecessarily dramatically, half and page 1 out of the way. And what do I now know? I've gone from 1,000 pages to like 500. I can kind of repeat roughly the same algorithm, go to the half of this. And so this time I went back a little too far. I'm in now the E section. So what do I know? Is John Harvard to my left or to my right? To my right. So I can, again, tear the problem in half, throw this half away, and now I'm really flying. I'm doing it verbally slowly, but that went from 1,000 pages to 500 to now 250. And now I can do it again, 125. I do it again, roughly like 67, and keep doing it again and again and again until I get left with, hopefully, just 1 single page, or in this case, an ad for, ironically, a mechanic. OK, so what is the implication for our performance? Well, let's just do this, sort of in the abstract, if you will. If that first algorithm were to be plotted just quickly on a chart without even numbers, here's my x-axis, size of problem on the x-axis. So the bigger the problem, the farther out that way. Time to solve the problem, the higher you go up on the y-axis, the more time you're taking to solve it. How would we draw the running time, the amount of time taken to run that first algorithm? Well, it's going to be a straight line. Why? Because if you add 1 more page next year, because more people move to Cambridge, you're going to add 1 more page turn potentially. So 1 more second, 1 more unit of time. So it's a straight line, and we'll abstract it away as n. If there's n pages in the phone book, the slope of this line is essentially n. The second algorithm, wherein I was doing 2 pages at a time, was twice as fast, but it's still a straight line. And in fact, let me just draw some dotted lines here. If the phone book is this big, with my first algorithm, it might take this many units of time, this many steps, this many page turns. But with that second algorithm, notice that the intersection is with much lower on the yellow line than on the red. So n over 2 means there's half as many pages here, if n is the number of pages. So indeed, that algorithm, the second one, is twice as fast, minus the little hiccup that I have to double back one page. But that's not a big deal if I'm still doing things twice as fast. But the third algorithm looks fundamentally different. It looks like this. Logarithms, if you recall from high school or prior. If you don't, that's fine too. It's just a fundamentally different function, a different shape. And notice that the green line is going up and up and up, but a much slower rate of increase, which means crazy things are possible. If two towns in Massachusetts, like Cambridge and Allston across the river, merge next year, for instance, in terms of their phone book just got twice as big. For the first algorithm, that's going to take me twice as many steps to go through. The second algorithm, almost twice. It's going to take me 50% more steps to go through, 2 at a time. But the third algorithm that I ended with, tearing things again and again, dividing and conquering, if you will, in half and in half and in half, how many more steps will my third algorithm take if Cambridge and Allston merge into a phone book that's twice as big? Just one more step, right? No big deal. You just take a really big bite out of the problem once you decide if John Harvard is to the left or to the right. And so you've made much faster progress. And so this, in essence, is what your computer, your phone, is probably doing underneath the hood when searching for Harry or Hermione or Hagrid or anyone else, because it's that much faster, especially when you have large data. If you don't have that many contacts, it probably doesn't matter if you search from top to bottom or more in the form of this divide and conquer algorithm. But if you're the Googles of the world or you're analyzing large data sets, indeed, this is going to add up quite quickly. So where do we go with this? Well, we're going to introduce next something called pseudocode. How can I translate what I did verbally there sort of intuitively to actual code? Well, this won't be Scratch, this won't be C or Python just yet. It's just going to be an English-like syntax. And this is how many programmers would start solving a problem. They don't start typing out code in C or Python or the like. They use English or whatever their human language is to jot down an outline for their ideas. My first step really was picking up the phone book. My second step was opening to the middle of the phone book. My third step was somewhat different. Look at the page, because why? My fourth step was, if person I'm looking for is on the page, I then do what? Never happened in my example, but I call the person, so I'm done. Else if the person is earlier in the book alphabetically, as John Harvard was in the case of my H, then I should search to the middle of the left of the phone book. And then I should go back to step 3. Step 3 is look at the page, thereby repeating the same process again and again. Step 9, though, might be else if the person is later in the book, then let's go ahead and open to the middle of the right half of the book, and then go back to line 3. Else there's a fourth scenario we should probably consider, lest my search process freeze or crash or give me one of those spinning beach balls with a bug. Yeah, what if John Harvard isn't in the phone book? I'd prefer that my algorithm, my phone, not just reboot or freeze. I should handle that with some kind of catch-all. Else, so to speak, let's just quit the program. So there's well-defined behavior for every possible scenario of the 4. Now let's call out a few of these salient terms. It turns out if I highlight in yellow here, there's a pattern to what I've been doing here. These are all of my English verbs. And in a moment, we're going to start calling those verbs functions. When you program or write code and you want the program or the computer to do something for you, some action or verb, we're going to refer to those actions or verbs as these things called functions, like those here. By contrast, I've just highlighted instead my if, my else if, my else if, and else. This is going to represent what we're going to start calling a conditional, a proverbial fork in the road, where you can either go this way or that way, do this thing or this other thing. And you're going to decide which of those things to do based on what I've now highlighted here, which are going to be called Boolean expressions. Bool referring to a mathematician last name Boole. A Boolean expression is just a question with a yes, no, a true, false, a 1 or a 0 answer, if you will. And it governs whether you do this thing or this thing or this thing or that. The indentation in this case is important. The fact that I've indented line 5 implies, by convention in programming, that I should only do line 5 if the answer to line 4 is a yes or a true. And same for these other indented lines as well. And the last characteristic here is this here. Someone called this out earlier, in fact. These lines 8 and 11 are now highlighted and represent what? What might we call these in code if you've done that? Yeah, so these are loops, some kind of cycles that result in my doing the same thing again and again. But there's a key detail with this algorithm in pseudocode. Even though it's telling me to go back to line 3, why is this algorithm eventually going to stop? Why do I not constantly keep looking for John Harvard forever by nature of these loops telling me to keep going back to line 3? Good. Eventually, he'll be on the page, or to your point earlier, he won't be at all, and we're out of pages, and so we just quit. And that's the key about going to the left half or the right half. It doesn't matter if you do the same thing again and again. You're not going to get stuck in a so-called infinite loop so long as you keep dividing the problem and shrinking it into something smaller, smaller, smaller. Eventually, there's going to be no problem left to solve. So even if you don't think of yourself as a computer person, even if you've never written code, what you'll find in the coming days is that these ideas that we've just kind of harnessed from real life are at your fingertips already. And a lot of the process of learning to code is just going to be a bumpy road, some bumps in the road because you can't quite see the new syntax in a familiar way. But you'll find that the ideas, in fact, are going to be more familiar than you might otherwise think. And so we'll see in a bit, and we'll take a break in a moment to take a breather, that you will see these same ideas in a moment in the context of Scratch, an actual programming language via which we'll drag and drop puzzle pieces to make actual code work. We'll see some variants of these ideas, things called arguments and return values and variables, but we'll ultimately convert it into this somehow. Anyone want to wager what this program will do if fed to your Mac or PC or phone? Here's just a massive pattern of zeros and ones. It will indeed say, rather disappointingly apparently, just hello world. And indeed, baked into all of these zeros and ones are not just the H-E-L-L-O, but also the verbs, the action of printing something to the screen. And there's other stuff too, so that the program knows how to start and how to stop. A lot of stuff that we won't have to worry about that whoever designed the computer or the language did. But at the end of the day, you're never going to be writing these zeros and ones yourselves, though our ancestors once upon a time did in some form. We'll be using a much higher level language like this in C, or better yet, in just a moment, like in Scratch, like this. And indeed, this is why today we focus on and begin with Scratch, this graphical programming language, so we have a way of expressing ourselves with functions, conditionals, loops, and more, but in a way that doesn't have stupid parentheses and curly braces and all of these visual distractions in the way. And we'll translate that thereafter to this lower level language. But for now, that was a lot. That was definitely a fire hose. Let's go ahead and take a 10-minute break. Feel free to get up or stay here, and we'll resume in a bit with some actual code. So this then is Scratch, a graphical programming language from our friends down the road at MIT's Media Lab that indeed some of you might have used in grade school or the like for playing and writing code and the like, but you maybe didn't necessarily think about how some of these primitives ultimately worked. And in fact, everything you've done, if you've used Scratch before, and everything you'll see today is going to apply to all of the weeks to come as we explore these things called functions and loops and conditionals, Boolean expressions, and more. With Scratch, because it's so graphical and animated, can you create animations like this one, interactive art, and software more generally. But you'll do so by dragging and dropping puzzle pieces that only lock together if it makes logical sense to do so. And what you won't have to deal with in this first week of class is curly braces, parentheses, all of the weird symbology that you might recall seeing when we just wanted to say hello world. Now, this particular program, Raining Men, was written by a former CS50 teaching fellow, Andrew Barry, who's actually now the general manager of the Cleveland Browns, the American football team. And so these are just some of the programs that some of your predecessors in the class have created. And you'll see in the remainder of class here a couple of others as well and more in the course's first assignment, namely problem set 0. So how do we get there? Well, first, a quick tour of what it is we're going to do. This, in Scratch, is perhaps the simplest program you can write. And even if you've never seen Scratch or any programming language before, can probably guess that this just says on the screen somehow, hello world. But what you don't have to do is type esoteric commands and weird syntax, those curly braces and parentheses I keep alluding to. You just drag this yellow puzzle piece, you drag this purple puzzle piece, let them magnetically lock together, so to speak, click a button, and boom. With those same building blocks and several others, can you make exactly the sorts of things that Andrew brought to life as well. So here's what we're about to see. At scratch.mit.edu is a cloud-based programming environment on MIT servers. You can also download it offline on your own Mac or PC. And it gives you an interface like this. On the left-hand side of the screen, you'll see a blocks palette. These puzzle pieces, aka blocks, come in different colors which rather categorize them. So pictured here, for instance, in blue, are a whole bunch of motion-related blocks. So Andrew used a whole bunch of those to have the singer and the men moving around on the screen in synchronicity with the song that was playing in the background. Meanwhile, in the middle of this interface is going to be the code area. And this is where Andrew and soon you will drag and drop some of those puzzle pieces and other colors as well and lock them together to get your characters, soon to be invented, to do something on the screen. Indeed, at the bottom right here, will you see ultimately a sprite area, where a sprite is a technical term for like a character in a video game or a programming environment like this. By default, historically, Scratch is the cat, the mascot, if you will, for this programming environment. And so here we see by default just one sprite selected, because on the top right of the screen is the stage for that sprite. And you can click and zoom in to make it full screen. But this is the world in which Scratch, by default, the cat, will live. But you can change Scratch's costume so that it looks like a singer or a man falling from the sky or the like, or anything else, either creating the art yourself or importing some of the things that come with it or elsewhere online. So what is this world that Scratch rather lives in? Well, generally speaking, we won't have to care too much about numbers, because we'll be able to ask questions like interactive ones, like is Scratch the cat or any character otherwise touching the edge of the screen, touching something else. But Scratch does exist in this two-dimensional coordinate system world. So when the cat or any character is dead center in the middle, that would be XY location 0, 0, if you will. Meanwhile, over here is 240 pixels or dots all the way to the right. So this would be 240, 0, where y is 0 because it's right on that midline. So it's neither up or below. Over here to the left, of course, would be negative 240 and 0. Above the cat would be x equals 0, because it's right on that vertical midline, and 180. And then down here, as you might guess, would be 0, negative 180. Generally speaking, we don't have to care about those precise pixel coordinates, but it's helpful ultimately if you do want the cat to move up, down, left, or right, having some sense of direction according to the x-axis and y-axis as well can help you express your ideas ultimately. So what might some of those ideas be? Well, let's do this. I'm going to go ahead and create on scratch.mit.edu just an empty screen like this one here. And so this is the exact same interface, but now I'm in my browser, full screen, so that I can start writing some code. And let's get that cat to say something actually on the screen. Now, this takes a little bit of practice, but honestly, just by scrolling through these puzzle pieces, can you quickly get a sense of what's possible, not just categorically, but specifically? And I'll jump around, because I've done this, of course, before, but I'm going to go to events in yellow first. And I'm going to drag and drop this first block called when green flag clicked. And I've zoomed in there just to make it a little more legible. And notice that the shape of this green flag just so happens to mirror this green flag here at top next to this red stop sign of sorts. And the green flag is going to mean go, and the red stop sign is going to mean stop, to start or stop our program. Next week, you're going to be writing a textual command at your keyboard to do the exact same idea, but for now it's a button. So when green flag clicked, what do I want Scratch to do? Well, how about we have Scratch just initially say something like hello world, which indeed historically is the first program that most any programmer might write. So anything related to what the cat looks like it's doing is actually going to be under looks here in purple. So I'm going to drag over say hello. And you'll notice something curious and different about this purple block. It says, of course, say in purple, but then there's this white oval and some text that by default is hello, because MIT just decided that by default the placeholder will be hello. But anytime you see this white oval, it's an opportunity to provide an input into the function called say. And so here I'm borrowing terminology from before. Problem solving, again, is all about inputs, producing outputs, and in between there is some algorithm. In a moment, we're going to start referring to algorithms quite frequently as functions. Why? Because it's the implementation of some algorithm. So let me override the default with hello, world. I'll zoom out. And now if I go to the top right of the screen and click the green flag, we'll see, hopefully, my very first program in code. Now, it wasn't a huge lift, right? It only was a matter of dragging and dropping puzzle pieces. But what has now happened? Well, it turns out that two things have happened. When I, the human, clicked on that green flag, I triggered what we're going to start calling now an event. An event is generally something graphical or interactive that just happens in a computer program. You and I trigger events on our phones all day long. Whenever you tap or drag or long press or pinch or any of those gestures invoke vogue nowadays on phones, you are triggering events. And people at Apple and Google and elsewhere have written code that listen for those events and do something when that event happens. That's what I just did. When green flag is clicked, I want something to happen. Namely, I want this purple function, this verb, this action called say, to do something. What do I want it to do? I want it to say what this input is. And I'm going to introduce another vocabulary term. The white ovals here are, yes, inputs very generically. But in a programmer's terminology, they're called arguments, otherwise known as parameters. And that just means an input to a function that modifies its behavior in some way. When I click stop, that's just another event. And that one is just built into Scratch. Scratch knows that when you click the green stop sign, everything should just stop automatically. I don't have to write code to support that feature. So that's all fine and good. Hello world. But if I keep doing stop and start and stop and start, it's going to do the same thing again and again. And it's really not that interesting at the end of the day. Maybe gratifying once, but it'd be nice if this were a little more interactive. So it turns out that we can do that too, but we need a different mental model instead. So in this case here, when we think about this function say in this input hello world, this actually maps pretty cleanly to this model earlier that I propose is problem solving, is computer science, if you will. The input to the current problem is going to be in white here, hello world. The algorithm is the say algorithm. Now, I don't know how MIT got it to print out the little pretty speech bubble on the screen, but they wrote those underlying low-level implementation details, and they gave me and you a purple function called say that just does that for you. You and I don't have to reinvent that wheel. The output of say is another technical term now called a side effect. A side effect is usually something visual that happens, like as a side effect of you calling a function. And so the side effect here is that the cat has this speech bubble magically appear, inside of which is hello world. So we have an input, we have an output, we have an algorithm, but now we're talking about these ideas in the context of programming. So now the input is an argument. The algorithm is a function, and the output in this case is a side effect. Terminology that you'll just hear more and more, and it'll eventually sink in. But not to worry if the terminology doesn't come naturally early on. So what more might I do with this? Well, let me go back to Scratch here and make this maybe perhaps more interactive and actually get the cat to say something a little more dynamically. So instead of hello world, why don't I get it to say hello to me or to you or anyone else? So let me do this. Let me go under, say, let me get rid of this first. And you'll notice this neat trick. As soon as you start dragging on a block, if it gets close to it, it kind of goes gray, and it can be magnetically snapped together. You don't have to do it very precisely. Conversely, if I want to get rid of a puzzle piece, I can just drag it anywhere on the left, let go, and that deletes it. Or you can right-click or control-click, and a little menu will let you delete it as well. Well, let me do this instead. Under sensing, which I know is there because I've done this before, are a whole bunch of things related to sensing, whereby the cat can kind of feel out its world in some sense. It can do things like ask this question. Am I touching the mouse pointer, like the user's cursor? Am I touching a specific color that you can override to be anything you want? Is the distance to the mouse pointer some specific value? But for now, I'm going to focus on this blue puzzle piece that asks a question, which itself is this white oval that I can apparently change, and then it's going to wait for a response. But this puzzle piece is a little different. It's a little special. It comes with a freebie. It comes with what we're going to call technically a return value. So some functions don't just do something on the screen. They hand you back, so to speak, a value that you can do anything that you want with. Nothing happens immediately unless you do something with that so-called return value. So let me go ahead and drag this thing over here. Ask what's your name. And I'll use the default question. That seems a reasonable place to start. I'm not going to override that default. And now let me go ahead and zoom out. Let me go back to looks. Let me go to say, and let me just form the English sentence I want. So let me zoom in here and type in hello, maybe comma, space. I could do David, but that's obviously not right because I'm asking for a name and then I'm like in advance hard coding my name. That's not what I want. I just want hello, comma. And now let me zoom out and grab one more say block. Let me maybe say here. OK, I don't want to say hello, hello. I don't want to just type in my own name because, again, then what's the point of asking the user for their name? But notice this. If I go back to the sensing block, this is where that oval that's blue called answer is useful. This will be the so-called return value of that function. So I'm just going to go ahead and do this and drag and drop. Even though it's not the right size, it is the right shape. And so Scratch will be smart about it and grow to fill that puzzle piece for you. Let me zoom out now. And now let me click the green flag. You'll see that Scratch is indeed prompting me with the speech bubble. What's your name? Notice the little text box below the cat is asking, what's your name? So I'm going to type in DAVID and hit enter. Or I can click the blue check, enter. OK, it's a little weird. I wanted him to say hello, not just my name. So let me stop. Let me start it again. All right, hello, what's your name? DAVID, enter. Huh, kind of rude. Why is there this bug? Like, I wanted to say hello, David, not just David. And yet twice it has failed to do so. Yeah, the computer is processing my directions, my actions really quickly. And so it actually is doing it. It's just you and I in the room are just way too slow to notice that it said, hello, David. It just seems to have just said David. So, all right, how can I fix this? Well, here's where you start to poke around and think about how you might solve this. Let me go back under looks. Maybe there's a smarter way to do this. Maybe I could do this. How about instead of just say hello, there's apparently another puzzle piece where I can time it. So I can maybe slow things down a little bit. So let me do this. Let me throw away all of this. Let me drag a say hello for 2 seconds. Let me drag another say hello for 2 seconds. Let me change the first one to indeed hello, comma. And then let me go back to sensing. Let me grab that same answer, because I threw it away a second ago, and I'll just change it. I don't even have to delete hello. I can just overwrite it like this. So now I think we'll kind of pump the brakes and see things more slowly. Let me stop. Let me start. DAVID, enter. Hello, David. OK, so it's better. Like, it seems to be working. I think your hypothesis was right. It just looks kind of stupid, right? Like the fact that it's saying hello, David, like we can do better. And like literally every piece of software on your phone or Mac or PC is better than that. It adds words together in the user interfaces you and I are familiar with. So let's go a little more fishing here. Let me throw away these. Let me go back to looks and just get the simpler say. I want this to say hello, comma, name, where name comes from that answer return value. So how can I do this? Well, let me go under operations, which we haven't been before. There's a lot of stuff in here. Some of it's mathematically related, adding, subtracting, and so forth. You can generate random numbers, which might be useful. And if I keep scrolling down, there's this join apple and banana. But that's just placeholder text. You can join one piece of text with another piece of text. By default, apple and banana, but let's change it to hello and my name. So this too, wrong size but right shape. So let me let it snap into place. Let me go ahead now and do hello, comma. And now I think I just want to go grab that answer return value. Let me drag the same oval as before, clobber, that is overwrite banana. So now I'm kind of composing functions. The output of one function, join, is going to be the input of another function, say. So let's see what happens now that they're kind of stacked on top of each other or nested, so to speak. Click the green arrow, a green flag, DAVID, enter. Hello, David. All right, that was pretty fast. Let's just do it once more. Stop, start. Here we go, DAVID, enter. OK. Right, it's not the most exciting program in the world, but it's more correct. It's better designed just because that's what you would kind of expect the software to do and not be some kind of lame user interface that's just inserting random delays to just make it kind of work. Like that's a workaround, a hack, if you will. But there's some cool things you can do with Scratch. And we won't really go down the rabbit hole of all of the fun and family-friendly features that it has. But there is one that's kind of cool here. Let me go into the extensions button at the bottom left of my screen. And this one's kind of cool. Let me go to text to speech. And you'll notice that this one requires internet because it's cloud-based. But this just gave me some new puzzle pieces in a new category, text-to-speech. And these green ones do exactly what they say. So let me do this. Let me zoom out again. Let me keep the join block. And I'm just going to temporarily toss it over here. It's not going to delete itself because I didn't drag it over to the other side. But I'm going to get rid of the say block in purple. I'm going to do the speak block here in green and let it snap into place. And then I'm going to drag and drop this onto the input to speak. And now, perhaps a little more adorably, let's try this. Green flag. What's your name? DAVID. Enter. And?
Hello, David.
OK. It's a little robotic, but at least now it has synthesized speech. And I've kind of got my own like Siri or Google Assistant or Alexa thing going on here now, where it's now recognized whatever text it is and it's played it. Well, let's make this an actual cat that doesn't talk in that weird human voice. Let me go ahead and get rid of most of this stuff. And let's get the cat to actually meow like a cat tends to. And let me go under the sounds block. Now, MIT gives you a few sounds for free because it's designed around a cat by default. And I'm going to go ahead and grab this one. Play sound meow until done. And now, and we heard a teaser for this earlier in the crowd. It's a little piercing, admittedly. We can lower the volume a little bit there. But notice if I want the cat to meow a second time, I'll just click it again. OK, and over there too, I hear. OK. All right, so it's kind of cute now, right? So it's just meow. OK, yes, echo, echo. So it's meowing now every time I hit the green flag. Now, that's great, but even a kid is probably going to would prefer that it just meow, perhaps, like again and again without having to keep hitting the button. So well, how might we do this? All right, well, if I want it to meow multiple times, why don't I just grab it another time and another time? Alternatively, you can right-click or control-click a puzzle piece and just duplicate it from a little menu that drops down. So here we go, 3 meows. All right, that's not really a happy cat, it sounds. Maybe hungry. So can we slow that down? Well, maybe. In fact, if I poke around, let me go under Control. Looks like there's a wait block. Wait 1 second by default. And notice, Scratch will be pretty accommodating. If you just hover in between blocks, it will grow to fill that too. So I could change it to 1 or 2 or anything seconds. I'll just leave it at the default for now, 1. And now I'll go ahead and do this. OK, so cuter and less hungry and just more friendly. But this isn't the best design. It is correct. And let's use that as a term of art. Correct means the code does what you want it to do. I want the cat to meow 3 times, slowly, and it did. So I'd wager this is correct. But it's not the best design. And this is where things get more subjective, right? Like you could write accurate sentences in an essay for an English class, but otherwise it's just completely a mess. Like your arguments here and there, and you don't say anything wrong, but you don't say it well. In the context of code, we can do better than this. And copy paste or repeating yourself again and again tends to be bad practice. Why? Suppose that you want to change the wait to 2 seconds instead of 1. It's admittedly not a big deal. Fine, I click there, I change it to 2. I click there, I change it to 2. But what if you meow 5 times, 10 times? Now I have to change the wait like in 5, 10 different places? Like that's just stupid. It's taking unnecessary human time. And you're going to screw up eventually. Especially if your program's getting longer, you're going to miss one of the inputs. You're going to leave the number wrong, and that's a bug. So just based on what you've seen already, or if you've programmed before, which a few of you have, what's the term of art here that will solve this? How could we design this better? I heard it here. Yeah, so a loop, some kind of cycle that says do that again, do that again. Not infinitely many times necessarily, but some finite number. Well, you can perhaps see a spoiler on the screen. Under the same orange control category is a repeat block. And by default, it's proposing 10, but we can change that. So let me do this. I'm going to throw away most of this copy-paste as redundant. I'm going to detach this temporarily just to make room for something else. And I'm going to drag a repeat block over here and let that snap into place. And I'm going to change it for now just to be 3 for consistency. And this is the correct shape, even though it's too small, but Scratch will accommodate that for us. And now, same output, but arguably better designed. Why? Because if I want to change the number of meows, I change it in one place. No copy-paste messiness. If I want to change the weighting, one place. I don't have to change it in multiple places and not screw up. So let me hit the green flag. All right, so nice. Now, it would have been nice if MIT had just given us a meow block that just automates all of this for us. Let me wager they gave us the low-level implementation details. They gave us the play sound meow. But I had to implement like a decent number of blocks just to get a cat to meow again and again. I feel like we should have gotten that for free from MIT. Well, they don't have to be the only ones that invent blocks for us to use. You can write your own functions, your own verbs or actions. So how can we do this? Let's make our own puzzle piece called meow that uses this code but creates it in such a way that it's reusable elsewhere. So let me do this. Under my blocks in pink here, I'm going to go ahead and click literally make a block. Now, here's an interface via which I can give the block a name. MEOW will be the name of this block. And I'm just going to go ahead and quickly click OK. That just gives me a very generic pink puzzle piece that starts with the word define, because Scratch is asking me to define, that is, implement or create this new puzzle piece for me. Well, what does it mean to meow? I'm going to claim that it means to do these 2 steps, to play the sound meow and then just wait for 1 second. But what's powerful about this idea is look at this up top. Now that I've made a block, it exists in Scratch. MIT didn't need to create this for me. I created it for myself. And even you, if we end up sharing code. So I can now drag meow up in here. And what's nice about meow is that itself is, yes, a function, but it's also an abstraction. Like, never again do I, or even you, need to worry or care about what it means to meow or implement it. I can sort of drag it out of the way. I didn't delete it. Drag it out of the way, out of sight, out of mind. Why? Because my code is now even better designed in some sense because it's more readable. What is it doing? When the green flag is clicked, repeat 3 times, meow. It just says what it means. And so it's a lot easier to read it, and it's a lot easier to think about it, especially if you're using meow in other projects too. Now, let me go ahead and hit click play. Same thing. So it's not really fundamentally any different. But I can make this custom puzzle piece, this own function of mine, meow, even more powerful. Let me kind of rewind a bit and go to my meow puzzle piece. And I am going to control click or right click on my pink puzzle piece. And I'm going to edit it. So I kind of regret making meow so simple. Wouldn't it be nice if meow took an input, aka an argument, that tells meow how many times to meow? Then I can get rid of that loop and just tell meow how many meows I actually want. So I'm going to click on another button here called literally add an input. And it's going to have placeholder here. So I'm just going to put a placeholder there. I keep using n for number, which is a go-to in computer scientist terms. And I'm going to add some descriptive text just so that it's a little more self-explanatory. I'm just going to say meow n times. But there's only one oval. Times is just going to be explanatory text. And now notice what has happened. Now my puzzle piece takes an input, aka an argument, that will tell that function to meow some number of times. But it's not just going to work magically. I need to implement that lower level detail. So let me zoom out. I have to remind myself what this function was. So I'm going to drag it higher up just so they're on the screen at the same time. I'm going to go ahead now and temporarily move this over here. I'm going to temporarily detach this over here. Why? Because what I think I want to do is move my loop into the function itself, move the play and the wait into the loop, but I don't want to hard code 3. Notice that n here is its own oval. I can drag a copy of n and just let it go there. So now I have a new version of meow that takes an argument, n, that tells meow how many times to meow. And now, let me again drag this out of sight, out of mind, because who cares how I implemented it? Once it's implemented, it's sort of done. Now my program is even better designed in some sense. Why? Because now it really just says what it means. There's no loop, there's no repeat, no like implementation details. When green flag clicked, meow 3 times. And so functions indeed let you implement algorithms, like they're just code that do something for you, but they're also themselves abstractions. Why? Because once a function exists, it has a name, and you can think about it in that term, and you can use it by its name. You don't have to care or remember how the function itself was built, whether it's by you or even MIT. So again, here, I'll click the green flag. It's the same thing. So still correct, but better and better designed. And so anytime here and out with Scratch or soon C and eventually Python, when you find yourself doing anything resembling copy-paste or again and again grabbing the same code, probably an opportunity to say, wait a minute, let me refactor this, so to speak. That is, rip out the code that seems to be repeated again and again and put it in its own function so you can give it a descriptive name and use and reuse it. Any questions just yet on now saying or these loops or these functions that we're using? Yeah. How did I make it so it meows 3 times? So I originally only had a puzzle piece called meow, and I decided to improve it. So I held down Control, and I right-clicked or Control-clicked on the pink puzzle piece at top left, and I clicked Edit. And that brought back the original interface that lets me add some arguments to the puzzle piece itself. And I clicked Add an Input on the left here, and then I clicked on Add a Label over here. So that just lets you customize it even further. All right, so we've done this. Let's add one of those other primitives too, to do something optionally. So how about we make the cat meow only if it's being petted by a human, as by moving the mouse to hover over the cat like a human would pet a cat. Well, let me go ahead and throw away the meowing for now. And let me simplify it by just using a sound. I'm going to go ahead and do this. I'm going to go ahead and have a control block that says if, because I want to implement the idea of if the cursor is touching the cat, then play sound meow. Or I could use my same pink puzzle piece, but I'm going to throw that away and focus only now on the sounds. And I'm going to do this. If touching mouse pointer, so I need to sense something about the world. And we saw this earlier. So if touching mouse pointer. So notice this shape here, way too big, but it is the right shape. So if I hover just right, it'll snap into place. And this now in blue is my Boolean expression, a yes/no question, true, false. If is a conditional. And what do I want to do? Well, if the cat is touching the mouse pointer, I want to go ahead and play sound meow until done. So let's do this. I'm going to hit green flag, click. Now, nothing's happened yet because it's a conditional, right? It's only supposed to do something if I'm touching the cat. Let me move the cursor over to the cat and wait for it. Another bug. Why is the cat not meowing? Even though I very explicitly said, if touching mouse pointer, meow. Yeah, in the middle. Yeah, this is, again, my computer's just so darn fast. Like yours, I click the green flag. It asks the question, am I touching the mouse pointer? Well, no, because my cursor was up there, not touching the cat. It's too late. The cat's out of the bag. And so we have to instead solve this by some other means. How can we fix this? How do we fix that sort of race? Yeah, so why don't we just keep asking the question until I eventually am or am not actually petting the cat? So let me detach this temporarily. Let me go under control. Let me go under, instead of repeat some finite number of times, let's just do it forever. So sometimes loops that do work forever are a good thing. Like the clock on your phone, that's in a loop forever because you want it to always tell time and not stop at the end of the day. So sometimes you do want code to loop forever, as in this case. So let me go ahead and drag and drop it there. Let me again click the green flag. Nothing's happening yet, but notice the program's still running. And so if I move my cursor, and oh, OK, so maybe we could add some waiting, but the cat does not want to be pet in this case. But it's indeed conditional. So there we have an incarnation in Scratch of doing something conditionally. Now, we can make this really cool, really fast, if you will. Let me stop this version. Let me go ahead and do this. Let me go ahead and throw all of this away. Let me go into my little extensions bucket over here. And let me do video sensing, since most laptops or phones these days have cameras. And there, indeed, I am with Sanders behind me. And let me do this. When video motion, and let me get out of the way. When video motion is greater than some value, so 10 is the default. This is just a number that measures how much motion there is or isn't. So small number is like no motion. Big number is lots of motion. So I'm going to choose 50 somewhat arbitrarily here. So 50. This is not normal to program off to the side. But I'm now going to say this. When video motion is 50, go ahead and play sound meow like this. So the cat is still in that world. I'm going to stop the program and rerun it. So here we go, green flag. And now, all right, this is a little creepy the way I'm petting the cat, but, OK. There we go. OK, so 50 was too big of a number. I have to pet the cat faster. Whereas this, I don't know. Yeah, so OK. So you can make things even more interactive in this way by just assembling different puzzle pieces. And honestly, there are so many different puzzle pieces in here. We're not going to even scratch the surface of a lot of them. But they generally just do what they say. And indeed, when you see on the screen here, this palette of puzzle pieces, really a lot of programming, especially early on when learning a language, is just trying different things and try and fail. And if it doesn't work quite right, look for an alternative solution there too, as even I just had to do a moment ago. Well, let's go ahead and use actually, how about another example of something a predecessor of yours made? Let me go ahead and grab a program I opened in advance here called Whack-A-Mole. Might we get a brave volunteer to come up who is willing to whack-a-mole with their head virtually? Maybe. OK, let's see. How about in way back? You want to come on down? All right, come on down. And in just a moment, sure, round of applause for our volunteer. All right. So here we have, come on down. Okay. What's your name? Oh, actually, say it into the microphone.
Hi, I'm Josh.
OK, nice. Welcome, Josh. Come on over. All right. So same idea here. I'll take the mic back. You'll have to stand in front of the camera. In just a moment, you're going to have to position your head in a box that your classmate from yesteryear created. And we'll start with beginner.
Okay.
So line your head up in the box in a moment. Nice. 12 seconds. Five seconds. Notice the score is up to 18 already. Pretty good. All right, a round of applause for Josh if we could. So notice how using some fairly simple primitives, things do get interesting pretty fast. And how was that implemented? Well, there were probably at least 4 sprites. So you're not confined to just one cat. You can create more and more sprites, change what they look like so they actually look like a mole in this case. There's probably some conditionals in there, some loops for 30 seconds. That's checking if Josh's head's movement is exceeding some value over this way or over this way, then increment something called a variable. We'll see those too. Just like in algebra, you might have x and y and z storing values like numbers. So can computer programs have variables called x or y or z, or more descriptively called score, as in this case at top right, or another variable called countdown, typically 1 word in code, but in this case 2 words, that just store some value. So there's probably some math going on in there, whereby the author of this program just is incrementing, that is adding 1 and 1 every time it detected that a mole had been whacked, in this case with movement. So back in the day, I myself actually implemented my very first program in Scratch when I was a graduate student, actually, at MIT, cross-registered at MIT, taking a class from MIT's Media Lab, specifically the Lifelong Kindergarten group, which is the group that created Scratch itself. And the program I wrote all those years ago, and still rather cling to, is a little something here called Oscar Time that I thought I'd play just a quick excerpt of myself here. So in this case, consider as the music starts playing, how this program, which is much more sophisticated certainly than the earliest say hello examples we just did, might also be implemented. Let me go ahead now and click the green flag.
So some trash is moving, presumably in some kind of loop from the top. If I'm touching the mouse cursor, it follows me. If I hover over the trash can, it responds. If I let go, in some kind of loop, Oscar pops out, creates a variable with the current score, and it happens again. Pretty easy at first, but I don't need to keep playing this up on stage in front of everyone. So my score is already now up to some 6 or so. But in a moment, too, you'll see that it's going to escalate. So I'm taking into account some time, apparently. So now, more and more sprites are suddenly appearing. And notice that each time they're appearing from a different part of the screen. That's an illusion, perhaps, to that. Pick a random number between x and y. So you can actually pick some range of values to have the game constantly changing. And indeed, I'm going to go ahead and click stop, since I spent like
8 hours plus years ago making this, and I can never listen to the song again. Not that I should be anyway at this point in my life, but this song is synchronized then with a lot of the actions that's happening, and ultimately there's just a lot of building blocks. But I didn't sit down and implement Oscar Time, as I called it, all at once. I really did take baby steps, so to speak, and I figured out, well, how could I decompose this vision I had at the time to create this game ultimately, and how do I bite off maybe the easiest parts first? And honestly, the first thing I did was I found this image, and I just like dragged and dropped it into Scratch. So, okay, done. Like lamppost is installed. It doesn't do anything. It's not interactive, but I at least set the stage, so to speak, for the program. Then what else might I have done? Well, let me do this. Let me go ahead and open up in another editor here a early incarnation of Oscar Time by doing this. Let me go into Oscar Time here. Let me full screen this. And here you have, let me hide the trash for just a moment, is what I might call the second version of my program, wherein at the top right of the stage here, I had the lamppost, which I just dragged and dropped and got going, but then I added an actual sprite. And it has to be a sprite if you wanted to do things interactively. The lamppost, not a sprite. It's just an image, a costume, if you will, for the whole stage itself, a backdrop. But this thing is indeed a sprite because it needs to respond to code and events like dragging and dropping. So what might I have done early on with that code? Well, maybe the first version would have been something like this, whereby my very first version of Oscar time might have said something like, oh, this. How about let me control the program as before, or rather events. When the green flag is clicked, what do I want to do? Well, I want to go ahead and forever do something like this, forever. So I want the lid to open up if I touch it. So if the cursor gets near the lid, I want the lid to open up. And then if I move away, I want it to close. So how can I do that? I want an if, but I just don't want one question. I really want two, a fork in the road that goes left or right, so to speak. And let me grab this puzzle piece here as I did long ago. So notice it grows to fill. What's the question I want to ask? Well, under sensing, I'm going to go ahead here and say if this trash can is touching the mouse pointer, what do I want to do? Well, I want to change what the trash can looks like. And this part I did in advance of class. If you go up here to costumes, this is where all the graphical stuff happens. And you'll see that I imported a whole bunch of different costumes that effectively, much like a video, when you play them quickly, creates the illusion of movement, some animation. But it's really just dot, 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 different images showing on the screen. Well, some of these costumes are called like Oscar 1, Oscar 2. Oscar 1 is closed. Oscar 2 is open. So let's just deal with those first. So if I'm touching the mouse pointer, let me go under, how about looks? And we didn't use this before, but there's this block. Switch costume to something else. I'm going to drag and drop this inside of the if, and notice it's a little bit indented. I'm going to change it not to Oscar 8, but Oscar 2. Otherwise, if not touching the mouse pointer, this is the other direction in the fork in the road, let's go ahead and switch the costume back to what I described as Oscar 1. So let me run this program, and not much of interest is happening yet, but notice if I move the cursor up, down. But how is that working? It's just changing the costume that's being overlaid on the sprite. So it looks like interactivity, but you're really just changing the aesthetics. And we humans are just kind of, assuming, oh, it's opening up. Well, no, it's just changing a costume. So here's the difference. The high-level abstraction, trash can opening, the lower-level implementation detail, costume changing, creating that illusion. And if I wanted to look prettier, I could just have many other costumes and go boom, 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 boom to create more frames per second, if you will. So I need to do one other thing. Maybe if I accidentally leave the trash can open, let me make one change here. Let me make sure that the very first thing I do when the green flag is clicked is always start with the trash can closed, because otherwise you might accidentally leave it open. So this gets me into some default state. So now it's always closed until I manually hover over it instead. Well, what might I have done next? Well, if I wanted to introduce something like the trash, I need a second sprite. And here in advance, I grabbed the image already. Let me pretend that this never happened. Let me drag this away here. And now I have nothing in my code area for this piece of trash. But it is a second sprite. And all I did was I clicked on the little cat plus icon here, created a second sprite. I named it trash. I added a costume for it, sort of the aesthetic stuff I did in advance. But here I'll do now the code. How do I want to do this? Well, how about when the green flag is clicked, for the trash can, I want the trash can in parallel to do, or I want the trash, the piece of trash, to do its own thing. So what I want it to do is maybe, let's do motion, how about? And let's go to a specific coordinate. Now, there's a lot of options here. There's turning, go to a random position, go to x, comma, y, glide more elegantly. There's a lot of different ways to implement movement. I just want it to go to a very specific location first. So I'm just going to go to x, comma, y first. And I'm going to say x, how about will be, let's not hard code this. Let's just have it be, well, let's do it at 0 initially, and then 240. So whoops, let's do 0, comma 240 so that this piece of trash always starts at the top middle of the screen if you think back to that coordinate system. 0, 0 is in the middle, 240 is straight above it. All right, now after I do that, what do I want to do? Well, how about I control this thing by forever falling? Now, how do I make the trash move? We haven't seen this puzzle piece yet, but under motion, the very first thing is called move some number of steps. By default, it's 10, but we'll do it more simply. Let me go ahead and move. Move is going to move it in whatever direction it's facing. I only want it to move down. So here, even I'm getting confused as to how many different ways there are to do things. What I think I want to do is this. Let me only change my y-axis as follows. So here's another puzzle piece called change y. So again, y is the vertical. So let me just change y by 1 pixel downward at a time. So -1, 1 pixel at a time. So it's kind of slow. And I think that's it. Let me hit stop. Notice that my trash can is still going to be interactive. I haven't changed or deleted that code. I've just added now code for my trash piece of trash. If I click the green flag, notice that after I enable it, let me start that again. I had it hidden before class, but let me enable it now. Green flag, notice it starts dead center at x equals 0, y equals 240, and it's dropping 1 pixel at a time. If that seems a little boring, we can change it to negative 10 pixels at a time, and boom, it's done. So that's how you might change the speed of a program. But I'm going to leave it more simply as -1. And honestly, it would be nice if it doesn't always start from the top. Otherwise, this game is not going to be very interactive. I'm literally going to be grabbing the trash from the same place every time. So why don't I instead stop this? Let me go under operators, and let's pick a random number. So let me change the hard-coded, the manually inputted 0, and let's make x be somewhere between 0, so in the middle, and all the way over to, what was it, I got my numbers wrong, 240, and my y will be 180. Sorry, I got my x and my y confused. So let me play this again. And now we have a game that's more like games you might have played growing up, or even now, like there's some randomness to it. So the CPU, so to speak, is doing something more interesting. Let me run it again. Now it's a little to the left. Let me run it again. Now it's a little more to the left. Again, now it's back to the right. So randomness just makes games more interesting. And this is why when you play any video game, if different things are happening, there's probably just some randomness. And it's quantized as just a simple number. Now I think I just need one final flourish here, if I may. Let me go ahead and add this. How about events, or rather, yes, events. When green flag is clicked, I can do multiple things within the same sprite. They don't all have to be attached to the same one. Let me go ahead and forever go ahead and do something else. How about whenever the trash is, how about touching the trash can? So forever, if, let's see, I need a sensing block. So how about is touching, not the mouse pointer this time, but touching Oscar himself there. Now let's see what happens. All right, so let's go ahead and click the green flag. Now I go down over here and let go. OK, I kind of want it to go into the trash can. How do I make it go into the trash can? How can we take this high-level idea, put trash into the trash can, and make it seem to disappear? Logically, what could we do? Yeah. OK, so when it touches it, let's have it disappear. So I could hide it. Or honestly, if the game's going to be ongoing like it was, letting me drop more and more trash, let me just have it go ahead and pick a new random location. So let me do this. Let me go ahead and copy this puzzle piece up here and duplicate. And I don't want the whole thing. Sorry. Let me get rid of this. Let me just do this. Let me go back to some random location at the top. So now notice what happens. If I click and drag on it, here it goes, and I let go, it looks like it's going into the trash can because it snaps back up to some random location. Now, the only thing I'm not doing really is keeping track of any kind of score. And it turns out, if I full screen this, it's not going to be draggable by default. So just as a corner case, so to speak, something that you might trip over otherwise, let me go ahead and under, let's see, sensing, it turns out I also need this for the piece of trash. There's this way of setting in Scratch a sprite to be draggable or not draggable. I need to explicitly make it draggable so that when I do full screen this thing now, it still remains draggable. And someone like myself can play it again and again. Well, how about we supplement this with one final flourish? Why don't we keep track now of the user's score? So how about when the user actually drags the piece of trash to the trash can. Let me go under variables here, where in advance I've already made myself a variable called score. I could have called it x or y or z or abc, but that's not very descriptive. In programming, you typically give things a more descriptive English or some other language name. So I called this one score. So how do I want to do this in my score? Well, let me go ahead and initially set this game's score to 0 at the very top of one of these scripts, or one of these programs up here. And then any time my cursor, my piece of trash is touching Oscar, let's not just jump to the top. Let's change the score by 1 up here. So now notice, if touching Oscar, change the score, that is, add 1 to the score, and then pick a new random location. And now, green flag, let's do this slowly. Here it goes. It's the trash can opens. I let go. And now notice at the top left of my program, notice the score is now 2. Notice the score, if I do this again, is about to become 3. And so here we have building blocks, literally, of making this program better and better and better. And so indeed, that's how you generally approach solving any large program, any problem with code, be it in Scratch or C or Python or some other. You take this vision you might have, or some vision you've been assigned in a homework assignment, and try to break it down into these constituent parts. And just pluck off the easy ones first. Put the lamppost there first and at least feel like you're making some progress. Then pluck off something like the trash can and just make it do a little thing. And it doesn't have to be in some same order here. I could have done this in a million different ways, but figure out what the small pieces are that ultimately, like a few of the problems we've solved today, assemble into a greater solution there too. So that you have now a mental model for these types of blocks and others, let's return for a moment to this. We saw a moment ago that when I started saying, hello, David, and nesting those puzzle pieces, we had a whole different paradigm altogether. My input for that second version of hello world was to now pass in, for instance, what's your name, into my function called ask. That gave me not a side effect, but what I called, again, a return value called answer by default in Scratch. And now notice and recall, when I had that same output become the input to my next block, it looked a little something like this, say. So how does this type of block and this nesting, this stacking of blocks fit into the same mental model? Well, same idea. My input for that part of the story is now taking in not one input, but two arguments, hello and the answer from before. The function in this case is that new block called join. The output thereof is hello, David, which itself became, if we sort of animate this, the input to my final function, which indeed was still say. And this is only to say, no pun intended, that almost everything that you do with these puzzle pieces, be it in the context of Oscar time or the mole whacking or even just something simple like hello world, will ultimately fit into that relatively simple mental model there. Now, I thought we'd end by taking a look at just a couple final examples, these ones too made by some of your predecessors. And for this, I thought we would not write code together, but read it instead. And so allow me to open up one other example here that will show us a few different versions of a program that a predecessor made. Give me just a moment here, and we'll see how we might build up to something even more interactive. And in just a moment, we'll see something they called Ivy's hardest game, focused here on these particular mechanics. So here is version 0, so to speak, of this program, wherein the goal was to create a game where you have to get out of some kind of maze. And you have to get out, in this case, the Harvard crest from this maze. Let me go ahead and just hit play on this green flag so you can see what the first building block for this program might have been. Notice that my hand here is actually on the arrow keys of my keyboard. And it seems that by moving up, down, left, or right, this little crest on the screen responds in exactly that way. Now let's hypothesize for just a moment, even though we've not done anything quite like this before, how might this code be implemented? How do you get a sprite, be it a cat or a crest, to respond to keys on a keyboard? Might you think intuitively? Yeah. Yeah, there could be something sensing what key you're pressing on. And if you do it again in a forever loop, you'll just constantly be listening for keystrokes. And this is how every piece of software nowadays works. It's constantly waiting for your phone to be tapped or something to be typed on the screen. So let me go ahead and look inside of this existing program here. And there's more going on, but we'll take a quick glance. What's actually going on? Well, up here at top left, notice we just have go to x equals 0 and y equals 0. That means put the Harvard crest dead center in the middle of the stage. Then we have forever two functions that we made in advance as custom functions. Listen for keyboard, feel for walls. So it's doing two things at once. It's forever listening for the keyboard, up, down, left, right, and feeling for the walls in the sense that if I get too far to the left, I don't want it to keep moving past that black wall. And if it moves too far to the right, I don't want it to blow through that wall either. So it's going to do two things constantly, listening for keyboard and feeling for walls, so to speak. And how are those implemented? Well, this one's a bit long, but on the left here is listen for keyboard. So this pink puzzle piece, listen for keyboard, first checks if the key up arrow is pressed, question mark, Boolean expression in a conditional, change y by 1. That means move it up 1. Else, if the key down arrow is pressed, then change y by -1. And similar for left arrow, similar for right arrow. And even though there's not a loop in this pink function, there is where I'm using it. So it's constantly being asked again and again. How about feeling for walls? Well, over here to the right, it's a little cut off, but here you have if touching left wall, change x by 1. So if you hit the wall, it's too late. You're kind of blowing through it already. So I want to move it whack 1 pixel so it's no longer touching that wall. Similarly, if it's touching the right wall, I want to back it up 1 pixel so it's no longer touching that wall. So it's kind of like bouncing off ever so slightly so that it doesn't slip through that actual wall. And what are those walls? Well, notice down here, it's just a simple sprite with a black line that I've oriented vertically instead of horizontally. And that's just so that I can ask questions of these other 2 sprites. Now, that gives me that form of interactivity. What more can I now do? Well, what if we make things a little more interactive here? Let me go ahead and see inside version 1, our second, and let me propose what's going to happen here. Well, how might we add a little something like Yale into the mix? Well, what's Yale going to do when I hit the green flag now, based on this code? Any hunches? Here is the code for my Yale sprite. Yeah, it's kind of going to be an adversary by blocking my path, theoretically, if I keep writing more code. So why? It, too, goes to the middle of the screen. It points in direction 90 degrees. So similarly, there's a whole degree system as well. And it forever asks this. If touching the left wall or, notice the green block, touching the right wall, then just turn around 180 degrees. And indeed, if you think this through logically, that just means you're bouncing this way and this way by just flipping yourself around 180 degrees for just this Yale sprite. So if I go ahead and zoom in on this and click the green flag, I can still move up and down. But Yale is just kind of doing this all day long, back and forth forever. Nothing bad happens if I try to go through it, but we could add that, certainly, to the mix. In fact, let's add one final feature before we play this particular game. And let me go ahead and open up the final version of these building blocks that adds MIT to the mix. So here's MIT. Someone want to explain what this code does? And this is what we're doing. This itself is a skill. Reading someone else's code and understanding it is half of the part of programming besides writing. Yeah. Yeah, it's chasing down the Harvard logo outline. So this is apparently the name of the costume that this student made, Harvard logo outline. And apparently it goes to a random position first, but then it forever points to Harvard. So no matter where I'm moving it, up, down, left, or right, MIT is being a little more strategic than Yale, bouncing back and forth like this. So let's go ahead and play this one in full screen. And here we have a green flag. So if I move up, MIT, rather strategically, is following me no matter where I go. All right, so still nothing bad happens, but and now it's struggling, right? It's going up, down, up, down. It's trying to follow me even though I'm not moving. So we need some final flourishes. And so I think for this, we need perhaps one final volunteer. After this, cake awaits for everyone outside, as is an end of first lecture CS50 tradition. Would you like to come up and be our volunteer? All right, and so this will be the actual version written by one of your predecessors that I'll full screen here. It's going to stitch together all of these same primitives and more, but add the notion of scores and lives so that there's actually a goal, which in this case is to move the Harvard crest to constantly pursue the character on the right-hand side so that your sprite touches that one. Would you like to introduce yourself?
Hi, my name is Mohammed.
All right, wonderful. Welcome aboard. And here we come with some instructions and final flourish if we want to keep the lights up but perhaps increase the music. All right, this is CS50, and this is week 1, wherein we continue programming, but we do it in a different language, because recall last time we focused on this graphical language called Scratch, but we use Scratch not only because it's sort of fun and accessible, but because it allows us to explore a lot of these concepts here, namely functions and conditionals, Boolean expressions, loops, variables, and more. And so indeed, even if today's syntax, as we transition to this new language called C, feels a little bit cryptic, maybe a little intimidating at first, and you don't quite see all of the meaning of the symbols beyond the syntax itself, realize that the ideas are ultimately going to be the same. In fact, as we transition from what was last week, a hello world program that looked a little something like this week, of course, it's going to now look a little more cryptic. It's going to look a little something like this. And now even if you can't quite distinguish what all of the various symbols mean in this code, turns out that at the end of the day, it's indeed going to do what you expect. It's just going to say hello world on the screen, just like we did in Scratch. So let's start to apply some terminology to these tokens first. So what we're about to see, what we're about to write henceforth, we're going to start calling source code. Code that you, the human programmer, write is just henceforth called source code. Doesn't matter if it's Scratch, doesn't matter if it's C, doesn't matter if it's Python before long. Source code is the general term for really what you and I as human programmers will ultimately write. Of course, computers don't understand source code, it turns out. Computers don't understand Scratch and puzzle pieces per se, or C code like we're about to see. They only understand this, which we called what last week? Yeah, so this is binary, zeros and ones, but really it's just information represented in binary. And in fact, the technical term now for patterns of zeros and ones that a computer not only understands how to interpret as letters or numbers or colors or images or more, but knows how to execute as well, henceforth is going to be called machine code, to contrast it with source code. So whereas you and I, the humans, write source code, it's the computer that ultimately only understands machine code. And even though we won't get into the details of exactly what pattern of symbols means what, you'll see that in this kind of pattern of zeros and ones, there's going to be numbers, there's going to be letters, but there's also going to be instructions. Because indeed, computers are really good at doing things, addition, subtraction, moving things in and out of memory. And suffice it to say that the Macs, the PCs, the other computers of the world have just decided as a society what certain patterns of zeros and ones mean when it comes to operations as well. So not just data, but instructions. But those patterns are not something we're going to focus on in a class like this. We're going to focus on the higher level software side of things, simply assuming that we need to somehow output machine code. So it turns out then that this problem we have to solve, getting from source code to machine code, actually fits into the same paradigm as last time. But the input in this case is going to be source code on the one hand, like that's what you and I ideally will write so that we don't have to write zeros and ones. But we need to somehow output machine code, because that's what your Macs, PCs, phones are actually going to understand. Well, it turns out there are special programs in life whose purpose is to do exactly this conversion, convert the source code you and I write to the machine code that our phones and computers understand. And that type of program is going to be called a compiler. So indeed, today, we'll introduce you to another piece of software, and these come in many forms. We'll use a popular one here that allows you to convert source code in C to machine code in zeros and ones. Now, you didn't have to do this with Scratch. In the world of Scratch, it was as simple as clicking the green flag, because essentially MIT did all of the heavy lifting there, figuring out how to convert these graphical puzzle pieces to the underlying machine code. But now, starting today, as we begin to study programming and computer science proper, now that power moves to you. And it's up to you now to do that kind of conversion. But thankfully, the fact that these compilers exist means that you and I don't have to program in machine code like our ancestors once upon a time did, be it virtually or with physical punch cards, like pieces of paper with holes in them. You and I get to focus on our keyboard as such. But it's not just going to be a matter today of like writing code. It's going to be a matter ultimately today onward of writing good code as well. And this is the kind of thing that you don't just learn overnight. It takes time. It takes practice. Just like writing an essay in any subject might take time and practice and iteration over time. But in a programming class like CS50, we're going to aspire to evaluate the quality of code along these three axes generally. Is it correct first and foremost? Like, does the code do what it's supposed to do? After all, if it doesn't, well, what was the point of writing it in the first place? So it sort of goes without saying that you want code you write to be correct. And it's obviously not always. Again, anytime your Mac or PC or phone has crashed, some human somewhere wrote buggy, that is code with mistakes. But code correctness is going to be the first and foremost goal. But then there's a more subjective goal we'll see in time, a matter of design. And we saw a little bit of this last week when I proposed that we could design even Scratch programs better, maybe by using loops instead of just by copying and pasting the same blocks again and again. So design is more subjective. It's more of a learned art whereby two people might ultimately disagree as to which version of a program is better designed, but we'll give you building blocks and principles over the coming weeks so that you can have a better sense for yourself if your own code is well designed. And why is that valuable? Well, the better designed your code is, often the faster it's going to run, the more maintainable it's going to be by you or colleagues if you're working with others in the real world. So good design is a good thing. It helps you communicate your ideas, just like in a typical English essay. And then lastly, we'll talk this week onward about style. And this is really just the aesthetics of your code. It turns out that computers often don't care how sloppy your actual code is. In the world of code, it turns out that you don't really need to indent things in a beautiful way. You don't need to paginate things like you might in an essay. The computer generally does not care, but the human does. The teaching assistant does. You will care the next day when you're just trying to understand what your code does. So we'll focus lastly on style, the aesthetics of the code that you're writing. So where are we going to write code? Where are we going to compile code? So for this class, not only with C, but the other languages we use later in the term, we're going to use a free text editor that is program called Visual Studio Code, aka VS Code. It's super popular nowadays, not just for C, but for C++ and Python and Java and any number of other languages. It's a text editor in the sense that it lets you edit text, and that's all code is going to be. Now, strictly speaking, you could write code on paper pencil. In fact, in high school, if you took a class, you might have done that one or more times as sort of an in-class exercise. You can't run it on paper, of course, but you could write it certainly. You could use something like Microsoft Word or Notepad.exe or TextEdit on the Mac, but none of those programs are really designed to format the code in the best way for you, nor are they designed to let you compile and run the code. So VS Code is going to be a tool via which you can do all that and more. Write the code, compile the code, run the code. So that you all don't have to wrestle with stupid technical support headaches at the beginning of the course by installing this software and that on your Macs or PCs, we'll use a cloud-based version of VS Code at code.cs50.io, and that's going to be the exact same tool. And the goal then is by the end of the semester to sort of migrate you off of that cloud-based environment to your own Mac and PC so that even if CS50 is the only CS class you ever take, you're 100% equipped to continue writing code after the class using not something that's even CS50 specific, but a de facto industry standard, at least for some time. So what's this program VS Code going to look like, be it on your Mac PC or initially in your browser? It's going to look a little something like this. And there's going to be several different regions to the screen. And pictured here is that very same code I keep proposing is the simplest program you can write in C. And what are these different regions of the screen? Well, there's essentially these four here. So first, highlighted up top, is going to be one or more tabs where you're going to actually write code. So much like in Google Docs or Microsoft Word, you can have tabs open with files. Similarly, in VS Code, or really any programming environment, you generally nowadays have tabs of some sort. And this is going to be a tab containing a file, it seems, called hello.c. And that's going to be the very first file we write in just a moment. Down here, though, is going to be an interface that many of you might not know. This is what's called a terminal window. And a terminal window provides what's generally called a command line interface, or CLI. And this is in contrast with a graphical user interface, or GUI. Now, you and I every day are using GUIs on our phones, on our PCs. And a GUI is literally graphical. So menus and buttons and icons. And you generally use your finger or a trackpad or a mouse or something like that to interact with it. But it turns out that many programmers, dare say most programmers, at least over time, come to prefer not a GUI, but a CLI, a command line interface where you actually do everything somewhat arcanely via keyboard alone. Why? Well, it turns out there's just more features built into most computers if you can access them with a keyboard. Turns out most of us can type faster than you can point and click, and so that ends up being an efficiency gain over time. So in time, will you get comfortable using this terminal window to do things like compile your code or make your program, as well as run it. So you won't be in the habit initially of just double-clicking icons like we do in our typical real world. You'll do it sort of the programmer's way, but it's not to the exclusion of adding icons and clickability and more. On the left-hand side of VS Code, there's going to be a somewhat familiar file explorer, some kind of hierarchical tree like on your Mac or PC where you can see all of the files in your account. Pictured here, for instance, is just hello.c, which I'll create myself in a moment. And then far away on the left is the so-called activity bar. And this is where you just get a lot of traditional menus and buttons. So VS Code itself gives you both a GUI and a CLI, but it's within the CLI, the terminal window, the bottom region of the screen, that we're actually going to type most of our commands. And in general in class, I'm going to hide all of the graphical stuff that's just not of all that much interest. So with that said, let me actually change over to a live version of VS Code. And I've indeed hidden the activity bar. I've indeed hidden the file explorer. So what I have here, for visibility's sake, is a really big area for writing code and a really big terminal window at the bottom. You'll see in the terminal window, there's a $sign. And this doesn't mean any form of currency. This is just the standard symbol that represents type commands here. So the fact that there's just a $sign and a cursor means eventually that's where I'm going to type commands. But first, I'm going to actually create some code. So how might I program using VS Code, be it on my Mac PC or in this cloud-based environment that you'll get set up for problem set 1, go about writing my first file? Well, perhaps the easiest way is this. Literally run the command code, and then the name of the file you want to create. Notice that I deliberately end the file with .c in lowercase. Notice that I've deliberately lowercase the whole file name. And these are just conventions. You could use a capital H. You kind of could use a capital C. But just don't do that. Follow best practices so that it's consistent with what most everyone else would do. When I hit enter, I just get an empty tab, just like the screenshot a moment ago. And it's in this tab where I can now write my very first program in C. Unfortunately, it's not quite as user-friendly as Scratch, where you drag and drop a couple of puzzle pieces and boom, it's done. So I'm going to do this from memory, but this too will become familiar to you over time. I'm going to include something called standard.io.h. I'm going to type int main void in parentheses. On a new line, I'm going to insert some curly braces, as we'll call them. And then I'm going to type printf, and then some parentheses, and then in quotes, hello, comma, world, then a backslash, then a lowercase n, then a close quote, and then a semicolon at the very end of the line. So all I've done is recreate, just from memory, that very first program. In a little bit, we'll make clear what most of this does. But for now, let's just actually run this thing. And just like I clicked the green flag last week for the first time, let's actually compile and run this program. If it were your Mac or PC and Google or Microsoft or someone else had made the software, at this point in the story, we'd be double-clicking an icon. But we can't do that yet. This is still source code. So I'm going to click back down in my terminal window. Notice I have a second $sign below the first, which just means it's ready for a second command. And now the command via which to make this an actual program, to compile it from source code to machine code, is going to be quite simply make, and then the name of the program I want to make. Slight subtlety. I'm omitting deliberately .c because the program I want to make, I just want to call hello. So don't write make hello.c, just write make hello. And this program make is essentially our compiler. Technically speaking, it's a program that automates the compilation of my program for me. But it is going to see that I've typed the word hello. It's going to automatically look now for a file on the hard drive called hello.c and convert it from source code in C to machine code in zeros and ones. So if I didn't make any typos, enter. Nothing seems to happen, and that's a good thing. Almost always, if nothing gets outputted on the screen, like you did good. Like you didn't make any mistakes. You didn't get yelled at. There's no error messages. So this is actually a good thing. How do I now run this program? Well, notice I've got a third $sign, which just means I'm ready for a third command. And now I'm going to go ahead and run /hello. And this is admittedly a little weird that you have to do /, but for now, just take on faith that this is how you run a program called hello in your current folder, in your current directory in this cloud-based environment. All right, crossing my fingers again, hitting enter, and voila, my very first program in C, hello world. And now let me go ahead and reveal the file explorer that I proposed exist earlier. I'm just going to use the keyboard shortcut to reveal that. And generally, I keep it closed because I don't really need to know constantly what files are in my account. But you'll see now in the file explorer, similar in spirit to a Mac or PC, but graphically a little different. Here's my file, hello.c. It's highlighted because I have that tab open. But now there's a second file here called just hello. That's the name of my program. So if you were on a Mac or PC, you would ideally double-click that thing. You can't do that in a command line environment. You have to run it down here, but that's all we've done. We've created a file called hello.c, and then my compiler made the program from that. Let me pause here and see if there's any questions, because it's a lot of magical phrases. Yeah? Yeah, so if you're currently following along, playing along at home, and you're getting some kind of error message, part of today will be for me to deliberately induce some of those error messages. For now, let me just propose that if you literally did what I did, you must have made a typo somewhere. And notice that it's indeed standard IO, stdio.h. Maybe you type studio.h. Okay, super common mistake. If I could call you out, like it is not studio.h. It is standard.io.h. So common, but this is exactly representative of like the kind of stupid headaches you're going to run into this week, probably for a few weeks, probably honestly for a few years. But you start to see past these sort of stupid mistakes over time, and it just gets easier and easier because the computer is going to be so regimented. Like it will only do what you tell it to do. And if you say, because it verbally sounds like studio.h, it's not going to know what the file is. So actually, thank you for tripping over that so early. That's super common to happen. Yeah. So why do I have two hello files? So why do I have two hello files? One is the one I created as the human called hello.c, and it's pictured right here. But then when I ran make hello, that process compiled my source code into machine code. So this second file, just called hello, is the file that contains all of those zeros and ones that the server actually understands. All right, so yeah, question. If you try clicking on the hello file, you'll see in this environment of VS Code, quote unquote, the file is not displayed in the editor because it is either binary, aka zeros and ones, or uses an unsupported text encoding. In this case, it's binary. It's zeros and ones. Now, you could use software to see those zeros and ones. It won't be intellectually enlightening to most any human. So VS Code just takes the choice of not showing it to you at all. So that would be a common mistake, too, clicking on a file you don't intend. But the source code is indeed going to be editable by us. All right, so I've written this program. It seems to sort of magically work, at least with some effort. If you get every single keystroke right, well, what is it that's going on and how is this working? Well, first of all, notice that even without my highlighting things or choosing buttons from menus, notice that it's already kind of color coded. And yet I wasn't highlighting along the way and sort of Google Docs style changing the color, certainly. Well, it turns out what VS Code and most programming environments nowadays do for you automatically is syntax highlighting. So syntax highlighting is just this feature of typical text editors nowadays that analyzes the code that you've typed. And when it notices certain types of keystrokes, things that represent functions or conditionals or loops or variables, a lot of the vocab from last week, it just highlights it ever so differently for you. So main, for instance, which we'll soon see, is in purple here. Int and void and include are in red. Hello world is in blue. My parentheses are in green. This will totally vary by programmer too. In fact, if you do want to change these colors for problem set 1 for your own environment, you can poke around VS Code settings via the gear icon. You can change to a different color theme. Syntax highlighting isn't some specific color scheme like it is in Scratch. It just generally is to each human their own preference. But that's all that's happening here is this notion of syntax highlighting at the moment. Well, what more is going on in this code before I run it, but rather write it? Well, it looks a little something like this if I take away all of the colors. And then just for discussion's sake, let me go ahead and color it a little more like Scratch. Recall that our very first Scratch program that just said hello world on the screen had a when green flag clicked icon, puzzle piece, roughly in orange, and then a purple say block beneath it. So whereas this is the C version, if we rewind to last week, this was the same program in Scratch. But what's happening now is exactly the same. So if you think back to last week, and you've got some function, like the say function in purple, that might take one or more arguments, like inputs that influences what it says on the screen. And then functions, recall, can sometimes have side effects, right? Like the speech bubble appears on the screen. So last week, when we used the say block and we passed in an argument of hello world at left, we got this visual side effect on the screen that says now hello world in the speech bubble. And that's exactly what just happened in VS Code, but much, much more textually. And let's look a little closer now at the code itself. Let me wave my hand at the equivalent of the when green flag clicked part of my code. And let's focus only on the say block in Scratch and the corresponding function in C. So if I step through this and I wanted to convert what we did last week with a say block to C, I would first use the print function. Although that's actually a bit of a white lie. It's actually the printf function. Printf means formatted, and it's just a function that allows you to format text on the screen. There is no say function in C. There's a printf function. What MIT did down the road years ago was they took what existed historically as printf, and they simplified it for a broader audience by just calling it essentially say instead. But notice that now, if I want to convert the Scratch code at left to C code at right, it's sort of the same shape. So MIT deliberately used this white oval, if only because it kind of conjures this idea of having parentheses too. So on the right, if I want to pass an argument or an input to the printf function, I use an open parenthesis and a close parenthesis. In those parentheses, I then type whatever it is I want to print on the screen. In this case, hello, comma, world. But notice I've deliberately left some room because you need some extra keystrokes in the world of C. Anytime you type out some text, otherwise known as a string of text, to use computer science jargon, you need to quote it, in this case with double quotes. Double quote at the left, double quote at the right. And notice, too, I'm going to include some slightly cryptic symbol here, too, \n, which I also typed and said verbally earlier. And then one last nuisance at the end of this, which is a semicolon. So suffice it to say, this is why we start with Scratch. This, drag and drop, you're good to go. In a language like C, printf, parenthesis, double quotes, the text you want, \n, semicolon at the end. There's just so much syntactic overhead. But at the end of the day, it's just a function. And you'll get used to these sort of nuisances like the parentheses, the quotes, the semicolon, and the like. But things can very easily go wrong. And it's very easy to make mistakes even with lines of code like this. So let me do this. Let me go back to VS Code where I have the exact same code. Notice that on line 5 is exactly that line of code. So this is the equivalent of the say block. And let's consider what mistakes I may make early on, or even now, 20 years later after learning this, that are quite common in general. Suppose I forget the semicolon there. So easy to do. You will do this eventually. Let's see what happens now when I go back to my terminal window and try to compile my code again. Just to keep things tidy, I'm going to clear my screen. But that's just for lecture's sake so that we can focus only on the most recent command. But I'm going to go ahead now and rerun make hello. This will ensure that my program is recompiled. And this is a manual process. I changed my code. The zeros and ones on the hard drive have not changed. I need to recompile it to output the latest machine code. So here we go. I'm going to hit enter, crossing my fingers as before. But again, I removed the semicolon by accident. Oh my God, there's like more lines of errors now than there are of actual code. And this too takes some getting used to. The programs we're using were not necessarily written with the least comfortable audience in mind, but really professional programmers back in the day. But through practice and through experience and through mistakes, you'll start to notice patterns here too. So here's what I typed. Make hello after the $ prompt. Now I get yelled at with as follows. Hello.c :5:29. Well, what's that referring to? I've screwed up somewhere on line 5 on the 29th character on that line. Generally, the specific character is not that useful unless you actually want to count it out. But line 5 is a good clue. Why? It means I screwed up somewhere on line 5 here. All right, well, what is the error? Expected a semicolon after expression. And this error is actually pretty obvious now that I see it and I realize, oh, wait a minute. All right, here's my line of code. Here in sort of ASCII art, so to speak, textual text representing graphics, it wants me to put in green here this semicolon at the end of that line. One error generated, built in, so some esoteric stuff there. But my program did not compile. When you see an error like this, it means it did not work. So what's the fix? Well, obviously, the fix is to go back up here, put the semicolon there. And now, if I recompile my code with make hello, I won't clear my screen just yet, just to show you the difference. Now, it just worked. So we're back in business as before. All right, let me pause here, though, and ask if there's any questions about what I just did. These error messages will become frequent initially. Yeah? Really good question. Do you need a semicolon after every line or just some? It turns out just some. This is something you'll learn through practice, through demonstrations and examples today. Generally, you put a semicolon after a statement, so to speak. And this is the technical term for this line of code. It's a statement. And think of it as it's kind of the code equivalent of like an English sentence. So the semicolon in code is sort of like a period in English when you're done with that particular thought. You don't need semicolons for now anywhere else. And we'll see examples of where else you put them. But it usually is at the end of a line of code that isn't purely syntactic like curly braces instead. Other questions on the mistake I just fixed and created for myself? Yeah. Correct. So line 5 is where the error is most likely. Character 29 means it's sort of 29 characters that way. And then it's actually, in this case, giving me a suggestion. The compiler won't always know how to advise me, especially if I've made a real mess of my code. But often it will do its best to give you the answer like this. Yeah. So how come I first typed code space hello.c, and now I'm typing make hello? Two different processes. So when I typed code space hello.c, that was because I wanted to open VS Code and create a new file called hello.c. It's like going to file new in a Mac or PC. Thereafter, though, once the file exists and is actually open here, and it does autosave, you don't need to hit Command S or Control S all the time, I can now compile it with make hello again and again. So theoretically, I should never need to type code space hello.c again unless I want to create a brand new file called the same thing. All right, so what about this other piece of syntax here? Let me clear my terminal window here. You can also hit Control L just to throw everything away, just to clean it up aesthetically. Suppose that I omit whatever this sequence of symbols is, \n, since I'm not really sure at first glance why that's even there. Does anyone want to conjecture, especially if you've never programmed before, what might happen now if I recompile and rerun this version of the program? I left the semicolon, but I took away the \n. Any instincts? All right, well, yeah.
Will the next $sign appear straight after your hello world?
It will. The next $sign will appear right after my hello world. But what makes you think that?
Because the \n creates a new line.
Exactly. \n is actually a special sequence of symbols that creates a new line. And so, to your point, if I recompile this program, make hello, enter, no syntax error, so it did compile this time. So you don't need the \n, you do need the semicolon. But if you don't have the \n, watch what happens when I do /hello this time. Now, indeed, I see hello, comma, world, and then a weird $sign. And this is still a prompt. I can still type commands at it like clear, and everything gets cleaned up. But it just looks kind of stupid. If I run it again here with /hello, it's just not very user-friendly. It is convention that when you're done running your program, you should ideally clean things up, move the cursor to the next line for the user. And so the \n is simply the special symbol, otherwise known as an escape sequence, that C knows means move the cursor to the next line. In other languages, Python among them, uses this same symbology as well. Now, if I go back to the code here, and for instance, I try to do this differently. Like, suppose I don't put the \n. I just hit enter, like a normal person would in Google Docs or Microsoft Word. Let me go ahead and try compiling this program. And this, you would hope, would work, right? You would hope this would print out hello world and then a blank line because I moved the cursor to the next line. But no, if I run make hello now and try to compile that, C does not like this. Now I get a different error, still on line 5, this time starting at character 12. Error missing terminating double quote character, and then some other esoteric stuff. And then this does not sound good. Fatal error this time. Too many errors omitted. Stopping now. So I really screwed up here. So why can't I do this? Just because, like the humans who designed C decided that if you have a string of text, it must stay on the same line. It can get really long. It can soft wrap, that is without you hitting enter, but you can't hit enter to create a new line. If you deliberately want a new line, you have to indeed use this \n escape character. So let me go ahead and do this. Let me put it back. Let me go back to my terminal window. I'll clear the screen again. Let me go ahead now and do make hello to recompile to that version, /hello, and voila, we're back in business with hello. All right, so now let's tease apart some other aspects of this code, because there's a lot going on just to get us to say hello world on the screen. For today, we're largely going to ignore this. Int, main, void, and these curly braces here. We'll come back to that before long as to why it's there. But for now, just think of int, main, void, and these curly braces here as really being the C equivalent of when green flag clicked. Like why? You just need it there. That's how you get your program going. And main is indeed going to be some special function. But more on that another time. But why do I have this line of code here? The correct spelling is indeed standard.io.h, stdio.h, and they're angled brackets this time, so that's a little new. There's a hash and then an include keyword. You know, if you don't know what something is, you know, there's not really that much harm in just getting rid of it and see what happens. So let me delete that line. Let me go back to my terminal window, clear the screen, and then run make hello again. And let's try compiling this program now without that first line. Why? I don't understand it, so let's see what happens. All right, here's yet another error, but let's see. Hello.c, line 5, character 5, so it's pretty early on. Error, implicitly declaring library function printf with type int and then ... So implicitly declaring library function printf. So this is very cryptic sounding. You'll get better at understanding phrases like these. But apparently, I do need the include line for standard.io.h. But why? Based on this symptom, what might your instinct be for what that first line of code is doing for us in the first place? Why intuitively must it be there? Exactly. It's like importing a library so that you can do things like print things out on the screen. Now, in Scratch, you didn't have to do this for most of the puzzle pieces, but you might recall that partway through week 0, I went to the extensions button at the bottom left of the Scratch screen, and I imported some extra puzzle pieces for text to speech that gave us the sort of creepy humanized voice that actually came out of the cat's mouth. Well, that was like adding a library, code that someone else wrote. In that case, it was a third party, but I gave myself access to it. Same here. Turns out that you don't really get printf automatically in C. You have to include a so-called header file that declares that function to exist. Now, the reason for this historically is just efficiency. Back in the day when computers were really slower and resource constrained, you don't want to just give yourself access to the entire kitchen sink of functionality. You only want to include only the functions you actually care about. Nowadays, it's sort of a copy-paste step because you almost always want to print something out on the screen, at least when writing programs like these. But these so-called header files contain enough information about all of the functions in what's called the standard I/O library. And standard I/O just means standard input and output. And that's appropriate, right? Because printing is pretty basic output. Turns out there's other functions for getting input from the human's keyboard. More on that in a bit. But anytime you want to print something on the screen in C, you indeed need to include this header file at the top of your code. And that's going to essentially inform the compiler, hey, compiler, I want to use functionality from the standard I/O library, including printf in this case. And if you omit the header file by accident, it's just not going to work because it doesn't know what printf is. It's sort of some unrecognized symbol in that case. All right, questions then about this line of code. This line of code here, or what these header files are. All right, you might wonder, well, how do you know what functions exist? How do you know what files you might indeed want to include? Well, it turns out that C is a many-year-old language, and it has ample documentation. A caveat is that its documentation isn't necessarily all that user-friendly, but what we have for the course is a simplified version of the official documentation for C at this URL here, manual.cs50.io. So in the world of C, and other languages too, there are what are called manual pages. And these are just like text-based documentation that honestly is typically written in a voice that you kind of have to be an experienced programmer to understand some of it. So what we've done at this version of the same documentation is we've imported all of the original official documentation, but we've added sort of less comfortable translations in English for a lot of the functionality that you might use in class just to help onboard you. So at the end of the day, you don't need this documentation long term, but just to get started, we'll translate it into terminology that you might appreciate from a teaching assistant, for instance, as opposed to the original author of these documents. And so for instance, if you were interested in reading up on what functions exist in the standard io.h header file, well, you could go to a URL like this, or you could search for it at manual.cs50.io. That would show you a list of all of the available functions in that library. and printf indeed would be one of them. And then you could click further on that, reaching a URL like this, that's just going to give you all of the documentation for how to use printf. It turns out you can do even more than than just printing out hello world, and we'll scratch the surface of that today. But it turns out that the documentation will always be your authoritative source ultimately for questions like what can I do and how can I do it. Meanwhile, it turns out that CS50 has its own library accessible via a header file called CS50.h. It turns out in C that output is actually pretty easy, relatively speaking, once you get used to all the curly braces, parentheses, quote marks, and the like. But input is a little more difficult. And if you have programmed before, input's not that hard to do in Python. It's not that hard to do in Java. It's more difficult to do in C. And we'll see why in a couple of weeks. But for the first couple of weeks of the class, we actually provide you with some training wheels of sorts, whereby we have a number of functions that are declared in this file, cs50.h. It lives its documentation at a URL like this. And in a moment, we'll use a few of these. You'll see that CS50 provides you with some functions like getChar for get a single character from the user's keyboard, getInt to get an integer from the user's keyboard, getString to get a sequence of text from the user's keyboard, and a bunch of others as well. So let's actually use some of these functions, how about, by revisiting really the second program we wrote in Scratch last time, which adds some input to the output. So first version of Scratch was just hello world, said the same thing every time you click the green flag. Version 2, recall, though, did this. It asked the user, what's your name? And then that somehow gave it back a return variable, a return value, we called it. And we then joined hello and that name to say something a little more interesting on the screen. So what did that model look like? Same thing as before. We've got a function in the middle, where function is like the code implementation of our algorithm. That takes in one or more arguments, like what is it you want to say on the screen ultimately. And return value in this case is going to be actually a value that comes back. So in the case of getting input, we can consider this ask block again, like last week. The input to it is whatever words of English you want to ask the user. And then it returns a value. And this was called by default in MIT's world answer, though we'll see in C you can call these return values anything you want ultimately in variables. But this is different from a side effect. A side effect is just something visual often that happens on the screen, like the speech bubble or hello world. A return value is actually a value you get back from a function that you can use or reuse. So how do we convert this Scratch block from last week to C code this week? Well, if you want to ask the user for something like their name, you can do this. You use a CS50 function called getString. And you use the parentheses to represent, here comes the inputs there too. You can then put the sentence you want to ask the user, quote unquote, what's your name? But you do indeed need the quotes literally in C, so I'll go ahead and add those as well. Subtle, but I've deliberately included a space after the question mark, but before the double quote, just so that the cursor moves one step over, because in this case, we're not going to get a special speech box like we did in Scratch. It's just going to leave the cursor where it is. So we'll see that aesthetically, that just moves the blinking cursor one space after the sentence on the screen. All right, but the catch is with Scratch, we just automatically got back the answer from the user in a special variable called answer. In C, you're going to have to be a little more specific. In C, if you want to get back a return value from a function like getString, you have to use an equal sign and then the name of a variable on the left. The choice of variables is up to you. I could have called this anything, x, y, z. I'm going to more descriptively call it answer for parity with what MIT did with Scratch. But notice that this doesn't represent equality per se. This is assignment in this case. So in C, when you use a single equal sign, that means copy the value on the right over to the value on the left, from right to left. So what does this do for us? Well, if getString is a function that prompts the user with, quote unquote, what's your name, and it has, I claim, a return value, that means it kind of hands me back some value. But it's up to me in C to do something with that value. So if I want to copy that value into a variable that I can use and reuse, I use an equal sign, and I invent on the left-hand side of that equal sign any variable name I want. There's certain rules, there's certain conventions, but generally if you use a single word with all lowercase, you're in good shape. But C is a little more pedantic than that. And those of you who have programmed before might not be used to this, for instance, in Python, which is a world we'll get to in a few weeks. You also have to tell C what type of value you're storing. So if I do want a string of text from the user. So not an integer, not a single character. I want a whole string of text, like a phrase, a sentence, a name in this case. I have to tell C that this variable is of type string. So it's a little wordy, but you get used to it, and you just have to be precise. You're informing the computer what type of value is going in this variable. All right, it's so close to being correct, but I have omitted something that's annoyingly important still. What's missing still? Yeah. So semicolon. This is a statement. This is like a full thought, if you will, in code. I do need to end it ultimately with the semicolon at the end there. All right, so this was more of a mouthful, but let's try using this in now my code. Let me go back to VS Code, where I have version 0 of my code here. Let me go ahead and include one other file at the top of hello.c, namely include CS50.h, so that I have access now to getString and anything else I might want. Now let me go ahead and add a line of code here inside of these curly braces. And let me go ahead and do this. String answer equals getString, quote unquote, what's your name, question mark. I'm going to add an extra space before the double quote. I'm going to indeed end my thought with a semicolon. And now let me deliberately make a mistake just to make a point here. Let me now try changing hello world to hello, comma, answer. All right, now perhaps, even though this is some new lines of code, you can see where I've erred already. But let me try making this program now. So far, so good. So no error messages. So that's a good thing. Let me go ahead and run /hello. And you'll see the prompt. What's your name? Question mark. And notice the cursor's indeed one space to the right, just because I thought it would look prettier to put a little blank space there, as opposed to leaving it right after the question mark. Let me type my name. But even if you've never programmed before, I have screwed up here. What are we going to see on the screen when I hit enter? Yeah, hello answer, most likely. Why? Because the computer is going to take me literally. And if I say, quote unquote, hello answer, that is the string of text followed by a new line that's going to be outputted to the screen. So we need some way of actually plugging answer into this line of code. It's not quite as simple as Scratch, where you could just grab like a second say block and drag and drop the variable there. We actually need a new syntax. And it's going to look weird at first, but it is everywhere in software nowadays, especially in the world of C and certain other languages. So let me go ahead and propose that I solve it as follows. Well, back when we did this in Scratch, remember that the most elegant solution was this here. We used the say block still, which is going to be analogous to printf today. But I used the join puzzle piece in Scratch to combine hello, comma, space, and then the name of the human. So how do we translate this code to C? Well, it's going to look a little different now. I'm going to start with printf with some parentheses and a semicolon representing the say block. But how do I now do this joining? This is where the puzzle pieces don't quite translate perfectly. This would be the way to do this. You put hello, comma, and then a placeholder. So this is what's known as a format code in C, specifically for printf. And it just means this is a placeholder for a string. Again, a string is just text. So this means, hey, computer, print out literally hello, comma, space, and then not literally %s. %s is treated specially to mean plug in some value here. All right, so what else do I still need? Well, this is still some text. So I'm still going to surround the whole thing with double quotes. I'm still going to include my \n just to keep things tidy and move the cursor to the next line. So the last step here in C is to somehow join the answer with that word hello. And the way you do this is with printf, passing it not one argument, which is what I keep doing. I keep passing it one string of text, quote unquote. I'm going to now add a comma and then the name of the value that I want printf to go back and plug into that %s. And printf is just smart about this. If you have 1%s and one additional argument after a comma, it just does from right to left, it plugs it in. If you have 2%s's and two variables after the comma, that's OK too. If you separate them with commas, it'll plug the first into the first %s and the second variable into the second %s. So it's just left to right order of operations. It's not as pretty or as simple as this, but this is how it's done in C. All right, let me pause, because this is a lot of symbology. Any questions on this technique here? Yeah? Yeah, really good question. Why did I exclude the \n a moment ago? Really just my sense of aesthetics, if you will. No good reason beyond that. So if I look back at my code, you quite rightly notice that I didn't have a \n there. That's just because for whatever sense of style that I have, I wanted the name to be typed right after the question. I totally could have added a \n there instead of a space. That would have just allowed me to type down here. Totally fine. Just wanted to show you something different. Good catch. Yeah. Can I show an example with 2% s's? Surely. So let me, in VS Code, do this. Let me clear my terminal window to clean things up. And let me do this. Instead of calling the variable answer all over the place, let me call it first. And I'll ask 2 questions. What's your first name? And now let me do string last equals get string, quote unquote, whoops, capitalization matters. So let me fix my capital S there. Quote unquote, what's your last name? Question mark, semicolon. And now we'll plug in 1% s and a second %s. And now I'm going to plug in first, and last, coincidentally. And now I'm going to go back to the terminal window. Make hello, crossing my fingers. All good. /hello. Here's my first question, David. Here's my second question, Malin. And again, hello, David Malin. So it just inserts them left to right. All I was doing for parity with Scratch, though, and let me go ahead and undo this again. I'll go back to answer like this. I'll go back to just asking for the person's name. I'm going to delete mention of last. I'm going to delete mention of the second %s. And now if I recompile this simpler version, I did screw up. Didn't intend it. What did I do wrong? Yeah, so just newbie mistake. So I changed my variable back to answer just to be consistent with week 0, but I didn't change it here. So I have a use of undeclared identifier first. It's undeclared in the sense that I declared answer a line prior. I didn't declare first. So indeed, intuitively, I want to just change that to that. Let me now do make hello again. /hello. Type in just my first name this time, and there it is. Hello, David. Questions on this then syntax with printf? Yeah. The placeholder, I'll zoom in, is just a single % and then an s. So inside of my string here is %s. And then I have a comma outside the quotes, and then the name of the variable whose value I want to plug in for that %s. And now notice there's technically 2 commas inside of these parentheses on line 7. And yet I claim that printf at the moment is only taking in 2 arguments. Why is there then 2 commas but only 2 arguments? If there were 2 commas, you would think there'd be 3 arguments, right? Exactly. The comma in between the quotes is just an English thing. It's separating the hello from the name. So that's why, indeed, it's not only in quotes. That's also why programs like VS Code tend to syntax highlight it a little differently, just so that it sort of jumps out as different to you, even though in this case it's a little subtle, a light blue versus white. But indeed, it's trying its best. Other questions now on this placeholder? Yeah? Good question. If I wanted to add an exclamation point after the name, would I have to add another placeholder and so forth? I could actually do that much more simply. I can just put the exclamation point right after the %sign. I don't need an additional placeholder per se. If I zoom out now and run make hello again, /hello, and type in just my name, no exclamation point, now you'll see more excitedly hello, comma, David. So printf is smart. It will figure out where the %s is and then go and replace it. Now, let me propose that a common thing in programming is that as soon as we make a decision as to how to design something, we often paint ourselves into a corner and sort of regret a decision. Can anyone think of a problem that arises from using %s as a placeholder in this string to printf? What could go wrong if we're using % in this special way? Yeah, if you literally want to say, for whatever weird reason, %s on the screen, or honestly, even just a single %. It turns out that a % is treated specially inside of printf strings. So what's the solution here? There's different patterns of solutions to problems like these. But suppose you wanted to say, I got 100%, for instance. Let me go ahead and change this completely. So I got 100% on your test or whatever. All right, let me go ahead and run make hello, enter. All right, so invalid conversion specifier. I mean, I have no idea what this means, but it's underlining the percent sign is problematic. Well, it turns out that humans years ago decided, oh, all right, damn it, we already used percent. Well, 2% signs will mean 1% literally. So now if I rerun make hello, aha, /hello, I got 100%. So there's going to be things like that, honestly, that you have to ask someone, you have to Google, you have to look it up in the documentation. But there's always a solution to those kinds of problems. And thankfully, they don't come up all that often. Yeah. Oh, just pointing. Other questions? Yeah. If you have multiple variables, it is in the left-right order. So printf will analyze the first string of text that you pass in between quotes, and whatever the first percent is, the first variable that's passed in after a comma gets plugged in there. And then the second gets plugged into the second, third into the third, and so forth. So it's just based on left to right. Yeah? It's just a placeholder. It's called a format code. And it just means colloquially plug in some value here. And printf, the humans who wrote printf decades ago decided to treat %s special. Why? Just because. They needed some placeholder. They decided that no one's ever going to really want to type %s. And if they do, they can just do %s. So they decided to implement printf in such a way that they have code that analyzes whatever text comes in, looks for %s, and then somehow plugs in the subsequent values into that placeholder. And just as, question? Sorry? So what if you wanted to do single characters like initials like DM or DJM for first, middle, last? Absolutely. And that, too, is a perfect segue from the two of you to what in general are going to be called data types in C. So it turns out in C, there's not only strings as text, and we'll see in more detail and over the next couple of weeks what a string really is underneath the hood, but strings of text are not the only thing that programs can output. They can indeed output single characters, as for initials. They can output integers as well. Turns out that printf has different format codes for all sorts of different data types. And just some of the data types we'll see in the coming weeks will be this list here, which you'll notice it almost perfectly lines up with the CS50 functions that I rattled off earlier, like getChar, getInt, getString. The reason we called those functions that is because each of them is designed to return to you a different type of value. We've used getString already in this example here. We'll soon see getInt, and we'll see opportunities to use others. But these indeed are the menu of available data types, plus others, ... that you can use when writing a program in C. The onus, therefore, is on you to decide in advance, do I want to store an int in this variable, or a string, or heck, when writing fancier code, an image, or a sound, or a video even. Those can all be different data types, ... But for now, we'll focus really on just these primitives. That was a lot. Let's go ahead and take a 5-minute break here. No cookies yet, but in 5 minutes, we'll come back, dive into more detail. In our second break today, we'll have cookies. All right, we are back. And so if you have been playing along at home but hitting some bumps in the road, that's totally normal. And indeed, the goals of lecture generally will be to give you a sense conceptually of where we'll be going during the course of the week. But it's indeed through the hands-on labs and problem sets that you'll really have an opportunity at your own pace to work through some of those same bumps in the road. But for today, let me give you a few more building blocks. And these two will translate from scratch initially, namely like conditionals, like how now in C, after knowing now how we can use functions, at least getString and printf, and we can use variables like the string I created earlier. How can I now add to the mix things like decision making and conditionals at that? Well, with conditionals in Scratch, we had this kind of syntax. On the left, here in Scratch is how you might express if two variables, x and y, have this relationship. If x is less than y, then say on the screen x is less than y. Well, let me translate that to the right now in C code. So in C, the corresponding code is going to look like this, assuming x and y already exist. More on that later. And notice a pattern we're going to see again and again. there is going to be parentheses around the x and less than y. So parentheses around the Boolean expression, recall. The Boolean expression is the true, false, the yes, no answer, a question that you're trying to ask in order to decide whether or not to do something. So you use parentheses there. So similar in functions where we used parentheses for printf and parentheses for getString. And this is just a weird inconsistency stylistically. When using the keyword if, you should, as a matter of best practice, put a space after the word if. When using a function like printf or getString, you shouldn't. Both will work, but you'll find that these are conventions stylistically that most people adhere to. So space when using an if here. All right, now inside of the curly braces is where the actual code goes that you want to execute conditionally. So if you want to print out x is less than y only if x is actually less than y, in C, you use this open curly brace, which up until now you've probably rarely used on your keyboard, and the closed curly brace down here. And those are kind of hugging, if you will, the one or more lines of code underneath the if. Very similar in spirit to how the orange block here kind of hugs the purple puzzle piece here. So there's no graphics in C. It's all text. So you can think of those curly braces as really representing the same idea. As a side note, if you only have one line of code inside of the if condition, if you will, you strictly speaking don't need the curly braces, but as a matter of good style, do include them. It will make more obvious what your intent is. How about in Scratch if you wanted to express this? Two ways in the road that you might go, left or right, so to speak. Well, if x is less than y, I want to say x is less than y. Else, I want to say the opposite. X is not less than y in this case. So I'm making a decision based on that Boolean expression. In C, it's almost the same, but you're adding to the mix the keyword else. So MIT borrowed for Scratch the same keyword there, and a second pair of curly braces, open and closed respectively. And you might guess now what goes inside of those. Well, you print out x is less than y, or you print out x is not less than y. All right, what if there's a three-way fork in the road? In Scratch, this actually gets a little unwieldy graphically, if you will. But notice that in Scratch, this is how we could express if x is less than y, say x is less than y. Else if x is greater than y, say x is greater than y. Else if x equals y, then say x is equal to y. Now, minor inconsistency here. Just a little bit ago, I claimed in C that an equal sign represents what operation? Assignment from right to left. Insofar as Scratch is really meant for kids and they didn't really want to get into the weeds of this kind of semantic, equal sign in Scratch means equality. However, we're going to need to fix this in C in just a moment. In C, equal sign means assignment right to left. In Scratch, it literally means what you would expect. All right, let's translate this code then to C. On the right, this code would correspond really to this. And you can perhaps see somewhat goofily what the solution was, not unlike the %% solution earlier when humans painted themselves into one other corner. You say if, you say else if, and you say else if. And how did we resolve the use of a single equal sign already? In C, when you want to express equality, is the thing on the left equal to the thing on the right? You literally use two equal signs right next to each other, no space in between them. But now, this code would be correct on both the left and the right, whether you're doing this in Scratch or C respectively. But now we can kind of nitpick our code, specifically the design thereof. Logically, can anyone critique the design of this code, either in Scratch or C? Like, I feel like we could do better. How about in back? Perfect. Logically, it's got to be the case that x is less than y, or x is greater than y, or by conclusion, it's got to be equal to y. So why are you wasting my time or the computer's time asking a third question? You don't need to ask this final else if, because logically, as you note, it should go without saying. So it's a minor tweak, like you're doing extra work potentially in the cases where x equals y. So we can just refine that. And just like in Scratch, you could just use an else block. Similarly, in C, could we simplify this code to just an else, a sort of catch-all logically that just handles the reality that, of course, that's going to be the final situation instead. All right, so we have this ability now to express conditionals with Boolean expressions. Let's actually do something with this next here. So let me go back to VS Code. I've closed hello.c, and I want to create a second file for the sake of some demos now. Recall that you can create new files by typing code space, and then the name of the file you want to create. For instance, I might do compare.c. I want to write a program that's going to start comparing some values for demonstration's sake. But before I do that, let me just show you by opening the File Explorer at right. This is similar in spirit to a Mac or PC. Like you can go up here and click on an icon, and you can click on the plus icon, and you'll get a blue box, and I can type in compare.c, and I can just manually create it that way. Notice that opens the tab even without my having typed code. So again, on the left, you have a GUI, a graphical user interface, albeit a simplistic one. On the right, and at the bottom here, you have a command line interface, but they're one and the same. What's nice, though, is that if I close this file, accidentally, intentionally, whatnot, I can reopen it without creating a new one by just running that same command, code space compare.c. So code is a VS Code thing. It's just a user-friendly shortcut, but it's just creating a file or opening an existing file like that. I'm going to hide the File Explorer just to make more room for code here. And let's go ahead and do this. Let's write a program that compares two values that the human inputs, but not strings this time. Let's use some actual integers. All right, I'm going to go ahead and include the CS50 library's header file at top. CS50.h. I'm going to also include standardIO.h. Why? One gives me user-friendly input via getString, getInt, and so forth. One gives me user-friendly output via printf in the case of standardIO.h. Now I'm just going to kind of blindly type this line of code, which we'll come back to in future weeks. But for now, that's analogous to the when green flag clicked code in Scratch. And now let's go ahead and do this. Let me go ahead and get an int from the user and ask the user, what's x, question mark. I'm not going to bother with a new line. I want to keep it all in one line just for aesthetics sake. But when I get back an int, just like I get back a string, I get back a return value. So if I want to store the result of getInt somewhere, I had better put it in a variable. And I can call the variable anything I want. Previously, I used answer or first or last. Now I'm going to use x. But there's still two things left to do here. Logically, even though we haven't technically done this yet. What do I still need to do? So I need the semicolon at the end and the int at the beginning. You, the programmer, starting today, kind of need to decide what you're going to be storing in your variables, and you just need to tell the computer that so that it knows. Now, as a teaser for languages like Python, more modern languages, turns out humans realized, well, gee, this is stupid. Like, why can't the computer just figure out that I'm putting an int there? Why do I have to tell it proactively? So in some languages nowadays, like Python, we'll get rid of some of this syntax. We'll get rid of the semicolons. But for now, we're looking at really the origins of how this all worked. All right, so I've done this one line ending with semicolon. Let me do one other, and let me get a second int asking the user, what's y, question mark. So almost identical, but different responses from the user, hopefully. And let me just ask simply, if x is less than y, in parentheses, then some curly braces, let me go ahead and print out, quote unquote, x is less than y, \n. And now just as a side note, I seem to be typing kind of fast. Some of that is because VS Code is helping me. Let me go back to this first line with the if, hit enter, and now I'm only on my keyboard going to type the open curly brace. This is a feature of many text editors nowadays. It finishes part of your thought. Why? Just to save yourself a keystroke, to make sure you don't accidentally forget the closing one. So you'll notice sometimes that things are happening that you didn't type. It's just VS Code or future programs you use trying to be helpful for you. I'll go ahead and manually type out now printf, x is less than y, \n, close quote, semicolon. So let me go ahead now and try to run this. And we'll see. Let's see. So make, not hello, but make compare, because this file is called compare.c. Hitting enter. OK. No output is good because it means I haven't messed up. Let me do /compare instead of /hello. Enter. What's x? How about 1? What's y? How about 2? X is less than y. Well, let's try it again. And here I'll save you some keystrokes too. Let me clear my screen. Instead of constantly typing /this and /that, you can also use your keyboard's arrow keys in VS Code to scroll back through time. So if I hit up once, there's the last command I wrote. If I do it up twice, there's the second to last command I wrote. So sometimes if you see me doing things fast, it's just because I'm kind of cheating and going through my history like that. All right, let me go ahead, though, and rerun /compare. Enter. Let's reverse it this time. 2 for x, 1 for y. And now, of course, there's no output. All right, well, that's logically to be expected because we didn't have an else here. So let's add that. Else Now let's open my curly braces, letting VS Code do one of them for me. Printf, quote unquote, x is not less than y, \n, semicolon. Let me go ahead and try this again. /compare, enter. Again, 2 for x, 1 for y, and we should see, what did I do wrong? Why am I not seeing any else output? Yeah. Exactly. You got to get into the habit after you change your code of recompiling it. Otherwise, the zeros and ones in the server are the old ones until you manually compile. So let's fix this. Make compare, enter. No error messages. That's good. /compare 2, 1. And now I get back the output. So x is not less than y. How about if I go and add in the third condition? Well, we can do this either efficiently or inefficiently. Let me go ahead and refine this. So else if x is greater than y, let's literally say x is greater than y. And now I could do else if x equals y, but I think we already claimed that that's unnecessarily inefficient. So let's just have our catch-all. And here I'm going to say, quote unquote, x is equal to y \n, close quote there. So I think now with this code, we've handled all 3 scenarios. Let me go ahead and recompile it properly. Make compare, /compare, and now 1 and 2, x is less than y. Let me run it again. 2 and 1. X is greater than y. And lastly, 1 and 1, and x is equal to y. So for the most part, our code's getting longer. We're up to like 21 lines of code, though some of them are just single characters on the screen. Almost everything else is the same. I'm using the CS50 libraries header file for my getInt function, standardIO.h for my printf function, and the rest of this is just now new syntax for conditionals as well. Questions then on this C implementation of just some basic comparisons like this? Any questions? Yeah? Good question. Do the opening brackets need to be on a separate line? In CS50, yes. What you'll see is that as part of the submission process, we compare your code against a style guide, which is the norm in industry. A company would have its own sense of style and how its code should look. And there's generally automated tools within a company that help give feedback on the code or stylize it as such. There are alternative styles than what we use in the class. We deliberately keep and ask that you keep the curly braces on their own line, if only because it rather resembles like the hugging nature of Scratch's blocks and just makes clear that they're balanced, open and closed. However, another common paradigm in some languages and with some programmers is to do something like this on each of them. So you have the opening curly brace on the same line as here. We do not recommend this. This is in vogue in the JavaScript world and some others. But ultimately, in the real world, it's up to each individual programmer and or the company they're working for, if applicable, to decide on those things. All right, so beyond then these conditionals, what if we want to do something that's maybe pretty common? So almost every piece of software or website nowadays that you use has you like agree to some terms and conditions by typing like yes or no, or just Y for yes and N for no. So how could we implement some kind of agreement system? Well, let me do this. Let me create a new program, a third one called agree.c. So I'm going to write code agree.c just to give myself a new tab. I'm going to start as always now, include CS50.h. Let's include standardIO.h. And then let me do my int main void, which again, for today's purposes, we'll take at face value is just copy paste. And if I just want to get y or n, for instance, instead of yes or no, we can just use a simpler variable here. How about just a char? A character, a single character. So I can use getChar to ask the user, for instance, do you agree ? But as before, I need to store this somewhere. So I don't want a string because it's a single char. I don't want an int. I just want a char. And it's literally char. And then I could call this thing anything I want. It's conventional. If you have a simple program with just a single variable and it's of type char, call it C. If it's an int, call it I. If it's a string, call it S. For now, I'm just going to keep it simple and call it C. And now I'm going to ask a question. So if C equals, how about quote unquote y, then let me go ahead and print out agreed \n as though they agreed to my terms and conditions. Otherwise, let's see, else if the character equals quote unquote n, then let me go ahead and print out, say, not agreed. as though they didn't, quote unquote. And let's leave it at that, I think, here initially. Now you'll notice one curiosity, one inconsistency perhaps. Does anyone want to call it out, though it's somewhat subtle? I've done something ever so slightly differently without explaining it yet. Do you see it? Yeah, so I've suddenly used single quotation marks for my single characters and double quotes for my actual strings of text. This is a necessity in C. When you're dealing with strings, like strings of text, like someone's name, a sentence, a paragraph, anything really more than one character, you typically use double quotes, and indeed you must. When dealing with deliberately single characters, like I am here for Y or N, you must use single quotes instead. Why? Because that makes sure that the computer knows that it's indeed a char and not a string. So double quotes are for strings, single quotes are for chars. So with that said, let me go ahead and zoom out. Let me go ahead in my terminal window, run make agree, enter. Seems to work OK, so let me go ahead and do /agree. Let me go ahead now and type in Y. Here we go. Enter. Let me try that again. Rerun /agree. How about no? Enter. Why is it not behaving as I would have expected? Yeah, I kind of cheated there, and I hit the caps lock key just as I started typing in input. Why? Because I deliberately wanted to type in uppercase instead of lowercase, which is kind of reasonable. Right? It's a little obnoxious if you force the user to toggle their caps lock key on or off when you just need a simple answer. That's not the best user experience or UX, but it would work if I cooperated. Let me run this again without caps lock on. Y, lowercase for yes. That worked. N, lowercase for no. That worked. But how could I get it to work for both? Well, how about this? Let me go ahead and just add two possibilities. So else if C equals quote unquote capital Y, then also do printf agreed \n. And down here, else if C equals single quote capital N, then go ahead and print out again, not agreed. OK, this I will claim now is correct. And I'll do make agree real fast. /agree, and I'll use capital. It now works. I'll use capital. It again works. But this is perhaps not the best design. Let me hide the terminal window and pull this up on the screen all at once. Why might this arguably not be the best design, even though it's correct? There's another term of art we can toss here, like something smells kind of funky about this code. This is an actual term of art. Like there's code smell here. Like something smells a little off. Why? What do you think? Yeah, there's the same output again and again. I mean, I manually typed it, but honestly, I might as well have just copied and pasted most of my original code to do it again and again for the two capital letters. So if line 10 and 14 are the same, and line 18 and 22 are the same, and then the rest of these if and else ifs are almost the same, like there's some code smell there. Like it's not well designed. Why? Because if I want to change things now, just like last week in Scratch, I might have to change my code in multiple places, or copy paste is never a good thing. And God forbid I want to add support for yes and no as full words. It's really going to get long. So how can we solve this? Well, it turns out we can combine some of these thoughts. So let me try to improve the yeses first. It turns out if I delete that clause, I can actually OR things together. In Scratch, there's a couple puzzle pieces, if you didn't discover them, that literally have the word OR and the word AND on them, which allow you to combine Boolean expressions so that either this or this is true, or this and this is true. In C, you can't just say the word OR. You instead use two vertical bars. And vertical bars together mean or, logically. And so I can say C equals quote unquote capital Y agreed. And now I can get rid of this code down here. And let me go ahead and say vertical bar twice C equals quote unquote N in all caps. And now my program's like, roughly a third smaller, which is good. There's less redundancy. And if I reopen my terminal window, rerun make of agree, /agree, now I can type little y or big Y, and same thing for lowercase and uppercase n. Any questions then on this syntax, whereby now you can combine thoughts and just kind of tighten things up? And there'll be other such tricks too. Yeah? A really good question. Is there not a function to just ignore the case? Short answer, there is, and we'll see how to do that in actually just about a week's time. And in other languages, there's even more ways to just canonicalize the user's input, throwing away any space characters they might have accidentally hit, forcing everything to lowercase. In C, it's going to be a little more work on our part to do that. But in fact, as early as next week, we'll see how we can do that. But for now, we're comparing, indeed, just these literal values. Other questions?
So we're assuming the user's going to put in what they're supposed to. How do you handle if they were to put in a number?
Really good question. So we are assuming with this program and all of my last ones that the human's cooperating. When I asked for their name, they typed in David and not 1, 2, 3. Or in this case, they typed in a single character and not a full word. So this is one of the features often of using a library. So for instance, if I run agree again and I say something like sure, enter, it rejects it altogether. Why? Because SURE is a string of characters. It's not a single character. Now, I could just say something like X, which is neither Y nor N, of course, but it tolerates that because it's a single character. But built into CS50's library is some built-in rejections of inputs that's not expected. So if you use getInt and the user types in not the number 1 or 2, but cat, C-A-T, it will just prompt them again. And this is where, too, if you were to do this manually in C, you end up writing this much code just to check for all of these errors. That's why we use these training wheels for a few weeks, just to make the code more robust. But in a few weeks' time, we'll take the library away, and you'll see and understand how it's indeed doing all that. All right, so how about this? Let's now transition to something a little more Scratch-like literally by creating, how about another program here called meow, so meow.c. We won't have any audio capabilities for this one. We'll just rely on print. And suppose that I wanted to write a program in C that just simulates like a cat meowing. So I don't need any user input just yet, so I'm just going to use standard io.h. I'm going to do my usual int main void up here. And then I'm just going to go ahead and do printf meow \n. And let's have this cat meow 3 times like last week. So I'm going to do meow, meow, meow. Notice as an aside, whenever you highlight the lines, you'll see little dots appear. This is just a visual cue to you to let you figure out how many spaces you've indented. VS Code, like a lot of editors, will automatically indent your code for you. I've not been hitting the spacebar 4 times every time. I've not even been hitting tab. However, in C, the convention is indeed to indent lines, where appropriate, by 4 spaces. So not 3, not 5. And these dots help you see things so that they just line up as a matter of good style. All right, so this program, I'm just going to stipulate right now, is indeed going to work. Make meow, which is kind of cute. And now meow, there, 3 times. Correct. It's meowing 3 times. But of course, this is not well designed. It wasn't well designed in Scratch last week. Why? What should I be doing differently? Yeah. Yeah. It's a perfect opportunity for a loop. Why? Because if you wanted to change maybe the capitalization of these words, or you wanted to change the sound to like woof for a dog or something, you'd have to change it 1, 2, 3 places. And that's just kind of stupid, right? In code, you should ideally change things in one place. So how might I do that? Well, we could introduce a loop, yes, but we're going to need another building block as well that we had in Scratch, namely those things called variables. So recall that a variable, like in algebra, x, y, z, whatever, can store a value for you. And a variable in Scratch might have looked like this. You use this orange puzzle piece to set a variable of any name, not just x, y, or z, but you could call it something more descriptive like counter, and you can set it equal to some value. In C, the way to do this is similar to some of the syntax we've seen thus far. You start by saying the name of the variable you want, a single equal sign, and then the value you want to initialize it to. Copying, therefore, from right to left. Why? Because the equal sign denotes, again, assignment from right to left. This isn't enough, though. You might have the intuition already. What's missing, probably, from this line of code? Just to create a variable? So we need int to make sure the computer knows that this is indeed an int. And then lastly, semicolon as well. And that now completes the thought. So a little more annoying than Scratch, but we're starting to see patterns here. So not every piece of syntax will be new. All right, if you wanted to increment the counter by 1, Scratch uses the verb change, and they mean add the value to counter. So if I want to increment an existing variable called counter, this syntax is a little more interesting. It turns out the code looks like this, which almost seems like a paradox, like how can counter equal counter plus 1? Like that's not how math works. But again, a single equal sign is assignment from right to left. So this is saying take whatever the value of counter is, add 1 to it, and copy that value from right to left into counter itself. You still need the semicolon, but I claim you do not need to mention the keyword int when updating an existing variable. So only when you create a variable in C do you use the word string or the word int, or any of the others we'll eventually see, only when creating it or initializing it for the first time. Thereafter, if you want to change it, it just exists. It's the word you gave it. The computer's smart enough to at least remember what type it is. So this line is now complete. Turns out in code, as we'll see, it's pretty common to want to add things together, increment things by 1. So there's actually different syntax for the same idea. The term of art here is syntactic sugar. Like there's often in code many ways to do the same thing, even though at the end of the day they do exactly the same functionality. So for instance, if after a few days of CS50 you find this a little tedious to keep typing in some program, you can simplify it to just this. This is the syntactic sugar. You can use plus equals and only mention the variable name once on the left, and it just knows that that means the previous thing. It's just slightly more succinct. This, too, is such a common thing to add 1 to a value. And it doesn't have to be 1, but in this case it is. But if it is indeed 1, you can further tighten the code up to just do this, counter plus plus. So anytime in C you see plus plus, it means literally adding 1 to that particular variable. There's other ways to do this in the other direction. If you want to subtract 1 from a variable, you can use any of the previous syntax using a minus sign instead of plus, or you can more succinctly do counter minus minus. This is the way a typical C programmer would do this. All right, so if we have now variables, let's go and solve the meowing with loops. So in Scratch, we saw loops like this. This, of course, had the cat meow 3 times. How do we do this in C? Now, this is where things get a little more involved code-wise, but if you understand each and every line, it will follow logically what's going on. So here I claim is one way to implement a loop that iterates 3 times in C. And this is kind of ridiculous, right? Like we went from 2 super simple puzzle pieces like this to, my God, like it's 1, 2, 3, 4, 5, 6 lines of code, all of which are pretty involved. So like that escalated quickly. But what's each line doing? And we'll see other ways to do this more simply. So we're initializing a variable called counter to 3, just like before. Why? Well, what does it mean to loop or to repeat something 3 times? Well, it's kind of like doing something 3 times and then do it, and then count down, and then do it, and then count down, and then do it until you're all out of counts. So this is declaring a variable called counter, setting it equal to 3. Then I'm inducing a loop in C, which is similar in spirit to repeat 3, but you have to do more of the math yourself. So I'm asking the question in parentheses, while counter is greater than 0. What do I want to do? Well, per the indentation inside the curly braces, I want to meow 1 time. And then to be clear, what's this last line of code doing? If counter starts off at 3, this makes it 2 by subtracting 1 from it. Then what happens? By nature of a loop, just like in Scratch, it kind of knows to go back and forth, even though there's a nice pretty arrow in Scratch and there isn't here. C knows to do this again and again and again, constantly asking this question and then updating this value at the end. So if I highlight just a few of these steps, the variable starts off at 3. And actually, let me simplify 2. I claimed earlier that when using single variables, people very often just call it I for int or C for char or S for string, unless you have multiple variables. So let me tighten the code up. And this already makes it look a little more tolerable. Let me actually tighten it up further and one more step. So now this is about as tight, as succinct as you can make this code at the moment. So what's actually going to happen here? Well, the first line of code executes, and that initializes I to 3. Then we check the condition. While I is greater than 0. Is I greater than 0? Well, per my 3 fingers, obviously. So we print out meow on the screen. Then we subtract 1 from I, at which point now we have 2 as the value of I. Then the code goes back to the condition. And notice the condition there is in parentheses. That's another Boolean expression. So loops can use Boolean expressions, just like conditionals use Boolean expressions to make decisions. The loop, though, is deciding not whether to do this thing or that, but whether to do the same thing again and again and again. And as it ticks through the code one line after the other, it's ultimately going to get down to 1 and then 0 and then stop. So put another way, came with some props here. So suppose this ball here is your variable, and you initialize it to 3 with like 3 stress balls. You can do something 3 times, right? If I want to give out 3 stress balls, here's your chance for free stress balls without having to answer any questions. OK, there we go. So here we go. Subtracting 1 from my variable. I'm left with 2. Oh my God. All right. Don't tell Sanders. Oh, I'm sorry. Oh, OK. That ended poorly. Apologies. All right, but now the educational point, though, is that my variable has been decremented further to just have. I'm not throwing that far again. I can't do this. Here we go. All right, here we go. And one final subtraction, and now our variable is left empty. So we have 3 stress balls there, and that's all a variable is, right? It's some kind of storage. It's actually, of course, implemented in the computer's memory. But metaphorically, it's really just like a bowl with some values. And every time you add, or in this case, subtract, you're just changing the value of that variable. And then the code, meanwhile, of course, in parentheses, is just checking, is the bowl empty? Is the bowl empty? Is the bowl empty? AKA, is I greater than 0 or not? Any questions on how we've implemented loops in this way? And I owe you a stress ball after class. Questions on loops? All right, so it turns out this is kind of ugly. And like this really starts to take the fun out of programming when you have to like write out this sequence of steps. So it turns out there's other ways to do this. But first, let's see logically how else you might express this, because it's a little weird that we keep using 0. So the one other way to do this would be to invert the logic. You could absolutely start with your variable, call it I, equal to 1. And then you could ask the question, is I less than or equal to 3? And notice a bit of new syntax here. On your typical keyboard, there is no less than or equal sign or greater than or equal sign like you would write in math class with one over the other. And so in C, you use 2 characters, less than followed by an equal sign, or if appropriate, greater than followed by an equal sign. And that logically captures that idea. So notice that I'm kind of changing my questions. I'm initializing I to 1, and then I'm going to increment it ultimately to 2, and then 3. But because I'm doing less than or equal to, it's still going to go from 1 to 3. So that works too. We could similarly do this yet another way. We could initialize I to 0, and then we could say, well, I is less than 3 and keep incrementing it. And I showed this last form as actually the most canonical. Like it might be the most human-like to think in terms of 1 to 3. It might be the most stress ball-like to think in terms of 3 to 0, counting down. But typically, the go-to syntax for most programmers, once you get comfortable counting from 0, is to always start counting from 0 and count up to less than the value you're counting up to. So it would be incorrect Y to change this to less than or equal to 3 here. What would happen if I changed the less than to less than or equal to? Yeah, it'll now a fourth time, in fact, total, right? Because you'll start at 0, then 1, then 2, then 3. And less than or equal to 3, sorry, 3 will give you the 4th time. So we do want it indeed to be just a single less than. All right, so now that we have those options, let me just give you one other. And this one takes a little more getting used to as well, but it's probably the more common way to write this. Let me go ahead and propose that we implement this as follows. Let me go back to my code here. Let me go into my several printfs, getting rid of all but one of them ultimately. And let's implement this in code. So let's do int I gets 0. How about then while I is less than 3. Then let's go ahead and say printf, quote unquote, mellow, meow, \n. And then we have to do I minus minus or plus plus? So plus plus, because we're starting at 0 and going up 2, but not through 3. So let me go ahead now and make meow after clearing my terminal, /meow. And it's still just as correct, but it's a little more, it's a little better designed. Why? Because now if I want to change it from 3 to 30 times, for instance, I can change it there. I can recompile my code. I can do /meow and done. I don't have to copy and paste it 27 more times to get that effect. And I can even change what the word is by changing it in just one location. But it turns out there's other ways to do this too. And let me propose that we introduce you to what's called a for loop as well. So if you want to repeat something 3 times, you can absolutely take the while loop approach that we just saw. Or you can do this. And this one's takes a little more getting used to, but it kind of consolidates into one line all of the same logic. So notice we have the keyword for here. And for is just a preposition in this case that generally implies here comes a loop. Inside of parentheses here is not just a Boolean expression. And this is where things get a little weird. There's three things. To the left of the semicolon, in the middle of the two semicolons, and to the right of the semicolon. This is really the only other context we'll see semicolons, and it's weird. Normally it's been at the end of the line. Now it's two of them in the middle of the line, but this is the way humans decided years ago to do it. So what is this doing? Almost the same thing. It is going to initialize a variable called I to 0. It's going to then check if it's less than 3. It's then going to do whatever in the curly braces, and it's lastly going to increment I and repeat. So just highlighting those in turn, at first, I is initialized to 0, just like before. Then this condition is checked. This is a Boolean expression. Yes or no, true or false will be its answer. And if I is less than 3, which it should be once it starts at 0, well, then we're going to go ahead and print out meow. Then I is going to get incremented. So it starts at 0. It goes now to 1. At that point, the Boolean expression is checked again. So you don't keep changing I back to 0. That first step happens only once. But now you repeat through those three other highlights. I check if I is less than 3. It is. So I print out meow. It then increments I. I check if I, now 2, is less than 3. It is. I print out meow. I gets incremented. I now check. Is I less than 3? No, it's not, because 3 is not less than 3. And so the whole thing stops. And whatever code is below this curly brace, if any, starts executing instead. Just like in Scratch, you break out of the loop and the puzzle pieces being hugged. Questions then about this alternative syntax for loops, aka a for loop. Sorry, say again? Yeah, can I explain again why it doesn't reset to 0? Honestly, just because. Like, this was the syntax they chose. This first part before the first semicolon is only executed once, just because. That's how it's designed. Everything else cycles again and again. And this is just an alternative syntax to using the slightly more lines of code. It was like 6 lines of code using the while loop. Logically, it's the same thing. Programmers, once they get more comfortable, tend to prefer this because it just expresses all your same thoughts more succinctly. That's all. Yeah. OK, so let's just work this into my meow example. Let me go back to the code here. And notice, indeed, if I highlight all these lines, I think we can tighten this up. Let me get rid of all of those and instead do for int I equals 0. And I'm saying equals. Most programmers would say gets. So int I gets 0 means assignment. The word get. Now I'm going to do I is less than 3, I plus plus. Now in here, I'm going to do my printf, quote unquote, meow backslash n. And so it's indeed a little tighter. I mean, 2 of the lines are just curly braces. There's really only 2 juicy lines of code now. Let me go ahead and do make meow dot slash meow. And again, we're back in business with 3 of them printing only. All right, there's one last structure we should explore just because it's sometimes useful. This was a forever block. And this would be a little weird in Scratch to just say meow forever, at least without waiting. But there is indeed a forever block in Scratch, which means do the following forever. And I proposed, I think verbally last week, at least one example where this is useful. Meowing forever, a little annoying. But can you think of common cases where you might want to write code or use a program that loops forever? Yeah. Yeah, playing music, like a Spotify playlist, just repeating again and again would be some kind of loop. Checking for collisions in Scratch. So seeing if something's bouncing off the wall or another sprite. Yeah. Checking for input. So yeah, get string is essentially just waiting there forever for me to type in some input until I do. Checking the time and actually maintaining like human time, like a wall clock behind you. Was that the same? OK, checking the time. And one more. Detecting a key press, too, like in Scratch, just waiting for some kind of event to happen, just like on a phone or a browser. And so there's so many examples where you might want to do something forever, just so you've seen the corresponding C building block. It's a little weird, but this is probably the most canonical way to do it in C. If you want to print meow forever, which would be a little crazy because it would literally print and take over your computer, printing forever, meow, you would generally do it like this. Why? Well, a while loop expects in parentheses a Boolean expression. And a Boolean expression is, again, a yes/no, a true/false question. But if you want the answer to that question always to be yes, or really always to be true, turns out in C, in a lot of languages, we'll then just say true. Because true, T-R-U-E, is never going to change magically to false. I mean, it's just a special word in the programming language. So by saying while true, it just means do the following forever. Another common paradigm before true and false became commonplace would be to do this instead. Change while one. You might see in online examples and texts and the like. While one is really the same thing. Any value that is 0 is generally interpreted as false by a computer. Any value that is 1 or any other non-zero value is generally interpreted as true. And so this too would have the same effect, saying while true or while 1. Generally speaking, while true is perhaps a little clearer these days. Now, meowing forever is not a good thing, but suppose I did that by intent or by accident. Well, let's try this. So here I'll go into my code. I'm going to get rid of my for loop and change my while loop to how about true? And in this case here, well, we'll keep it. Let's do this. Make meow, enter, and you'll see this. Use of undeclared identifier true. This is actually hinting at my mention that the old way was 0 and 1. Nowadays, you could say true or false. But true and false are themselves special words that you have to include. And it turns out if you want to use special Boolean values like this, there's another header file we haven't seen called standard bool that essentially creates true and false as keywords. Alternatively, CS50 includes that same file, so it's more common in CS50 to see it like this. Now, if I clear my terminal window and do make meow and then /meow and hit enter, well, unfortunately, this isn't the best thing to do infinitely when you're in the cloud using a browser. This is indeed browser, just full screened here. This means I'm sending millions of meows over the internet to my computer here. So this will happen to you at some point. Probably not with meow, but you'll lose control over your terminal window. Why? Because you screwed up and like you have an infinite loop. You didn't really intend it, or maybe you did. You were curious to see what happens. What do? Like when does the meowing stop? What recourse do we have here? All right, well, Control-C will be your friend. Sometimes you have to hit it a bunch in a cloud environment, but Control-C for cancel will interrupt a program that's running. And I promise that almost all of you will at some point accidentally introduce an infinite loop because your math is slightly off. When in doubt, click in the terminal window and hit Control-C, sometimes multiple times, and that will indeed cancel whatever is happening there. In this case, I might have intended it, but sometimes it's not, in fact, intended. All right, so we've been taking for granted this whole graphical user interface for some time. And indeed, the commands that I'm typing and the buttons that I'm clicking. And let me just give you a better sense of what it is we are using underneath the hood this whole time, namely an operating system called Linux. So I keep alluding verbally, of course, to Macs and PCs, because almost all of us are running Mac OS or Windows on our desktops or laptops nowadays. But there's lots of other operating systems out there. And one of the most popular one is called Linux. And Linux is very often used on servers nowadays, companies that host email, companies that host websites or apps more generally. Certain computer scientists or computer science students often like to brag that they run Linux just because that's a thing. But it is really just an alternative to Mac OS or Windows that provides you with both a GUI, if you want it, but also and especially a command line environment. Now, fun fact, Windows and Mac OS do have terminal windows or the equivalent thereof. And eventually, you might use it on your own Mac or PC to solve some problem. But Linux is really known for, along with other operating systems, its command line environment, which again I distinguished earlier from GUI as a command line interface or CLI. And that refers really to the terminal window. So if I go back to VS Code here, and let me, in fact, go ahead and close my tab and focus entirely on the terminal window. This terminal window is really just your command line interface to your very own server in the cloud. The term of art here is you each will have your own container in the cloud, which is like your own computer running somewhere on the internet with your own username and password to which you have access, and your own hard drive, if you will, your own home folder that has all of your files for the class. And it's only accessible to you unless you enable live sharing thereof. So when you're typing commands here, it looks like you're typing them, of course, on your own Mac or PC, but they're actually being sent over the browser to some server in the cloud where you are controlling really your own account therein. So it turns out that there are other commands that are worth knowing. And we'll give you just a few of these today. And over the coming weeks, we'll have opportunities to play with others as well. But these are kind of some of the basics. And they're all incredibly succinct. Because indeed, for things you're typing at the command line, humans generally have not wanted to type out long commands. So a lot of these are abbreviations here. Now, perhaps the most common one I'll start with first is ls, a lowercase l and a lowercase s. That stands for, succinctly, list. So if I go to my terminal window now, where up until now I've only typed code, which is a VS Code thing for creating and opening files, and make, which triggers the compilation of my code, what if I now type ls? This will list all of the files in my current folder, my hard drive in the cloud, if you will. So if I hit enter, you'll see a whole bunch of results. Now they're color-coded too. The white ones here end in .c. Those are the source code files I've written during class today. Agree.c, compare.c, hello.c, and meow.c. And you can perhaps guess the green ones here that just by convention have an asterisk on the end to denote that they're special represent what? What are the four others? Yeah. Yeah. The machine code. So those are my actual programs that are identically named minus the .c extension. And the asterisk means that they're executable. That is, in the world of Mac OS or Windows, you would double click. But in the world of a command line environment, that means you do // and then the name without the asterisk to execute or run the code therein. So if I open up my File Explorer, and I'm hitting Command B on my computer here just as a keyboard shortcut, you'll see the exact same thing. So ls is the command line interface for listing the files in your account. But here, because I'm using VS Code or any program like it, I also get a graphical user interface as well. So it's just two different places to be. You're welcome to use whatever you're comfortable with, but over time, will you naturally get more comfortable and capable with the terminal window alone? Well, what else is on this list here? Well, during the break, I saw that at least one of you, for instance, had created a file called hello instead of hello.c. So you were in a situation where you did this accidentally and hit enter, and then you went ahead and typed in all of your code like this. And then down in your terminal window, you were trying to do make hello, enter. And this now didn't actually do anything. Like I'm trying to run the command. I got permission denied, as at least one of you did. Now, why is that? Well, let's just do a quick check. If I do ls, I see now hello, but hello has no asterisk next to it, which means it's not executable. That's my code. Why? Well, notice the top of my tab confirms, oh, I screwed up. I didn't name my file hello.c, which it just has to be. So what do? Well, you could very hackishly like copy this, create a new file, paste it in, or no. Like we know how to rename things now here, because that's one of our options. Let me do this. Let me do mv for move, hello, and then hello.c, and hit enter. You'll see the tab closes because hello no longer exists. But if I now type ls, you'll see, there is hello.c. And if I open that file now, there's all of my same code. And now if I do make hello, now I do get an executable file wherein the world is restored. So mv is just a command not just for renaming, but it also turns out eventually for moving files as well. You can also create directories or folders. So for instance, if I go into VS Code again, and suppose I hover over here and click not on the plus file icon, but plus folder, I can create a folder called, for instance, like pset1 for problem set 1 in the class. And you'll see now that it's empty because all of my other files are in the default folder of my account. But I could also go in there like this, and I could click on File, and now I can create a new file called like mario.c, which is one of the first problems, for instance. But you'll notice now that mario.c is inside of the pset1 folder. So if I zoom out and I type ls at my terminal window, I won't see mario.c anywhere. But I do see a pset1 folder. And it's in light blue followed by a /, which you don't have to type. It just indicates that's a folder. Now, I can visually at top left obviously see pset1 contains mario.c. But if I try to do something like make Mario here, no rule to make target Mario, like it just doesn't seem to exist. And that's because you're in the wrong directory. So in a command line interface, it's not quite as simple as just clicking on a folder and voila, it opens. You have to change into the directory or folder, and cd is going to be the command there. So if I want to actually change into that directory, I can do cd space pset1, enter. And now you'll see my prompt changes. And this is just a common convention, but it's not the only one out there. Now I still have a $sign, which indicates where I can type commands. But before it, I see a reminder constantly what folder I'm in. And we put that there deliberately, like a lot of Linux users do, just to remind themselves where they are. Because unlike Mac OS or Windows, where you have a nice big window telling you where you are, at the command line, you kind of need to be reminded textually. But now if I type ls and hit enter, what should I see? Yeah, Mario.c. And now if I want to open it, if I want to actually compile it, I can run make Mario in this directory once I actually type out all of the code. Rest assured that in problem sets and labs will almost always, certainly in the first weeks of the class, give you exactly the commands to type. Odds are, because it's new to many of you, you will accidentally type the wrong commands. No big deal. Just remember that you have different ways to solve these problems. You've got like the graphical file explorer, which should feel a little more familiar. But in time, you'll start to know and honestly probably prefer commands like these. So cd for change directory, cp for copy a file, ls for list, mkdir to make a directory, create a new folder at the command line instead of with the button, mv for move or rename, rm for remove. So be careful with that one. rmdir, remove directory. And there's dozens, hundreds of other commands. You won't need many of them, but we'll start to scratch the surface all the more over time. But ultimately, this command line interface is going to be a more powerful mechanism, a more capable mechanism, and ultimately a more efficient mechanism for writing code, running commands, solving problems, analyzing data more generally, even though, no, there's going to be some growing pains early on, just because it's probably so new for many of you. So with that said, we have some problems still to solve, but we promised cookies today. So let's go ahead and take a 10-minute break. Cookies are now served in the transept, and we'll be back here in 10. All right, we are back. And up until now, each of the code examples in C we've done have been kind of designed to show one specific topic. But we thought we'd try to take a step back and solve a more general problem and give you a sense of when, given a problem set, for instance, or just a programming problem more generally, like where you even begin and how you go about approaching it when it's not obvious what the point of the exercise is. So one of my favorite games from yesteryear is this one here, Super Mario Brothers, that has come in so many different forms since. But in this original two-dimensional side-scroller game, there was a lot of artwork like this. So for instance, up here in the sky were 4 question marks. And we'll find that in C and a lot of programming languages initially, it's a lot easier, a lot more accessible to focus really on black and white type interactive programs textually as opposed to full-fledged graphics and the like, but more on the more graphical acoustic type of programs before long. But for now, let me go over and propose that we try to just implement in ASCII art. ASCII, again, being the code that maps numbers to letters, at least for English, into a textual version of these 4 question marks in the sky. So for this, let me go over to VS Code. I'll create my own version of Mario.c that will be different from the one you're challenged with in problem set 1. Indeed, in problem set 1, you'll be challenged to build a little something like this, albeit with hashtags for ASCII art instead of graphics. And in Mario.c, I want to just solve this simple problem first. So it's all involving output. So I'll do include standard.io.h so I can use printf. I'll do my int main void, more on why we keep doing that in future weeks. And I'm just going to do something simple initially like 1, 2, 3, 4 \n. This is about the simplest way I can implement 4 question marks in the sky like these here using pure text like this. So let me go ahead and do make Mario. /Mario, and voila, we have those 4 question marks. But we've seen, of course, that there are better ways to do this. And if you wanted to generalize this to be 5 question marks, 6, 60 different question marks, loop was always the answer for not repeating ourselves. So maybe I should rewrite this a little bit more flexibly and say something like this. For int I gets 0, I less than 4, I plus plus, and then inside of the for loop, now I can just do a single question mark. But I don't think what I've just done is correct. Anyone spot the aesthetic bug already? Yeah, why is this wrong? If I want to print the same thing, yeah. Yeah, so I don't think I want a \n after every question mark, because the goal is, again, this like row of question marks in the sky. So if I now recompile this, make Mario, /Mario, OK, it's almost there, but now I have that regression to where the $sign's not on its own line. So I think I need a new line, but I don't think I want it here, because that was not going to end well. Where do I want it instead? Any instinct? Yeah. Yeah, so outside the for loop. So indeed, I can just go below line 8 and above line 9, creating a new one. And now it's totally fine to just print a new line like that. You don't have to print anything else with it. It's indeed a character unto itself. So let's do make Mario one last time, /Mario. OK, so now we're back in business there. Well, what if we wanted to do some other scene from Mario, such as this one here, where there's a lot of vertical obstacles like these bricks here? If I wanted to print out now a column of 3 bricks, and I'll use hashtags for these instead of anything graphical, well, I think we're almost there, right? Like, I think I can now, it's almost maybe a little easier. I can go back here, change the question mark to something that looks more like a brick, like this hash symbol. And I think now I do want the new line character, because when I now do make Mario /Mario, OK, there's my wall of 4. Oh, but wait, I didn't want 4. I wanted to be consistent just with this particular scene here, so I just want 3. So I can still change it in one place. And here again is that paradigm. Even whether you're using 4 or 3, if you get into the habit of starting counting from 0, you go on up to, but not through the value you want to count up to. So that's why I'm using less than instead of less than or equals to there. So this would be the common paradigm, though you could certainly count it like we saw earlier in different ways. But what if things escalate one level further? And when you're in the underground version of Super Mario Brothers, there's a lot of these underground obstructions, including like grids of bricks like this. And let me conjecture that if you slice this up, it's roughly a 3 by 3 grid of bricks that all interlock prettily to give us just one big, large brick like this. So if I want to print out a 3 by 3 grid, now things are getting a little more interesting, because up until now, I've printed either one row horizontally or one column vertically, but we haven't really seen any code where I'm sort of printing or living in 2 different dimensions like the game would imply. But let me propose that we could do this. Let me go ahead and say, all right, suppose I want to print a 3 by 3 grid of bricks. It's really that I want to print, what, 3 rows of bricks. Like a grid is 3 rows. So if I take the high level idea and reduce it to something a little simpler, how do I do that? Well, let me get rid of the printf for a moment, as I did. And let me just stipulate that this for loop, even though it doesn't do anything useful yet, will do something how many times, just by design? All right, 3 times. All right, this for loop is good to go. It will do something 3 times by just using I to do the counting. All right, well, if I want to print out now a row of 3 bricks all on the same line, that's pretty similar to what we did earlier when I just wanted to print out 4 question marks in the sky. So we've kind of seen a solution there, and I dare say we can compose one into the other. So if I want to print out a row of bricks, I could just do this. For int I gets 0, I less than 3, I plus plus, and then inside of this inner loop, if you will, let me print out a single brick like this. And then I don't like where this is going yet, but I think I've taken 2 ideas and I've combined them. But what might be problematic about lines 5 and 7 at the moment? What might be bad here? Yeah, and back? Yeah, I'm using the same integer I, which I feel like could get me into trouble, right? If I'm sort of trying to count 3 things here, but then I'm hijacking this variable and using it inside of the loop, like I feel like I should avoid this collision of names. And so what's a good alternative to I? Well, a programmer, if nesting loops in this way, would pretty commonly go with J. You could certainly change this to be like rows and columns if you want more descriptive variables, but I and J is pretty canonical. So I'm going to go ahead and do this, J++ instead of I++ everywhere. And let me try compiling this. So make Mario, enter, /Mario. OK, so a couple of things are wrong here. This is not a 3 by 3 grid. But if you count these things, how many did I indeed print at least? You can probably just guess logically. Yeah, there's 9 hashes there. Unfortunately, they're all on the same line instead of on 3 different lines. So where logically can I fix this? I'm definitely printing all the bricks. They're just not on the right levels. Yeah? Yeah, so put a new line after the first loop, this inner loop, if you will, the nested loop, if you will. So let me go ahead and print out just a \n here. And what's this doing? Well, I think that's going to solve it by just moving the cursor to the next line after you've done 1 row. So let me go ahead and do make Mario, enter, Mario, and now we're in business. So it's a very simplistic version of this same graphic, but I'm leveraging two different ideas now, the same idea twice rather now. I'm using one loop to kind of control my cursor going row by row by row, but then within that loop, I'm doing left to right, dot, 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 with printing out each of these individual bricks like this. Now, there's a little sloppiness here still. Like if I want this to always be a square, just because that's what it looks like in the game, well, I could change it to be a 4 by 4 square by doing this, or a 5 by 5 grid, whoops, by doing this. Why is this perhaps not the best design, to just keep changing the numbers when I want to change the size? Where could this go awry? Yeah. Yeah, if it's always going to be a square and height is going to be the same as width, I'm just inviting trouble here, right? Eventually, I'm going to screw up. I'm going to change one but not the other. Then it's going to come out to be a rectangle instead of a proper square. So I should probably solve this a little differently. So let me do that. At the top of my main function here, let me go ahead and give myself a variable called maybe n for the number of bricks I want horizontally and vertically. And I'll just initialize that to 3 initially. And instead of putting 3 here, I'll literally just use n. But I'll do it in both places so that now, henceforth, if I ever want to change this and change it to 4 or 5 or anything else, like I'm all done. Like it's better designed because there's a lower probability of mistakes. But I could technically still screw up somehow. I could technically accidentally write a line of code like n++, or, I could just change the value of that variable even though I don't want it to ever change. And maybe it's because I'm a bad programmer. I copy-pasted wrong. I'm working with someone who doesn't know what n represents. I can defend myself and my code against human error like that by going up here to line 5. And instead of just declaring a simple variable like we did in Scratch, I can further harden my code, so to speak, by declaring it to be a constant using the keyword const. Now, this is just a feature of C and some other languages to protect you against yourself by proactively saying n is a constant. Specifically the number 5 or previously the number 3, you cannot accidentally write code elsewhere that changes it. The computer will throw an error and catch that error. So it's just a way of programming a little more defensively. Some languages have this, some languages don't. But in general, it's a good practice. It makes your code better designed because it just is less vulnerable to mistakes by you, colleagues, or anyone else using the code. So let me change this back to 3 just to be our default. But now I'm using n in both places. And if I do make Mario, ./Mario, we're back to where we originally started. But the code's a little more better designed. And let me note this too. All this time, I've been mentioning that there's correctness is important, design is important. There was also this matter of style. I've been very deliberately writing pretty code, if you will, not just the syntax highlighting, which is automatic, but notice that I keep indenting everything nicely. Anytime I have curly braces, like on lines 4 and 14, everything is indented one level. When I have additional curly braces on lines 7 and 13, everything is nicely indented as well. Technically speaking, the computer does not care about that kind of white space, so to speak. And you could really make a mess of things like this because you have a strange sense of style or just because you're being a little sloppy. But this code is actually still correct. If I recompile it, let me open up my terminal window, make Mario. No errors, ./Mario, it works perfectly fine. But you can imagine just how annoying this now is to read, like certainly for a TA, but certainly for you the next day, certainly for a colleague who has to read your code. This is just bad style. Like it still works, and it's well designed in that like you're writing code defensively, you're using a constant, but my God, the style is atrocious. Now, you'll often find that there's tools that can help you format your code for you in a manner consistent with the course's or a company's style, but this is the kind of muscle memory you'll want to develop over time too. Take VS Code suggestions as it's outputting lines of code for you because it's trying to format your code in a readable way. And oh my God, if and when you do have bugs in your code and things aren't even indented properly, there's no way you, the human, are going to be able to wrap your mind around what's happening and where. Like you're just making the problem harder for yourself. So do get into this habit too of manifesting good style as well. All right, well, let me propose that we don't only want a 3 by 3 grid. We want this to be a little more dynamic. So suppose we moved away from a constant to just using an integer called n. And let's ask the user for the size of this grid as by prompting them with getInt as we've done before. And I'll store it in n here. And then I can go ahead and more dynamically run make Mario to compile it. Whoops. Oh, I screwed up accidentally. What is it suggesting I do, albeit cryptically? Yeah, I forgot to include the CS50 header file up top, and that's why it doesn't know that getInt is in fact valid. So that's an easy fix. I'm just going to go up here and include cs50.h. Now I'm going to clear my terminal and rerun make Mario. Now we're good. /Mario. And now notice I'm prompted for size. So if I type in 3, it's the same as before. If I type in 10, it's even bigger. But it happens all now automatically. But there are some things that we're not detecting. For instance, suppose I type in cat. Well, that's handled by the getInt function, as I claimed earlier. That's one of the features of using a library. You don't have to deal with erroneous input. But we only designed a function called getInt to get you an integer. We don't know if you want it to be positive, negative, 0, or some combination thereof. And it's kind of weird to allow the user to type in like -1 for the size of the grid, or -3 for the size of the grid. And indeed, your code does nothing. So at least it's not crashing. But that's kind of stupid, right? Like, it'd be nice to force the user, if they want a grid, to give us a positive value. So how could we do this? Well, I could go up here, and I could say something like if n is less than 1, so if it's 0 or negative, which I don't want, what could I do? Well, I could say, well, prompt the user again for the size. And now notice, I'm not declaring n again, because once it exists, you don't have to mention the data type again. We said that earlier. But this is kind of stupid. Why? Because now when you've given the user a second chance, OK, now maybe I'll do, all right, if this version of n is less than 1, well, let's just go and prompt the user a third time. I mean, you can kind of see where this is stupidly going. Like, this can't be the right solution, to keep typing recursively the same thing again and again. Like, where would it stop? You'd have to give them a finite number of chances, or just make a mess of your code. So what would be intuitively a better solution here? Yeah, so some kind of loop. We've seen a while loop. We've seen a for loop. So maybe one of those. So let me try this. Let me delete this messiness and just go back to the first question. And let me do this. So while n is less than 1, so while the number is not what we want, let's just prompt the user in a loop this time for the size again. Now here too, this is better, because it's only 2 requests for information. But clearly, lines 6 and 9 are pretty much identical, other than the int. And if I went in and changed the size, if I add this, if I change the wording here, change it to a different language, like I have to change it in 2 places. That's bad. Copy, paste, bad. So what might be better? Well, it turns out there's another paradigm in C that you can use that gets around this problem, this duplication of code. It would be much nicer if I just write this code once. And I can do that using a third type of loop called a do-while loop. So it turns out in C, you can do this. If you want to get the value of a variable, like n, first just to create the variable without an initial value. So int n semicolon means we don't know what value it has, yes, but that's OK. We're going to add a value to it eventually. Then I'm going to say this, do, literally. I'm going to open my curly braces. And what do I want to do? I want to assign to n the return value of getInt, prompting the user for size. Well, when do you want to do that? I want to do that while n is less than 1. And this code now achieves the exact same goal, but by never repeating myself. Why? Well, notice on these lines of code now, I'm literally saying, on line 6, give me a variable called n of type integer. It doesn't have a value initially, but that's fine. You can do that. Line 7 says, do the following. What do you want to do? GetInt, prompting the user with the word size, and just store that value in n. But because C code runs top to bottom, left to right, now it's reasonable on line 11 to ask that question, OK, is the current value of n, which it definitely got on line 8, less than 1? And if the user didn't cooperate, they typed in 0 or -1 or -3, what's going to happen? It's going to go back up here and repeat, 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 everything in the do-while loop. So a do-while loop in C, which is not something some other languages have, like Python, if you know it, does not have a do-while loop. This is perhaps the cleanest way to achieve this, even though it's a little weird that you have to declare your variable, create your variable up top, and then check it down below. But otherwise, it's similar to a while loop. It just flips the order in which you're asking the question. Any questions on this construct? And do-while in general is super useful when you want to get input from the user and make sure it meets certain requirements. All right, so now that we have this building block after that interlude, how can I go about cleaning up this code? And then let's conclude by taking a look at things that our code can't do or can't do very well or correctly. Let me propose that in a final version of Mario, let me just add what are called now some comments. So it turns out in code in C, you can define what are called comments, which are just notes to self. Some of you discovered these in Scratch. There's little yellow sticky notes you can use to add citations or explanations. In C, there's a couple of ways to write comments. And in general, comments are notes for yourself, for your TA, for your colleague, as to what your code is doing and why or how. It's a little explanatory note in English or whatever your human language might be. So for instance, what I might do here in my implementation of this version of Mario, I might first ask myself a question like, I might first make a note to self like this on a new line above this first block of code, get size of grid. It's just an explanatory remark in any terse English that generally explains the next 6 or so lines, the next chunk or block of code, if you will. It would be a little excessive to comment every single line. At some point, the programmer should know what individual lines of code do. But it's nice to be able to kind of glance at this comment on line 6 that starts with 2 slashes. And it gets grayed out because of syntax highlighting. It's not logic. It's just a note to self. It generally gives me a little cheat sheet as to what the following lines of code should be doing and or why. And then down here, well, there's a second block of code that's a bunch of lines. But together, this just what? Prints grid of bricks. And so it's another comment to myself that just makes it a little more understandable what these 20 some odd lines of code are doing by adding some English explanations thereof. But now that I have these, wouldn't it be nice if I could kind of abstract these pieces of functionality away, this getting of the size and this printing of the grid? In other words, suppose that you didn't know where to begin with this problem. And the problem at hand were literally implement a program that prints a grid of bricks of some variable size, 3 or 4 or 5 or whatever the human types in. If you have really no idea where to start, comments are actually a good way of getting started, because comments can be an approximation of what we called last week pseudocode. Pseudocode is terse English that kind of gets your point across, like for the phone book searching like last time. So if you didn't really know where to begin, you could do something like this. I could, for instance, just say get size of grid as my first step, and then print grid of bricks as my second step. And that's it for my program thus far. This is now implemented in pseudocode. I have some massive placeholders there, like I still have work to be done, but at least I have a high-level solution to the problem in comments. And now I can even go this far. I could say, well, let's suppose that there's just a function already that exists called getSize. I could do something like this. I could do int n equals getSize. And now I just have to assume for the moment that some abstraction called getSize exists. It doesn't. This does not come with the CS50 library. But I could invent it, I bet. How else might I proceed? Well, let's just assume for the moment that there's also a function called printGrid that just prints a grid of that size n. So here, too, is an abstraction. These puzzle pieces don't exist. These functions don't yet exist. But in C, just like in Scratch, I can create my own functions. How do I do that? Well, let me go down later in the file. And by convention, you generally want to leave main at the top of your code. Why? Because it's the main function, and it's just where the human eye is going to look to see what some file of code does. And let me do this. I want to create a function of my own called getSize, whose purpose in life is to get the size that the user wants. I want this function to return an integer. And the syntax for doing that is to write, similar to a variable, the data type that this function returns. I don't need this function to take any inputs. And so I'm going to use a new keyword that we've actually been using thus far, more on it another time, just called void, which just means this getSize function does not take any inputs. It does have an output. It outputs an int. And this is just the weird order in which you write it. You write the output format, the name of the function, and then the inputs, if any, inside of parentheses. And now I can implement getSize. But I've already implemented getSize, or at least now at this point in the story, I at least know concretely what to do. And I could figure out eventually, with some trial and error perhaps, all right, if I declare a variable and I do the following, n equals getInt, prompting the user for size, and I keep doing that while n is less than 1, once that block of code is done, here is a new keyword in C where you can return that value n. So I keep referring to these values that some functions return as return values. In C, there's literally a keyword called return that will hand back to any function that uses that function the value in question. So in a nutshell, between lines 15 and 21 now, here is some code identical to our solution earlier that gets a value n from the user that is positive. It's 1 or 2 or higher. It's not 0 or it's not less than 1. And as soon as we've got that value, we hand it back as a return value. Notice how I'm using this function on line 7. Just like with getInt, just like with getString, I'm calling the function, nothing in the parentheses in this case, but then I'm using the assignment operator to copy whatever its return value is into my variable n. And so now I have a function that didn't used to exist called getSize that gets me a positive integer, no matter what. And now for the grid, how do I do this? How do I invent a function called printGrid that takes a single argument, a number, and prints a grid of that size? Well, let's go down here. I'm going to write the name of this function, printGrid. This function just needs to print. It has a side effect, as we keep saying. So I'm just going to say it has no return value. It's just void. It doesn't have an output per se. It's just an aesthetic side effect. But it does take in an argument. An argument is an input. And the syntax for this in C is to name the type of the input it takes and the name of the variable. And I could call this anything I want. I'll call it size. I could call it n. And it's OK to use the same variable in different functions, but I'll call it size just to be distinct. And then in this function, I'm just going to copy from memory the same code as before. For int I gets 0, I less than size instead of 3, I plus plus. Inside of this, for int j gets 0, j is less than size, j plus plus. And inside of that, print out with printf a single hash, print out after that loop a single new line, and that's it. Now, I did this fast, admittedly, but it's the same code that I wrote earlier. But now, just like I did with Scratch, let me just arbitrarily hit Enter a bunch of times to like move the code out of sight, out of mind. Now I have abstractions. I have puzzle pieces that now exist called getSize and printGrid, syntax for which takes some getting used to, but they now just exist. Except I do need to do one thing. Because C is a little naive, if I try to do make Mario now and hit Enter, implicit declaration of function getSize is invalid. And we've seen that before when I hadn't included a file. Right? When I hadn't included CS50 library, getInt didn't work. But that's not the issue here, because this is not from a library. I just invented this. C kind of takes you literally. And if you define these functions at the bottom of your file, they don't exist on line 7 or 10. So I could do this. I could, all right, fine. Well, let me just kind of highlight all of this, cut to my clipboard, and paste it up here. This would solve the problem. I could just move all of those functions at the top of my file. That's kind of annoying, because now main is like at the bottom of the file. It's going to take longer to find it. It's just, that's not a clean solution. So let me put it back where it was at the bottom. And let me do this. This is the only time in CS50 and really in C programming where copy paste is reasonable. If you copy and paste the first line of code from each function and then end it with a semicolon, you can tease the compiler by giving it just enough of a hint at the top of the file that, OK, these functions don't exist till down later, but here's a hint that they will exist. This is how you can convince the compiler to trust you. So those other functions can still be lower in the file, below main. But now when I do make Mario, oh, damn it. Oh, I said print instead of printf. That's my bad. Printf. So if I do make Mario /Mario, now I can type in 3, and we're back in business. Now, this was a very heavy-handed way and long way to get to a much more complicated solution. But this solution, in some sense, is better designed. Why? Because now, especially without the comments, I mean, look how short my code is. My main function is literally 2 lines of code. Why? Well, I kind of factored out the juicy stuff into its own functions. And now, especially if I'm working with colleagues or others, you could imagine splitting up large programs into smaller parts, having different people implement different parts, so long as you all agree in advance on what those inputs and those outputs actually are. All right, so let's now consider what computers can do well and not so well. C indeed supports a whole bunch of operators mathematically, via which we can do addition and subtraction, multiplication, division, and even calculate the remainder when you divide one number by another. In fact, why don't we go ahead and use these in a very simple program and make our very own calculator. So let me go over here to VS Code. Let me go ahead and create a new file called calculator.c. And in this file, let's go ahead and first include a couple of now familiar header files, CS50.h as well as standardIO.h. Let's go ahead then and declare main with int main void. And then inside of main, let's do something relatively simple. Let's declare an int and call it x and set it equal to whatever the return value is of getInt, prompting the user for a value for x. Let's then give ourselves a second variable. We'll call it, say, y. Set that equal to the return value of another call to getInt, prompting the user this time for that value y. And then let's very simply go ahead at the very end and just print out, say, the sum of x plus y, a super simple calculator. So I'll use printf, quote unquote, %i for integer, \n to give me the new line. Then I'm going to go ahead and do x plus y to indeed print out the sum. Let me go down to my terminal window now. Let me do make calculator in order to compile the code. No error messages, so that's good. Let me do /calculator, and let's do something like 2 plus 2, which of course should equal 4, and it does. But it turns out that sometimes there are going to be limitations that we bump up against. And let me get a little more ambitious here. Let me clear my terminal window, and let me go ahead and rerun calculator again. And this time, let's type in 2 billion for x, and let's type in the same for y. And of course, now the answer of 2 billion plus 2 billion should, of course, be 4 billion. And yet it's not. So curiously, we see, of all things, a negative number here, which suggests that somehow the plus operator doesn't quite work as well as we might like. Now, why might this actually be? Well, it turns out that inside of your computer is, of course, memory, or RAM, random access memory. And depending on the size of your computer and the type of computer, it might very well look a little something like this. A little circuit board with these black little modules on it that actually contain all of the bytes of your computer's memory. Unfortunately, you and I only have a finite amount of this memory inside of our computers, which means no matter how high we want to count, there's ultimately going to be a limitation on how we can count, because we only have a finite amount of memory. We don't have an infinite number of zeros and ones to play with. We have to actually be bounded ultimately. So what's the implication of this? Well, it turns out that computers typically use as many as 32 bits, zeros or ones, to represent something like an integer, or in C, an int. So for instance, the smallest number we could represent using 32 ints, of course, using 32 bits, of course, would be 0. 32 zeros like this here. And the biggest number we could represent is by changing all of those zeros to ones, which in this case will ideally give us a number that equals roughly 4 billion in total. It's actually 4,294,967,295 maximally if you set all 32 of those bits to ones and then do out the actual math. The catch, though, is that we humans and computers in general also sometimes want to and need to be able to represent negative numbers. So if you want to represent negative numbers as well as positive numbers in 0, you can't really just start counting at 0 and go all the way up to roughly 4 billion. You got to kind of split the difference and maybe allocate half of those patterns of zeros and ones to negative numbers and the other half roughly to positive numbers. So in fact, in practice, when you're using even as many as 32 bits, the highest most computers could count, certainly in a program like this in C using an int, would be roughly 2 billion. That is 2,147,483,647. But the flip side of that is that we could also now, using different patterns of bits, represent negative numbers as low as -2 billion, give or take. But the implication then, of course, is that if we only have a finite number of bits and can only count so high, at some point we're going to run out of bits, so to speak. In other words, we encounter what's generally known as integer overflow, where you want to use more bits than you have available, and as a result, you sort of overflow the available space. What does this mean, in fact, in real terms? Well, let's suppose that you only have 3 bits, but I'm going to gray out a 4th bit just to convey where we'd like to put an additional bit ultimately. If this, of course, is 0, per week 0's discussion, this is 1, 2, 3, 4, 5, 6, 7. Now, ideally in binary, if you want to add one more to this value 7, you're going to have to carry the 1 mathematically, and that would ideally give you 1, 0, 0, 0. But if you don't have 4 bits and your computer's only sophisticated enough to have 3 bits, not even 32, but 3, the implication is that you're effectively representing not 1, 0, 0, 0, but rather 0, 0, 0. There's just no room to store that 4th bit that I've grayed out here, which is to say that your integer might overflow, and as soon as you get to 7, the next number, once you add 1, is actually going to be 0. Or worse, as we've seen here in my code, a negative value instead. So what could we do to perhaps address this kind of concern? Well, C does not have just integers or ints. It also has longs, which as the name suggests, are just longer integers, which means they have more bits available to them. So let me go back into my code here. I'll clear the terminal window. And let me go ahead and change my integers to literally long here, long here. I'm going to have to change my function in CS50's library to be not getInt, but getLong. And that's indeed another function we provide in the library. Let me change this getInt to getLong as well. I'll keep my variable names the same, but I do need to make one other change. It turns out that printf also supports other format codes. So not just %i for integers or %s for strings, but also, for instance, %li for a long integer, as well as %f for floating point values with decimals. So with that said, let's go ahead and change my printf line to be not %i, but %li. Now let me go ahead and do make calculator again, enter. No apparent errors now. /calculator, and 2 plus 2 still equals 4 as before. But now if I do calculator again, and let's do 2 billion again, as well as 2 billion for y, previously, we overflowed the size of an integer and got some weird negative number because the pattern was misinterpreted, if you will, as a negative number instead. But a long, instead of using 32 bits, conventionally uses 64 bits, which means we have more than enough spare bits to go when we add 2 billion plus 2 billion. And now, in fact, we get the correct answer of 4 billion, which does fit inside of the size of a long. Now, a long can count up quite high. And in fact, it can count as high as this, 9 quintillion. And so that will give us quite a bit more runway. But of course, it too is ultimately going to be finite. So if you have numbers that need to go bigger than that, you might still very well have a problem. Now, there's another problem that we might run into as well, and we can see it in the context of even this simple calculator. Computers also suffer from, potentially, what's called truncation, where especially when you're doing math involving floating point values, that is, numbers with decimals, you might accidentally, unknowingly, truncate the value, that is, lose everything after the decimal point. So in fact, let me go back to VS Code here. I'll clear my terminal window, and let's still use longs, but let's go ahead and use division instead of addition here. So let me change this plus to a divide operator. Let me go ahead and recompile the code down here with make calculator. Let me go ahead and run /calculator, and let me go ahead and do something like 1 for x and 3 for y, and we'll see that, well, wait a minute, 1 divided by 3, I learned, should be 1/3, but in a floating point value, that should be 0.33333, maybe with a little line over it in grade school, but really an infinite number of 3s. And yet we seem to have lost even one of those 3s after the decimal point, because the answer is coming back here as just 0. So why might that be? Well, if I know that two integers, when divided one by the other, is supposed to give me a fraction, a floating point value with a decimal point, I can't continue to use integers, or even in this case longs, which do not have support for decimal points. So let me go ahead and change this format code here from %li to %f, which is, again, going to represent a floating point value instead of a long integer or even an integer. And let me go ahead further and define maybe a third variable, z, as a float itself. So I'll give myself a variable z equals x divided by y. And now, rather than print x divided by y, let's just go ahead and print z. So now I'm operating in a world of floating point values, because I know proactively that a long or an int divided by another such value, if it's meant to have a fraction, needs to be stored in a floating point value, something with a decimal point. Well, let me go down to my terminal window here and rerun make of calculator. Seems to work OK. /calculator, and let's do 1 divided by 3 again. And still here, we see all zeros. So we do at least see a decimal point. So we've made some progress thanks to the %f and the float. But it seems that we've already truncated the value 1 divided by 3. So how do we actually get around this issue? Well, if you, the programmer, know that you're dealing in a world that's going to give you floating point values with decimal points, you might very well need to use what's called a feature known as typecasting. That is, convert one data type to another by explicitly telling the compiler that you want to do so. Now, how do I do this? Well, let's go back to my code here. And if the issue fundamentally is that C is still treating x and y as integers, or technically longs with no decimal point, and dividing one by the other therefore has no room, so to speak, for any numbers after a decimal point, why don't I proactively do this? Let me, using a slightly new syntax with parentheses, specify that I want to convert x proactively from a long to a float. Let me specify proactively that I want to convert y from a long to a float as well. And now let me go ahead and trust that in z should be the result of dividing not a long by a long or an int by an int, but rather a float by a float. Let me clear my terminal window, run make calculator again. Seems to work OK. /calculator, and now 1, 3, and hopefully now we actually see that my code has outputted 0.333333. And I think if we kept showing more numbers after the decimal point, we'd theoretically see as many of those 3s as we want. But there is still one more catch. And especially when we're manipulating numbers in this way in a computer using a finite amount of memory, another challenge we might run up against, besides integer overflow, besides truncation, is this known as floating point imprecision. Just as we can't represent as big of an integer as we want using int or long alone, because there is going to be an upper bound, there's similarly going to be a boundary on just how precise our numbers can be. And indeed, let's go back to VS Code here. I'll clear my terminal window yet again. And this time, let me use some slightly unwieldy syntax to specify that I don't want to see the default number of numbers after the decimal point, which %f gives us automatically. Let's go ahead and show me 20 decimal point numbers after the decimal point. And the weird syntax for this is to do not %f, but %20 to indicate to C that I want to see 20 digits, not the default after now the decimal point. Let me rerun make calculator. Let me do /calculator again, and let's do 1, let's do 3. And now this is even weirder, right? From grade school, you presumably learned that 1 divided by 3 is, of course, 1/3. But that should be 0.33333 infinitely many times, or on paper with a little line over it. But the computer is doing some weird approximation here. It's a whole bunch of 3s, and then 43267440795990. Well, what's really happening under the hood? Well, again, is this issue of floating point imprecision. If you only have a finite number of bits, and in turn a finite amount of memory, the computer can really only be so precise intuitively. Equivalently, the computer has decided on some way of representing floating point values. But the catch is, per grade school math, there's an infinite number of numbers out there and an infinite number of floating point values, because you can keep adding more and more digits if you want. So the computer, given the way it's implementing these floating point values, is essentially giving us the closest approximation that it can. Now, how can we go about improving the situation? Well, there is one alternative. Instead of using float, I can use something called a double, which, as the name suggests, uses twice as many bits as a float. So instead of 32 typically, it will use 64. And that's just like the difference between a long and an int, which gave us more bits. But in this case, this will be used for more precision. Let's go ahead and cast x to a double. Let's cast y to a double. And now let's go ahead and, using the same format code, %.20f is still OK for doubles. Let me do make calculator. Let me do /calculator. And now let me do 1 divided by 3. And we still have some of that imprecision. And we'd see even more of it if we looked at more than just 20 digits. But now we have more 3s after the decimal point. So it's at least more precise. But it's not perfect, but it's at least more precise. So these kinds of issues then are going to be necessary to keep in mind anytime you do something numerically, scientifically, at least with a language like C, where you're going to bump up against these real world limitations of hardware and in turn language. Now later in the semester, we'll transition to a language called Python, and that's actually going to solve at least one of these problems for us, but just automatically giving us more bits, so to speak, as we need them, at least for integers. But even the issue of floating point imprecision is going to remain. Now, just how real world are these issues? Well, back in the year 1999, we got a taste of this when the world realized in the years leading up to that date that it might not have been the best idea to implement computers and software therein by storing years using just 2 digits. Like instead of storing 1999 to represent the year 1999, a lot of computers, for reasons of space and cost, were in the habit of kind of cutting a corner and just using 2 digits to keep track of the year. The problem with that is that if systems were not updated by the year 1999 to support the year 2000, 2001, and so forth, is that just like before with integer overflow, some computers might add 1 to the year in their memory, 99. It should be the year 2000, but if they're only using 2 digits to represent years, they might mistake the year, as some systems may very well have, for the year 1900 instead, taking literally a big step backwards, if you will. Now, you'd like to think that kind of issue is behind us, especially as we understand all the more about the limitations of code and computing. But we're actually going to run up against this very same type of issue again in just a few years. On January 19th in the year 2038, we will have run out of bits in most computers right now to keep track of time. It turns out years ago, humans decided to use a 32-bit integer to keep track of how many seconds had elapsed over time. They chose a somewhat arbitrary date in the past, January 1st, 1970, and they just started counting seconds from there on out. And so if a computer stores some number of seconds, that tells the computer how many seconds have passed since that particular date, January 1st, 1970. Unfortunately, using a 32-bit integer, as we've seen, you can only count so high, at which point you overflow the size of that variable. And so potentially, if we don't get ahead of this as humans, as a society, as computer scientists, on the date January 19th, 2038, that bit might flip over, thereby overflowing the size of those integers, bringing us back computationally to December 13th, 1901. So this is to say now with all of this computational ability in code comes a responsibility to actually write correct code. Next week, we'll peel back some of these layers. But for now, this was week 1. And best of luck on problem set 1.